Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Now that we've gone through the nature of active galaxies and looked at the nature of supermassive black holes that appear in the centers of those galaxies, it's time to look at the largest issues in the universe, meaning cosmology, the cosmological study of the Big Bang and the entire universe. So the first thing we're going to talk about is some underlying assumptions that we have about the nature of the universe before we actually get through all the rest. And the first most important underlying idea is what I call piece zero, is the homogeneity and isotropy of the universe. And so cosmology, again, is the study of the entire universe and the physics, distribution, motions of stuff in the universe and how it evolves with time, what the age, origin, and fate of the entire universe is, and it relies upon the cosmological principle that says that there's nothing special about our location in the universe other than that it's our particular little home. So therefore, we should see that but now we have two definitions, isotropy and homogeneity. So the principle is that if we have isotropy around any point in the universe with this principle, that means the universe is pretty much the same everywhere. And that's going to color everything we do from here on out. In fact, this is a fundamental aspect of the entire nature of everything, and that includes everything. Homogeneous everywhere doesn't just mean this type of thing is here. It means the laws of physics are the same there. So that tells us that anyone, anywhere, sees roughly the same thing no matter where they look. All right, so to help us with this thing, we are going to start looking at the Hubble Deep Field. We talked about this prior. This was one of the most important images taken in 1996 of taking a huge amount of Hubble time and staring out into space with the Hubble Space Telescope and viewing what can be seen. And this incredibly deep field stares back at us, and we see over 1,500 galaxies of various states and evolution. Some are closer, some are nearer, and this is a very small piece of the sky. But what we can see in this is that the view of the sky shows us that we really just see galaxies out there, so we may actually have something here. All right. We don't live in a special place in the universe. What does that end up meaning? Well, let's look at what we see when we do surveys, such as this is the APM Galaxy Survey, which is looking at the southern galactic pole. If we look around the southern galactic pole, and there's a huge area of sky, like 4,300 square degrees in the sky, this map of about 185 images combined together, all stacked together to make this survey. And they and what was looked at by this particular group, by Maddox et al. In 2003, is they found approximately 20 million galaxies in this area. So where the Hubble Deep Field saw a lot of galaxies inside a very narrow beam, this shows that things roughly are kind of smoothly distributed, except if we look at those kind of webby sort of structures that are in the nearby area. But if we think about the deeper colors, it almost looks the same everywhere. It's almost like you could take a bucket of it and center a box on it, and it'd be roughly the same appearance inside that box, no matter where you put the box on this field. And that's what we call homogeneity. So let's look at the history of the nature of this. And if we go back in time, we find that the universe this concept of the homogeneous and isotropic universe had to take time to develop. In Ptolemy's original formulation of the cosmos, as we saw very, very, very early on, Claudius Ptolemaeus said that if the Earth was at the center and all the planets orbited it and the stars were far out. Well, this kind of gave us an isotropic view, meaning if we're in the Earth, we're in a very special place, the Earth, and we looked out, we see stars in pretty much every direction. Now, this was altered by the idea that you had more stars along the Milky Way than others, so really it wasn't a very good isotropic view. And the planets orbited the sun, they orbited the Earth, They orbited the Earth and went around, but in general, the conceptualization was that the ancient Greeks and many people around there thought that this would be something that is about right, and that's why they drew it using perfect circles, is because while we see some imperfections, they thought that over the largest size scales, it would smooth out, and philosophically, they wished to have it this way. So This was the picture of ancient Greece and ancient Egypt. So when we get to the Renaissance in Europe, in the middle of the 1400s, late 1400s, early 1500s, we find that we see a slightly different alteration of things, getting out into the cosmos, pushing humanity different with Nicholas Copernicus's view of the cosmos with the sun at the center, and then again isotropic based upon the sun's perspective, not the Earth's perspective. So that means that the Earth's perspective is not as important as, say, the sun's perspective. So now we have an idea that we have multiple perspectives. Galileo came along and tried to assert Copernicus' view by saying that the Earth must not be at the center. And one of his, he used some major justifications when he first looked through the telescope. One of the major justifications, as you're seeing in this image, is that he saw the phases of the moon, and by looking closely at the moon with a telescope, you see that the moon has ridges and lumps, and you also see Jupiter has additional starry messengers around them, and those starry messengers are separate stars that orbit Jupiter. And so he posited that if the Earth was moving, it could take the moon with it in just the same way that as Jupiter moves, it takes its stars with it. However, for him, the more important thing was that Venus's phases could not be replicated in Ptolemy's view of the cosmos. They demanded something like Copernicus' view. Now, Galileo at the same time was ignoring the work being done by Johannes Kepler, who actually sent him some of his work, but Kepler himself said it was too difficult to understand. And Kepler said to Galileo, look, we can put, instead of circles like Copernicus did, we can use ellipses, and it works really well. Galileo was fighting with the Pope and getting himself under house arrest, so he didn't actually listen to Kepler or read about him or even acknowledge him. But they were roughly coincident. And it ended up that Kepler's view of the cosmos was the correct one. See, Galileo was fully Copernicanized, but Kepler said, well, let's use some ellipses, and it worked. And then along came, using those ellipses, Sir Isaac Newton, who then said, we have that laws of physics are the same. So why does the moon orbit the Earth? The moon orbits the Earth because it's falling towards the Earth, and it has a lateral motion around the Earth. So as it falls, it starts to fall, but then it has a lateral motion whose speed is so great that by the time it would have hit the Earth, it has moved a long ways. So the attractive force of gravity keeps it in a circular orbit. And so he said, well, if that's what's happening, then the Earth is going around the sun by the same principle, and Jupiter is going around the sun by the same principle, and all the stars in the sky are under the influence of gravity. And therefore, all of the laws of physics can be combined into three major laws: the law of inertia, the law of forces, the definition of a force, and the law of equal and opposites. So these ideas allowed to say, well, we no longer need a mystical structure such as a celestial sphere devised by Ptolemy and Aristotle and even supported by Copernicus. All we need is these laws, and they tell us how things move. And what that said is that these laws, if they apply here and they apply there, we're now branching out and applying physical laws to things we cannot get to. And that's interesting. It's really interesting. We're now saying that the laws of physics of the heavens are the same as the laws of physics on Earth. That becomes really critical. And that's what we did. That's how we divided up the world. And I mean, if you go back to the ancient times, back to pre-Ptolemy, if you look at Aristotle's view, Aristotle's entire physics was based on the idea that there were two different realms of physics, one in the celestia and one in the materia. And so they were different. However, Newton came along and finally said, nope, they're the same. All right, this matters a lot because we're going to try to demonstrate the largest size scales of the cosmos. And what do we mean by largest size scales? We don't mean things measured by parallax or proper motion or the High-Z fitting of main sequences to HR diagrams, nor do we even think of getting out to the Large Magellanic Cluster or out to M31, the Andromeda Galaxy, at 10 to the 6th parsecs. No, we don't even think about getting out to M81 or the Virgo Cluster, which is 60 million light years away, or even what we can find with the Tully-Fisher relation that gets us out to 10 to the 8th parsecs, or even supernovae, which get us out to almost 1 billion parsecs. No, we have to actually get out to where our measurements must be measured in Redshift, where we measure things on the order of hundreds of millions of light years or billions of light years. That's what we mean by the largest size scales of the universe. And this kind of homogeneity and isotropy only appears on the largest size scales. So when we look closely, we say, what do we mean by homogeneous and isotropic? Okay, a forest looks the same when you're in the middle of the forest, roughly in any direction. That's why it can get confusing to get lost in a forest, because you don't know which way to go, because all the trees look the same. And so your only way, and if it's a cloudy day, you don't even have the sun to help you. If it's a rainy, cloudy day, you better have a trail and you better have a map. And that's all there is to it. Otherwise, north is as good as south, is as good as east, is as good as west, and you can't tell one from the other. That's what we mean by isotropic. The cosmological principle says it's, again, largest size scales. There's no special place. It's homogeneous. Isotropic means there's no special direction. And largest size scales meaning we have a big box that's on the order of 100 million light years or greater. And the two little sketches below show us those to demonstrate the concepts of homogeneity and isotropy. So homogeneity then says, of course, we look at the average density of matter is about the same. So we say, how many counts of galaxies can we do over here? In this box, the average in this box size, say 100 million light years on a side, we get so many galaxies. And if we just change the position of the box and just say, well, if we go over here and make a box that is 100 million light years on a side, then we should have roughly the same number of galaxies. Now, we probably will have, 1,000 or so more galaxies or less, but on average, it doesn't matter. The total number of galaxies, it's not like you're going to have 0 here and a trillion over there. That's just not how that works when you get to the largest size scales. And as you can see from the APM Galaxy Survey, there's not really a lot of holes. There are no holes in galaxy distribution. It's not like, oh, over here, nobody has ever said anywhere, this is the place in the sky where you look to find galaxies, because that's where galaxies are, except because of the blockage by the Milky Way. Everybody who says, like, well, if you could look through the Milky Way, you should see galaxies, but no one has ever said, there's no galaxies there, right? It's kind of weird. Nobody's ever said that. It could have been said, that could have been how the world would have worked. The world can work however it wants to, but it worked out that there are galaxies in every direction. The universe is therefore pretty smooth on the largest size scales, but when you look closer, everything looks kind of lumpy, because you know what? A boat is not the same thing as a building, so the universe is lumpy and unsmooth on small size scales. And so the solar system is lumpy compared to the view around the sun in a few light years. But even then, when you get out a few light years, you start to say, oh, there's some big stars and small stars. And you get even further out and you say, oh, there's a galactic disk. You get even further out and you say, oh, there's the local group. And you get out even further and say, oh, there's the Virgo cluster. And it has to get out to the point where you look at superclusters of galaxies before you start to say, oh, now we're starting to get kind of even distributions of superclusters of galaxies. That's what we mean by homogeneity. Isotropy, on the other hand, is to say, look in some direction. Doesn't matter where you look. Start from where you're looking from. Look out in every direction. What do you see? Do you see roughly the same things in every direction? Again, that's not the same thing as a homogeneity. Homogeneity can be homogeneous, but not looking the same in all directions. That is possible, because there could be an innate structure, just like a brick wall, like we saw in the previous. A brick wall is certainly homogeneous because the lay of the bricks. But it isn't isotropic. And let's go back just to see that. See the brick wall? Brick wall is definitively homogeneous because no matter where you put your bin, you see a a pattern of bricks. However, there is a preferred direction, or at least there are directions where you can orient yourself left and right, and there's other directions where you go, okay, this is little stubby lengths and they're long lengths. So a brick wall is not isotropic, but is certainly homogeneous. And now this view of the the bullseye thing is certainly isotropic around the center, but is not homogeneous because you can go out to the edges of it and you see lines spreading. You don't see a line spreading out away from, say, the tip of one of these. You only see them spreading out from the center. So it's isotropic only around the center and is not homogeneous. Our trick is that we want both. We want both isotropy and homogeneity. So when we've determined that the cosmos seems to be homogeneous from our vantage point, and if we look out into the cosmos, we see that it looks the same in deep, deep, deep surveys in every direction, such as the Hubble Deep Field. We see roughly these things, this kind of thing, no matter which way we look. Now, if you take the cosmological principle, it says there's nothing special about our location in the universe, and that's been supported by the idea that we moved away from Ptolemy's place, where Ptolemy and Aristotle said the Earth is the center, that's the center of everything, and we're the center, we're the most important place. And then you went to Copernicus and said, no, we're off center. And then Galileo said, well, yeah, we're definitely off center. Kepler said, things move. And then Newton came along and said, it's just laws of physics, it's just stuff moving. And that began the idea that there's nothing special about our location in the universe. And then if you make measurements that demonstrate that you are isotropic around that point in the universe, it doesn't matter which one, any universe point, then you have combined isotropy around any point in the universe with the cosmological principle, and that means isotropy everywhere. So that means if you have isotropy everywhere, then it must be homogeneous everywhere. And therefore, anyone, anywhere in the universe sees things no matter which way they look. Now, what makes us think that this concept is that we're actually in nothing special about our location in the universe? And that arises from the idea of Newton's ideas about the laws of physics. We branch the idea from the concept of laws of physics, not from pictures. The pictures actually prove to us that things can be explained with laws of physics. So it's the explanation of the pictures using existing laws of physics. We don't have to make up new laws of physics in one direction to explain stuff over there in this direction, whereas if we look in this direction, we have to use different laws of physics because things seem to be behaving differently over there. It's not like we have to say, hey, in this direction of the sky, we have to use Newton's gravitational constant to be 100,000 times more than it is over here because things seem to be moving really fast over here in their orbits when they get in this part of the sky, if it's a planet, or distant galaxies in this direction of the sky seem to be moving really fast, then that's just what would be required if it was not isotropic. So when we think about it, the laws of physics must be the same because we see things that can easily be explained by the existing laws of physics, no matter which way we go. We also start with that as an assumption, as a very modern assumption, that the universe behaves according to laws and we can make our measurements where we can, not where we must. So there's a difference. So you can say, oh, this is where we must look in order to find this gravitational constant. No, we look where we can because that's where we can build a telescope. We look where we can because the Milky Way is not blocking that view. So that's what we mean by that, not where we must because, hey, if we want to see this law of physics, we look in this direction because that's the neat place over there. That's not the case. The laws of physics are the same everywhere. Therefore, there is nothing special about our location. Our location is the same laws of physics as any other location. And if you have isotropy plus that idea, then everything's the same across the entire universe. All right, let's take a little history lesson. Back in 1917, Albert Einstein was developing general relativity. And when he finished developing it, he said, well, what are the cosmological implications? What does this mean for the universe? And in 1917, pretty much everybody thought the Kapteyn model of the Milky Way was favored, where it was an island universe and that was the universe, and no one really knew about the distance to the spiral nebulae. Remember, that was a big, big, big argument, the argument of the Great Debate, which was about to come about in a few years. And so this was an important thing. The next thing is nobody really had good calibrations at the time of the period luminosity relationship that Henrietta Leavitt was working on, but they're first just coming in by Hertzsprung, and Leavitt was like shaking her head saying, I could have done it. I could have been a contender, but it was blocked. Darn. So she was angry, but at least it got done, and she was the one who actually discovered the period luminosity relationship for Cepheids in our libraries. So once these things those calibrations got done by everyone, then things could be progressed. Now Einstein, at 1917, because the universe was not known to be expanding, and the universe was known to only be the stars that were seen in the sky, that was the universe, he applied the cosmological principle to that, to the general relativity, and he found, hey, this is kind of weird. Because gravity is here, and space-time is here, and stuff is here, the universe can't be static and unchanging. Stuff's got to move. And he found that space-time itself must either expand or contract. That's what he found. He said, this is really strange because there's stuff in the universe. The space-time itself must change. And it must either expand or contract. And that's the cosmological principle, meaning everything must everywhere expand or contract, no matter where you are. And so people said, oh, put down the chalk before you hurt yourself. And that can't be true because, hey, we're not seeing any expansion or contraction. So don't worry about it. I think you got something wrong there. You might want to go back. I mean, you're doing the math. We're doing the observations. We don't see anything. So Einstein went back and said, okay, great. So the universe is not expanding or contracting. Let's just do something. So what Einstein said was, he said, let's pop in a term into his equations. He said, okay, my equations clearly aren't complete, so I'm going to add this term called lambda. The lambda term is a cosmological constant that acts as a repulsive gravitational force. It is simply part of space. It is defined, arises straight out of empty space. It is a property of space-time itself. And it does things, it counters the effects of gravity, and it can even halt the motion of space-time and make it static. It can even do that. So at the time, there was no reason to introduce it other than the fact that the universe must be static. Because he said, well, we don't see any motion, and at the time, people knew the Earth was a few billion years old, so if the universe is a few billion years old and those stars are there and the universe should be expanding and contracting and it's not, then the universe better be static. So here's a cosmological constant that does the job. Einstein was happy. He said, got it, plugged it back in the equation, and then the cosmic expansion started to be getting discovered. Meanwhile, over in Arizona, Vesto Slipher at Lowell Observatory was measuring radial velocities of the bright nebulae, and this is about the same time Einstein was doing all this work. And he found that we discussed this before, we found that 21 of the 25 spirals had a systematic redshift. That meant that they had some apparent motion away from us. He could not calibrate the distance. He was like, wow, this is really weird, though. There's this really big motion. They seem to have large radial velocities, and when they do that, they redshift strongly. Oh, that's really weird. I don't know how far away they are, but they're far. This is kind of scary. And then Einstein thought he made a big old mistake, and this was when people really started getting very, very, very active. And so Einstein introduced this ad hoc cosmological constant to try to actually deal with the nature of the static universe. However, in 1920s, everything started falling down around really quickly. Theoretically, there was huge amounts of work that went into this because Einstein's theory of relativity was ripe for the picking. And Willem de Sitter, in the upper right, found that Einstein, you made a little error here and said your cosmological constant made it static, but it's unstable. Sure, it's static, but it's a static just in the same way, perfectly balancing a pencil point on its tip. So any tiniest nudge, even a breath of wind will all of a sudden will make it tumble, and in fact that it will exponentially change now. So you might have a static universe, but it ain't gonna last long. Just like they say, so nice. Here's your static universe. Hope you can keep it. So basically is the idea. That was what De Sitter found. He's on the upper right. And then Friedman and Lemaitre, Alexander Friedman and Georges Lemaitre, who are the two on the right, lower right, showed that without a cosmological constant, if you get rid of that the general relativity seems to predict that the universe is actually expanding. And then Edwin Hubble in 1929, as we discovered, associated Vesto-Slipher's redshifts and others that he took with combining that with Henrietta Leavitt's work on Cepheid variables, and then being calibrated by Hertzsprung and others, and found that nearby galaxies not only had redshift, but that redshift had an order, and that ordering was the closer the galaxy was, the slower it was moving away from us. And the farther the galaxy was, the faster it was moving away from us. And there was the evidence that said the universe was expanding, and Einstein in the lower left said, say what? And said, this is going to be a problem. Okay, and he's called it my greatest blunder ever, as introducing that cosmological constant. Because gosh, we can't have a static universe. We can't have an unstable static universe. We have an expanding universe. So it's my original equations all along. Thanks, guys. I wish I'd known this 10 years before. I wouldn't have added it in. Thanks. Anyway, however, Einstein made, in order to do this, he had to actually assume homogeneity and isotropy in order to put the cosmological constant, in order to use general relativity to have any discussion about the nature of the cosmos. So he guessed that it was homogeneous and isotropic, and it was big. And modern observations do bear that out, as we discussed previously. Those galaxy surveys such as APM show that the distribution is basically the same everywhere on scales larger than about 100 megaparsecs. So there's the homogeneity. And maps of the cosmic background radiation. That's even more important because that's really old light that's traveled through, so it could get affected by anything on its trip to us. That cosmic background radiation, as well as pencil beam surveys, show that it looks the same in all directions, and that bears out the isotropic concept. So Einstein's guess was really right. He just added a cosmological constant in. All right. Now, funny thing is that good ideas don't really die, they just keep going. And the cosmological constant has reappeared recently in the last 20 or 30 years. Actually, it never really went away, but it reappeared as a result of observational needs. And so we see Einstein's equations of the field equations of relativity that show the curvature of spacetime, which is the Ricci tensor on the left with the letter R. The G is the metric by which we measure the spacetime, and the T indicates the tensor, or the stuff that's in the spacetime, and G is Newton's gravitational constant, and C is the speed of light. So the T is the tensor, is the field tensor that actually shows what the content of the universe is, and R is the curvature tensor, which shows how the universe is curved. So, this is really fascinating. I know the relationship between what's in the universe and what its shape is given by this equation, which masks and is a summary, essentially, of many, many equations, at least 16 equations that summarize the nature of it. And the addition of the cosmological constant with lambda was important, because now we see it as a vacuum energy of space. And we consider this thing to be like the ground state of space. So we think of atoms like the hydrogen atom. The ground state of the hydrogen atom, the electron isn't in the proton. It orbits the proton in its lowest possible energy state. And that lowest possible energy state is given by the wavelength, the de Broglie wavelength of the electron. And that demands that the electron have a certain distance away from the proton. Now, there's still a potential between the two of them, meaning there's still an attractive potential, But the electron can't get any closer when it's bound as an atom. It cannot do so when it's bound as an atom. In just the same, in a similar, an analogic, not just the same, but in an analogous way, the universe has a minimum energy state with which it cannot get rid of. Just in the same way the electron can't get rid of that extra energy that it has by being this distance from the proton. Oh, it wants to be next to that proton, but it can't get any closer because it can't get any smaller. So I can't get smaller, so I can't get closer. They're trying to get together, but they can't. So the vacuum energy of space is essentially, I want to get to no energy. I'm trying to get to no energy, but I can't get rid of this energy. I never can. And so it's basically the lowest possible energy state of the universe. And as such, it actually adds pressure that pushes the universe apart, meaning that every particle piece of space has this energy density. It doesn't. So if you expand space, you don't dilute this. You simply make more of this because it is a property of space. So if space expands, there's more of this compared to everything else. And therefore, what's weird is that there's a lot of significant observational evidence that this stuff actually exists, which we'll talk about soon. In summary, we can remember that the concept of isotropy and homogeneity are well established. They say that we see, no matter which way we look in the cosmos, we see the same things. And if we were to travel to a distant galaxy 100 million light years away, they too would see the Hubble relationship with galaxies rushing away from us faster and faster the farther and farther they are. And they too would see similar, not exactly the same, of course, because it's a different place, but they would see the similar kinds of things when they bend things on larger size scales. And it doesn't matter how far you went. If you went 5 billion light years away from here and just used Doctor Who's TARDIS and jumped over there, you would not see anything significantly different, which is really fascinating. Now, which also implies that there are some galaxies that are rushing away so fast from us that some of them are currently rushing away from us faster than the speed of light because the expansion of space between us is great enough that that thing is pushing it away. So even if we went to there, we would see the same thing. We wouldn't see everything rushing away around us at the speed of light. No, we would see, if we were 50 billion light years away, 50 billion light years away, we would see the same exact behavior no matter what. And that's what we mean by isotropy and homogeneity. And it also means the laws of physics are the same everywhere. And we will now use that in order to justify the 4 pillars of the Big Bang. We'll see you next time. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today, this time, we are really going to bend your brain around because it's time to really get what we mean by the Big Bang. The Big Bang is actually a description of how the universe expands. So we have all sorts of observational evidence concerning the expansion of the universe, from Hubble's observation of expanding galaxies to galactic evolution that we've seen with clusters of galaxies, as well as the evolution during the collisions. We've also seen that galaxies themselves colliding with each other and moving through time. So things do change with time. So it seems also kind of natural that space itself might change with time. That might not seem really natural on the surface, but it's an unavoidable consequence of general relativity and an unavoidable consequence of the solutions to exactly what Edwin Hubble found with the expansion of the universe, and has been subsequently seen by many, many, many astronomers ever since. In fact, there's been nobody who hasn't seen it when they go and look. So the Big Bang is based off the concept of the expanding cosmos. So now we're going to get into the nuts and bolts of exactly how Lemaitre and Friedmann and Hubble and Einstein actually got to the place where they said, well, it's got to be expanding. So here we go. I'm going to respect your brain by giving you the reality behind it. All right. The expansion of the universe was observed to be expanding today, and so we use that as Hubble's law. An interesting element of it, as the universe expands, it cools. So if you went back in the past, it must be smaller, hotter, and denser than it is today. Now, what do we mean by cooling? Well, if you take any kind of a box of gas, say like a car tire or something like that, or a bicycle tire. You want to have some fun, drive your car to the gas station, and then just let it sit for a bit, go get a Coke, come back in, and then let all the air out of one of your tires. Just because. I mean, why not? You can put it back in for just a few seconds, for a few minutes. So what you do is you're gonna deflate your entire car tire, and then you go grab your coffee, come back out, and then touch the car tire. Now it should be about room temperature or air temperature. Won't be very warm, and do this on not a hot day or anything like that. And you want to make sure you haven't been driving, so the car isn't hot. And then you quickly inflate the tire. Now the tire will be hot because you've taken air and compressed it inside the tire. And when you compress a gas, it heats up. If you compress the universe, the gas of galaxies will get closer together and therefore bump into each other in reverse, in time reverse. And so therefore must have been closer together and therefore must be hotter. All right, so ago it was smaller, denser, and hotter than today. If we run the clock backwards far enough, the universe should be very small and extraordinary high density, and it also should be very hot and opaque. And what we call this initial very hot, opaque, dense state is the Big Bang. It also can be called a primeval fireball. There's a lot of other names for it. But the Big Bang was coined by, I believe, Fred Hoyle on a British television show, on a British radio show, when he thought that it was a terrible idea. And he said, well, the universe began in some kind of crazy Big Bang, and it stuck. So we're stuck with the Big Bang. It's kind of a good name. The foundations of the Big Bang are very deep, and they begin in the 1920s and they continue today. It's the concept is that you have a nearly infinitely or infinitely dense hot universe. Infinite is such a horrible word. Just arbitrarily highly dense and hot universe in the past. And then you get three basic things that assume that. One, we talked last time about homogeneity and isotropy and the relevance of general relativity as an explanation for gravity, as well as its description of the nature of spacetime itself. The universe is homogeneous and isotropic on large scales, which means general relativity is valid everywhere. And the energy of the vacuum, meaning the cosmological constant, is tiny or small. And that's why it doesn't seem to have much of an effect. Every one of these assumptions is testable, and that makes it valid science, because you can't have science if you can't test it. And so that's really what we need to know about. Can we actually test it? And the answer is yes, we can test it. So let's see what those tests are. But we're going to go through a very detailed consequence of what we mean by the Big Bang. The Big Bang is a testable model. So the really important thing about the nature of science is that there's empirical data which you take, and then you explain the universe with physical laws, and you don't try to create new physics unless you run out of ideas. And then you try to describe it with how you see it to behave, and hopefully you'll find some underlying physical idea that it fits into. Otherwise, you might just find some new interesting phenomenon that is a result of the underlying physics, which is cool too. So we have then, the most important thing is that you create a testable model. That testable model then has predictions for what you have for the empirical data. If the data does not fit the model, then the model's bad. If the model is bad, you don't use it anymore. Here's a bad model for the universe. The bad model for the universe is it is a big box supported by turtles. And so you look for the bottom of the box, and you look to find, dig a hole in the bottom of the box. Do you see some turtles? Oh, you don't see any turtles. Well, darn it, that's not a good model for the universe. The question then becomes, does the Big Bang model explain the properties of the observed universe? And that's what we're going to find out. What is this model? As the universe expands, space gets stretched in all directions from all points. Sometimes people just say it gets stretched in all directions, but it's important because it's isotropic as well as homogeneous, that space is getting stretched in every direction as seen from all points in space. That's critical. Matter is carried along with this expanding space, and the distances between galaxies are getting larger, physically larger with time. So the Big Bang predicts Hubble's law, and we're going to see how that happened. It predicts it exactly for recession speeds that are small compared to the speed of light. Hubble's law, remember, is a relationship between the speed of recession and the distance, and that's if it's close by. The farther away you get, Hubble's law doesn't work anymore because it's no longer a linear relationship. And that's what we're going to find out soon. The more descriptive, in order to look at large cosmological distances, we need a major description of what we mean by the geometry of space-time. That really makes people angry. It's like, how can space have geometry? Well, take a topology class or take a geometry class and you'll find out the nature of that stuff. So space-time itself has a geometry. Let's see what it looks like. The cosmological redshift is really important. It says that space stretches light waves, and the wavelengths get stretched longer and longer, and therefore they become redder and redder because light itself has a length associated with it inside itself. So as the universe stretches, that gets stretched with time. The redshift of an object gets larger with increasing distance. That is a critical observation. The Big Bang naturally explains this cosmological redshift and distinguishes it from normal Doppler shifts due to motion. So the Big Bang says, hey, I'm going to stretch that space-time. You can wiggle around all you want on top of space-time and fall in terms of gravity towards each other, but I'm going to drag you along as best I can, and that's the Big Bang. So when we think about cosmic look-back time, we say how far back in time we can see. When we look at the sun, we see the sun 8.5 minutes ago because that's how long it takes light to get here from there, and that's the astronomical unit. But we're looking much further back in time when we look in cosmological distances. Cosmological distances means we're looking up back millions or billions of years in the past. So as we get the light, we're actually seeing things as they were billions of years ago. So this is actually good. We're not seeing them as they are, we're seeing them as they were. So if we have a model of how things should look and how things should be behaving ago, then we can model it in the past. So we actually can see the past. We just have to look at fainter and fainter and fainter objects and trust that redshift is actually telling us that we're looking farther and farther and farther back in time. That's what we can do. So this allows us to paint a history of the cosmos by looking farther and farther in the past. So the deeper into space we look, the fainter the objects we see, the higher the redshift, the farther back in time we see, and then we can actually see what the universe was like long ago. The shape of the universe is also important because everything attracts each other due to gravity. So gravity as formulated by Newton is purely attractive. But Einstein's theory of relativity allows for gravity, which is a description of spacetime instead, as I described in previous lectures, as a description of spacetime. It allows for spacetime to actually do things differently and you are allowed to create things inside the equations that would have a repulsive effect, but you have to have the stuff to do it. And that's kind of a weird thought. But Newtonian gravity is modeled and is a subset, a very large subset of general relativity, but it is a limiting factor of the equations of relativity. Now, we also know that relativity says that energy is equivalent to mass. So no matter what you have in the universe, matter and energy are the same thing. So anything that has energy density, whether it's mass in a box or light or anything else that you can possibly imagine that has energy density, it will affect spacetime because all of that stuff goes into what tells spacetime how to curve. And all of this stuff put together determines the global geometry. Now then, it's time to respect you and your brain, because now I'm going to show you exactly what all these words mean. This is like 3 sentences, but hey, let's just see what this means. Time to respect your brain. All right, let's go back. Let's take it back, a ways back. So how does Redshift measure the expansion? Let's make sure we're on the same page here. The definition of Redshift says, let's make a little triangle, assume little galaxies are at each of the points of the triangle, and then the scale factor, let's call it, is what we're going to do. So ago, the scale factor was, say, 1, and then that's then, and now we're going to expand the triangle, and as we expand the triangle, we've doubled the size of the triangle, and as we've doubled the size of the triangle, now the scale factor now is 2, since we've doubled the triangle. And so if we look closely at it, we say that that all of the points have separated from the center or from each other. Every length has doubled. It hasn't expanded from a place. Remember, each one of these things has expanded away from each other because the distance of each side has gotten bigger by a factor of 2. This is what we define to be the redshift. The redshift, as we saw before, is a direct relationship between this scale factor growth. All right, so we can then associate the stretching of space-time because light has a wavelength, and so we can now stretch the wavelength of light by stretching space. And I snuck in that equation that shows how redshift is related to the wavelength of light, and now I'm going to sneak it around even more by saying, oh, how did we get that? The side of each triangle grows. That's the R sub 1, 2, and 2, 3, and 3, 1. Those are the points 1, 2, 3 on the corners. And the scale factor grows as a function, and that parenthesis t means as a function of time. So this distance between point 1 and 2, or 2 and 3, and 3 and 1 grows as a function of time, and that function of time is the scale factor. A is a function of time, and R 1, 2, or 2, 3, or 3, 1 as a function of t0, well, it's not really a function of t0. It's as measured initially. So the blue triangle or the purple triangle. And so R1, 2 at a later time, t, is the green triangle, the aquamarine triangle that's bigger. And so we've just jumped a sub t from 1 to 2. Now we've jumped it, but how does it go with time? That's a real question. How does the thing behave with respect to time? Does it grow linearly? Does it grow quadratically? Does it grow exponentially? Does it go up and down and up and down? Is it like a sinusoidal function? Does it go to the cube power? What the heck does it do? How does A have a function of time? We haven't answered that question. We don't know yet. Let's find out, because that's the observational thing. So then we say, fine. We then say how fast it's growing with time, and that's the rate of change. That, say, one of the sides, we're isolating one because it's 3 equations. I don't want to write it all out. The R sub 1, 2 is the distance between points 1 and 2 on the triangle, and dr1, 2 is a little change in the distance as a function of time compared to the little change in time. So dr1, 2 says, make it a little bit, and then dt says in a little bit of time. And that is the rate of change, or what we call the derivative, and that we can hyphenate and call our a dot, which is how does the scale factor change with time. And the dot is just a really shorthand way of saying dA sub t dt. That's what I mean by the dot. And so now we have, if you look closely at it, we can then say that R sub 1, 2 is actually the velocity, or the speed, V sub 1, 2, the speed with which the triangle side is expanding, is proportional to the distance, and the length of the triangle, times the scale factor as it changes with time compared to the initial size. So what is that A dot of A? That A dot of A is actually just the Hubble parameter. So the speed with which the thing is expanding is equal to the Hubble parameter. So A dot over A is defined to be the Hubble parameter. That's what Hubble measured, because now we're looking at the rate of change of two things. So now we've related the scale factor's rate change to the Hubble parameter, and the speed is the redshift. So we got redshift, the redshift is the speed, and that is related to the stretching of the wavelength, which is related to the scale factor, which is related to the Hubble parameter, and all these things are related. So basically, if you measure the redshift, you're measuring the Hubble parameter. All right, so that's what we need to know. All these linked equations just simply tell us that the redshift is a measurement, knowing the measurement of the redshift and knowing the distance gives you the Hubble parameter, which is how the scale factor changes with time. And exactly how the scale factor changes with time is extraordinarily complex, but I'm going to break it down for you. And that's what we're going to do right now. We need to say how gravity figures into all this stuff. So gravity says force is a mass times an acceleration. Great. So we've got a mass times an r double dot. See, I'm getting rid of those dtts, so I'm saying how fast does the distance change as a function of time. So r double dot is the acceleration. That is the rate of change of the rate of change of the scale of the size. So now the force due to gravity might be say, hey, we got two things. They're separated by a distance r. One of them's got one little mass, and one of them's got one big mass. And so that's equal to the rate of change, the acceleration of the little thing. And that says, oh, how fast is that rate, that distance accelerating? How fast is that thing changing how fast is the rate of change rate changing? That's what r dot means. So then we can say, what's the mass of everything? We can break it all together. The mass of all the things that are pulling on the little guy is equal to we're assuming a spherical distribution. So we have a little bitty dot on the surface of a big, 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 big sphere. And we're seeing how that big, 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 big sphere changes with time. And that's where the 4/3 pi ar cubed goes. And we then multiply it by the density of the stuff. So the mass of the entire thing inside the sphere on which the little guy is riding as the sphere is either expanding or contracting. So now we got an expanding sphere and we have a little bitty guy on the surface, like an ant riding on a big ball. And that's what little m is. Little m is the ant riding on the big ball, and m could be m sub all is like the big ball underneath the ant. So the density, how fast the object is growing, is the scale factor. And that's the radius. So the big R is simply the scale factor times some initial value of the radius of the ball, which is little r. So we've got our scale factor again, and now we're going to make the big ball expand. And if we combine the mass and the density and the force due to gravity and the scale factor together, we get a series of equations. So there's two possibilities that we're going to find out, that the universe could either expand forever or it can contract. So we look at this ball as its scale factor, and it's gravitating on itself because now we've got a ball that's expanding, and either the gravity wins and the ball starts to collapse back down on itself, or the ball expands forever because there's not enough mass to pull it back. That's what we care about. The ball itself is the universe. We're making a toy universe, and the little m is the little ant on the surface of the universe. So all of the mass that's underneath the little ant is pulling on the ant, as though we're just is at the center. And the rate of change, the big R double dot, is the acceleration or deceleration of the rate of the radius of the ball on which the ant is standing. So universe ball, ant on surface. How fast is ball expanding? And is it expanding? Is it accelerating, decelerating, or staying constant? So there's really only two ways it can go. It can either expand forever, or it can collapse eventually. Or there's some really limiting value between them, where it just barely expands forever, but if it got a little bit less, then it would collapse. So it would collapse if there's a lot of mass, right? Pulling it back together. If it's not a lot of mass sub all is small, and so therefore the density is small. Therefore, the rate of it doesn't overcome the expansion. So we can think of it as expanding from a point. All right. So here's our three possibilities. Either in the past it was small, expanded to today, and sometime in the distant future, either it'll pull back on itself and collapse down to nothing, or it won't. And those are our only two possibilities, because the force due to gravity on the entire universe will either pull it back or it won't. That's the thing about an expanding universe. Either it'll stop or it won't. All right, there we go. So let's respect you even further, and we're going to integrate those two equations that we saw in the previous thing, where we linked the density and mass and the force due to gravity. We pile them together, and we get the equation above the green line. So we're taking a really basic concept that the force due to gravity is pulling on a spherical distribution with a density rho, and that rho is that little p. And we also see g, which is Newton's gravitational constant, 4 pi over 3 is because of spherical distribution. So we have r double dot and r, which are the scale factor sizes of the cosmos. That's just some scale size of the universe, or the radius of the universe, which is an interesting way of talking about it. And if we play around with that and add in the Hubble parameter, we get the two equations below. Now I'm not going to go through the whole derivation of that. That's an enormous derivation. I'm going to wave my hands here and allow you to go play and look with that. But the important thing is that we can actually, we're saying the scale factor, right? So the scale factor shows is all about the density, the scale factor is all about A, and A goes into the definition of the Hubble parameter, which is the H thing. So somewhere in there, we should be able to say how the density parameter is changing as a function of time. And if we play around with it, we find that we have two equations. And the two equations we have are actually identical, and I'm going to show you where the second one comes from in a bit. But the first one is the middle equation that I'm showing you, which says the Hubble parameter as a function of time squared is equal to 8 pi now times the gravitational constant divided by 3 times c squared, which is the speed of light, times the energy density of the entire universe as a function of time. That's what that epsilon means. And then the second term we're subtracting from is some kappa, is called kappa c squared over r naught squared, a as a function of time squared. Kappa is the curvature constant, and it's only three numbers. Either it's 1, -1, or 0. C again is the speed of light squared. R naught, r sub 0 squared, is the curvature of the universe measured to, or the radius, the scale size radius of the universe today, and A as a function of time is the scale factor of the universe as a function of time. So the Hubble parameter as a function of time depends on epsilon as a function of time, which is the energy density as the universe goes. It also depends on the scale factor, how the scale factor itself goes as a function of time. All the other things are constants. G is Newton's gravitational constant, C is the speed of light, and R is the characteristic size scale of the universe today, R sub naught. The second equation reframes the one above it. The third equation on this thing reframes the one above it, but in terms of the density of the universe. Okay, so that's what that omega is, and that's what you'll see in the literature, and that's what textbooks show, and all sorts of silly things like that. So that's what omega is about. So let's see why we use an omega. So first, let's look at that equation more carefully and see where we get that from. Let's pretend for a second in the equation above that we set kappa, the curvature constant, equal to 0. Let's also set the Hubble parameter equal to today's value in the entire universe. Not yesterday's value, but the value we measure today locally in the universe. So then you get the epsilon today. And epsilon today is today with no curvature, is a really important number. And that's equal to h naught squared over g. And that is H naught is the thing that Hubble measured, which we know roughly today is about 70 kilometers per megaparsec, 70 kilometers per second per megaparsec, and G is Newton's gravitational constant. But let's now define omega as a function of time, which is the density parameter. The density parameter as a function of time is equal to the epsilon sub t, which is the energy density of the universe as a function of time, compared to this new made-up number, which is the energy density today if there were no curvature. That's what the omega stands for. So we're going to reframe it, and that's kind of important because that'll tell it, because if you reference things to today, you get some good stuff. And if we reference it to no curvature, it actually tells us some important things about the rest of the equations. So that's the definition of omega, the capital omega as a function of time. It's the energy density as a function of time, epsilon of t, compared to the energy density today if there were no curvature. So that's E of today in the one above it. That's where we get these two equations. They're equivalent equations, and really they're the same thing, just parameterized with that omega instead. The density parameter is actually the cosmic dictator because it tells everything, and depending on the curvature, it tells everything, and it also even dictates a lot of stuff. So let's pretend that the curvature is now +1. The curvature can only be +1, -1, and 0 in this formulation of these equations. If it is +1, we have a positively curved universe. And the density parameter, therefore, is always positive. Because if you look at that and say, oh, if kappa is positive, everything else is a square, so those things are all positive. And then we move it to the other side of the equation and move omega to the other side, that number must always be positive. So we call that, the density parameter is always positive, and if it so happens that the omega is greater than 1, the expansion will eventually turn around and collapse. And we call that a closed universe. All right, cool. Next, make the curvature -1. If it's -1, we call that a negatively curved universe. And if the density parameter, after you munge it around, is less than 1, then the universe will expand forever, and we'll call that an open universe. So make kappa -1. The thing on the right-hand side of the equation, in the lower equation, is positive. Put the omega on the right-hand side and then shift it over to the left. And we find that maybe the other thing can then be the kappa is now -1, so it actually is ignored. So if the density parameter is less than 1, that thing could in theory be greater than 1, but pretend it's less than 1, the universe then will expand forever, and it's what we call an open universe. Finally, we look at the limiting case where we make the curvature 0 and we set the time today, and that gives us the special parameter for epsilon, the density parameter, which we call the critical density, and that is really important. So let's take a look at that for just a second. And we rename epsilon to rho, and we call 3h0 squared. So we're going back to that definition, right? And then we say that it's equivalent. We actually plug in the numbers for 3h0 over 8 pi g, and we get a value that's a really tiny amount in kilograms per cubic meter. But if you make it solar masses per cubic megaparsec, it's kind of big. That's about the same size as 1 Milky Way's worth of mass in a megaparsec. That's kind of what we see. That's interesting. So this critical density parameter, which is a mass density, which is an energy density, is actually equivalent to kind of what we see is in every cubic megaparsec 1 Milky Way galaxy. That's what 1.27 times 10 to the 11th solar masses per cubic megaparsec means. That's a lot. That's 100 billion solar masses, 127 billion solar masses in a cubic megaparsec, which is about the mass of the Milky Way. So we can then define a new thing called omega sub naught. And omega sub naught says, take the average density of the universe that we see today, whatever that is, and compare it to this critical density, whatever that which we just are showing above. And that's the value of the average density now and the critical density now, which is the number above, rho c comma naught. That's a very important number to measure, is the average density compared to the critical density today. Today. Not 2 billion years in the past, but today. So the cosmic density parameter really dictates a lot of things. If it's a high density universe, If the average density is greater than the critical density, then it shall be positively curved and it shall collapse. If omega sub naught is measured to the average density is less than the critical density, it will be a negatively curved universe and it will be open and it will expand forever. The funny thing is, what if it's a critical density universe and the universe is flat, meaning omega sub naught equals 1? We express that in terms of density parameter, and that is a spatially flat universe. So let's look at these things in detail. So a major quest in all of cosmology is to determine the cosmic density compared to the critical density. That's what omega sub naught is. And if we have omega sub naught greater than 1, that's a positive curvature, and it's like being on the surface of a sphere. If that's the case, then parallel rays eventually converge, and then the geometry of spacetime would be spherical. That's an interesting spacetime. But it has measurable consequences. The spacetime would be positively curved, and so then light rays would eventually collide if that is the case. Next, if it's negative, if the geometry, if the density parameter is less than 1, it's negatively curved. And it's an infinite hyperbolic universe. The hyperbolic curvature is every point in the universe has that shape. Not just one place, but every point in the universe has that shape. So you really can't represent it very easily. The fun part about this is that every light ray diverges from every other light ray. They don't stay on the straight lines diverge and get farther and farther and farther apart exponentially in this kind of universe. And so they diverge rather than get closer or stay parallel. Well, in parallel what we think. However, in a critical density universe, we find that parallel light rays do stay parallel. They stay in what we would say is our normal sort of 10th grade geometry sort of thing where they stay parallel. Universe expands forever, but just barely. All right. Fun thing about a closed universe, if it exists, shine a flashlight, look around behind you, you see the flashlight hit you from behind. Kind of neat. But unfortunately, and this was kind of the thought of things, that the universe was thought to be closed in the 1990s. And that was an interesting thought. And the radius of curvature was thought to be extraordinarily large, but the idea was that we thought that the universe must be closed because of there were various pieces of logic and reasoning and observational thoughts, as well as kind of let's not make the universe infinite in extent, let's make it kind of a thing, because that would be weird, because what does infinity mean? We don't really know. So let's hope it's closed. Unfortunately, it's not. All right, so how do we know what the density of the universe is? That's the question on the table. And ignore the equation at the bottom. Just look at the one in the middle. Ignore the one at the bottom. We'll get to it shortly. But the critical density parameter is just a sum of all the stuff in the universe in a typical box around us. So we have all sorts of parameters that go into it. Okay, so what are these parameters? And we have omega sub c, omega sub b, omega sub rad, omega sub k, and omega sub lambda. Omega sub c is cold dark matter, and that's kind of or cold dark matter that might be dark matter. And B is cold baryonic matter or normal matter like atoms and molecules. Rad is radiation like neutrinos and light. K is curvature, meaning the curvature density, the density of the curvature of the universe itself provides energy density, and energy density due to a cosmological constant lambda. So dark matter, C, normal matter, B, radiation like light and neutrinos, rad. K is curvature, meaning the universe itself provides space-time curvature, and that might have energy density, and lambda. So here's what we really think it is. We think there's not much due to radiation. We can tell that the energy density due to radiation is not very big. And we also think that the curvature contribution is almost nothing. So if we take the cold dark matter and baryonic matter and we call them just little m for like matter, we combine those two into one, and we retain the lambda, we really actually think that the current critical density is 1. We think it's flat. or really close to flat. So let's start with that as an idea, and we're going to actually show in future lectures how we know that that's actually true, or at least how we think it really is very close to 1. If not 1, it's really close to 1. And that has real problems for everything else later. All right, so let's see what we mean. If we take the Hubble parameter and digest it and push it through and see how all of the things actually affect the Hubble parameter, we say, well, how does each density parameter affect the Hubble relationship? So Hubble factor as a function of the scale factor, instead now of time, but of the scale factor A, this is how all of these pieces deal with it. The universe is about 13.8. I should make the 13.799. That's the Planck thing, but heck, there's a lot of ways to measure it, but 799 is the most, 13799 is the Planck measurement from 2015. Anyway, let's keep going. So these various parameters inside the big sum each have a meaning, and they all are part of the great cosmic recipe of what makes up the universe and how they affect the rate of expansion of the cosmos. Let's look at each one in turn. So this is the Hubble constant, or if it were set to today, we would just call it h sub naught. But now we're going to say let the Hubble constant vary as a function of time, or really now a function of the scale factor, how big the universe is. All right, so then that's defined in terms of the a dot, which is how the scale factor goes as a function of time compared to the scale factor. Each of these are, of course, squared. Dun, dun, dun. And now we have the next bit, which will be the Hubble parameter. And the Hubble parameter then says, there's the Hubble constant. We extract it out of that. So how does each of these things vary with time? So we're just going to take the Hubble constant out of there and put it through time. So how does each of these things go? So that's the Hubble constant. That's today's measurement. So we can measure that. We don't need to measure other stuff too. Great. This is the density of cold dark matter. Dark matter, stuff you can't see, doesn't do light at all, but really does everything else. So cold dark matter, and B is baryonic or normal matter like atoms and molecules. And how that stuff changes with time, how its energy density or its density changes with time, varies as the scale factor cubed. You put stuff in a box, make the box bigger, and just spread it out, the stuff is more spread out. The bigger the box, the more spread out it is. So the density varies as the scale factor cubed. That's why it is a cubed at the bottom, because it's normal matter. You take its density and you stretch the box it's in, you drop its density by the cube of however much you've expanded your box. Next, we have how radiation goes, like light. Remember, light gets expanded with the box, but it also gets stretched. And as it gets stretched, the light gets stretched. But we also know that the energy of a photon is proportional to its wavelength. So therefore, we have to add in, and this is energy density. So we have to say, its energy density also drops with an additional scale factor to the 4th power because the energy drops as it gets stretched. If the energy of light did not change when the wavelength got stretched, then we wouldn't have a 4, we'd have a 3, and it would be dumped into the previous one. But that's not the case. Radiation drops off as the scale factor to the 4th power because its energy drops as its wavelength gets stretched. Third, the curvature of space-time itself has energy, and it would also contribute to the overall rate of expansion, but it does so as the scale factor squared, like a surface density. So we can think of the curvature of space-time as the surface density of space-time, which is kind of weird. It's kind of like a surface tension or something like that. That's kind of a good way of thinking about it, but it drops off like a surface area. Okay. Finally, we have this component that we will call dark energy instead of lambda, because that's what we're calling it nowadays. Dark energy, cosmological constant. We really don't know what it is, but we're going to say, yes, it's going to drop off as the cubed, but then we're going to tack on a very strange thing. We're going to multiply that 3 by 1 plus w. Why? Because fish. No, because it actually allows us to set W to something, and when we set W to something, we can then change the value of how it goes. So depending on the type of thing that dark energy is, we can set it to something. All right. We think that it is a cosmological constant. So if it's a cosmological constant, we can set W to -1. If we set W to -1, 3 times 0 is 0. A to the 0 power is 1. So we get a constant. So there are good reasons to think that it's close, that W is close to -1. In fact, that is something that is actually measured as a parameter from the cosmic microwave background, which we'll get to in a future lecture, so it becomes a cosmological constant. This is what we call a tension in spacetime. It is a tension that pulls spacetime apart. Notice how this works. If every other one of the things were gone, it would just say, hey, the Hubble's constant, you're gonna grow. You're gonna grow according to me. If I'm positive, I'm gonna push you apart larger. If I'm negative, I'm gonna push you apart. I'm gonna make you go smaller. So it's a tension pulling space-time apart if the cosmological constant is a positive number. All right, so if you go in a textbook and say, how does everything evolve with time? We have radiation dominated, matter dominated, dark energy dominated. How does this equation work with time? And you see graphs like this in textbooks and online. So let's see what these kind of graphs really mean. And they come from that equation. So in the very, 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 very early universe, when everything was small and packed together, all of the terms of the equation were small except for the radiation version. Because if you take A and make it really tiny, then the reciprocal of it becomes really large compared to the others. So the only thing that matters as A becomes smaller and smaller and smaller, approaching 0, because we think of the scale factor as 0 at the beginning, or close to 0 at the beginning, and 1 today, and getting larger than 1 in the future. So let's let A get really, 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 really small compared to 1. So therefore, omega radiation term grows to be much larger than all the other terms. And that's what we mean by radiation density dominated, or radiation dominated. The energy density due to radiation is much greater than all other contributions combined. So you can just look at the universe growing or shrinking, or growing it as the scale factor of the 4th power, and that's how the universe was growing during that time, and that's approximately for the first 10 to the 5th years, or the first 100,000 years, couple 100,000 years of the Big Bang. The universe was radiation dominated. And so it grew according to the scale factor of the 4th power. Then, at about 50,000, or roughly about 50,000 to 200,000 years after the Big Bang, roughly 50,000 years, the radiation density dropped below the energy density due to matter. Matter grows less, drops off less quickly with time, so therefore it will dominate the energy density. Radiation density just drops really fast as time goes on because of that extra power of A. So then for a long time, from 50,000 years after the Big Bang, I said 200,000 a while ago, I mean 50. So 50,000 years after the Big Bang, up to about 5 billion years after the Big Bang, the universe was dominated, the density was dominated by matter, both dark matter and normal matter. And the universe expanded according to the density parameter of dark and normal matter. Now, about 5 billion years ago, the matter density dropped below that of the dark energy density, and the radiation density is already really, 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 really tiny compared to all that stuff. So right now, the universe is roughly is dominated by 2 terms, by normal matter and dark energy. However, in the future, the matter energy density will drop below that of dark energy, and you will find that in the far future it will be dominated completely by dark energy, and that's what will happen in the future. So this one equation at the top shows how this graph comes about, how the universe expands with time. It depends on what's in the universe, whether it's dark matter, normal matter, radiation, curvature, or dark energy, and that determines how the Hubble parameter expands with time, and that is the expansion of the universe in an equation. So that's what we mean by it. That's what we mean by the expansion of the universe. It's governed by the Hubble parameter, which shows the scale factor, which then is related to what's in it. What is the energy density in it? And the energy density tells the Hubble parameter what to do. So the universe is expanding now. Therefore, in the past, the universe was smaller. All galaxies were closer together in space, and if you go back far enough in time, all galaxies and matter that are in our local observable universe were all in one place. And how far back we can go is what we call the age of the universe. And so Hubble time is the age of the universe. And if we take the reciprocal of the Hubble constant today, we find that that is an estimate of how long the universe has been expanding. So the current level of the universe is roughly 70 kilometers per second per megaparsec, and if we convert that into just a time by taking its reciprocal and multiplying all these numbers together in a little calculator, I invite you to do that, you get about 14 billion years. So that's a good rough age of the universe, is about 14 billion years. And due to the cosmic expansion, the rate of expansion has changed with time, as we've seen by that graph and as we've seen by this equation. We've seen that all of those parameters are important, more important. Sometimes they're more important than others, and so we can eliminate them and ignore them, and that's what we do in physics. We say this equation is true across the board, but what's the dominant term? When is it dominant? We don't really, the crossover points are when it gets kind of mungy and we have two terms, or maybe three terms, or what have you, but really, when it's dominant, there are this term dominates, that term dominates, etc., etc. So if the expansion were faster in the past, then it would be slowed down by gravity, leading to an overestimation. So it's not constant. If the expansion were faster, then the universe has slowed down, and that made us think that the universe is older. If the expansion were slower, then the expansion would have accelerated by something. Then there maybe is something that is pushing on it, leading to an underestimation of the age of the universe. Maybe that's the case. So the total age of the universe is dependent not just on the reciprocal of the Hubble time, which is just an estimate, but how long it's been doing that thing according to this equation. And our big mystery is how much energy density is there in the cosmological constant? How much is there in matter, in normal matter? What is the total sum of all those things? So in order to understand that, we need to know the total sum. We need to now measure two hard to measure numbers, the Hubble parameter, which gives us today how fast the universe is expanding right now. And we also need to measure the density parameter today, which tells us how the matter and energy of the density affects the expansion rate. We can, and you do, include that cosmological constant in that thing because it seems like it could enhance the expansion rate, and there is observational evidence for it. All of these things combined together tell us how old the universe is. With all of this stuff, using certain numbers, we have what we call the benchmark cosmology. If we set h0 by discovery and by experiment to 67.74 kilometers per second per megaparsec, and that's a measured object by the Planck probe. And if we then measure the density parameter equal to matter plus lambda, meaning the cosmological constant equal to 1, we find that about 31% of the universe's energy density is matter, and about 69% of the universe's energy density is due to a cosmological constant. And the sum of those two things is 1, which is interesting. So the cosmological constant, so the value of that thing has, as from 30% is matter, 70% is from the energy density of cosmological energy. Since they're close to 1, the measured values are close to 1, we add them up. We live in an infinitely large, spatially flat, expanding universe that has no boundary. Wow. And that is consistent with the ages of the oldest rocks and oldest stars and the oldest stars in globular clusters and so on. And we have an estimate for the age of the universe at 13.799 billion years. That's our estimate, plus or minus 21 million years. That's a pretty good estimate, actually, if you think about it. All right, so what we see now, the universe is old, it's cold, it's low density, galaxies and all matter are getting further and further apart as space expands between them. As the universe expands, it cools even further. And in the past, the universe must have been hotter and smaller and denser. Let's see next time if there's any evidence for this early, hot, dense phase of the universe. That's the hot Big Bang. I've given you the description of how things expand with time, over time, but now, where was that starting point? And that's the hot, dense phase we'll get to next time. And we'll see you soon. Hello, this is Jason Kendall, and this time we're going to be talking on my introductory astronomy things about how exactly the cosmic redshift happens, meaning there's this Hubble relationship that shows the relationship between how fast a galaxy is receding away from us and the redshift of the light in the spectrum of the galaxy. So how does this actually happen? I'm going to show you basically the mathematics behind it, as well as what we mean by measurement. And then I'm going to use some underlying assumptions, which we'll have to leave for later. But I'm going to give you the basics of how we get redshift from the universal expansion. First, we have to remember that atoms and molecules, whatever they are, they vibrate. And when they vibrate up and down, let's say this is a proton. We're pretending there's a proton vibrating as opposed to an electron. Usually it's the electrons, but hey, I made this little graphic a long time ago, and so I just haven't had a chance to swap my plus for my minus. You can thank Thomas Jefferson for that and Benjamin Franklin. In any event, so you can see that the plus sign has lines of force radiating away from it. And if that charge is shaken up and down, then the propagation of the arrows to the right shows how fast it takes for the disturbance in that field of one field line to propagate to the right, and only one field line. And as the field line's change is received by the electron on the right-hand side, we see it is shaken up and down due to the force, the electrostatic force between the plus and minus charges. So really what we have is that the actual thing that we call a photon is this wave packet, is this disturbance in the electric field between two moving charged particles. So that thing that we see going up and down, that wave, that is a photon, a disturbance in the electromagnetic field. And usually we think of, because electrons are a lot lighter, that the electron itself is usually the thing that instantiates the field, because it's small. But you know, a proton can do it just as well. Something's going to shake it a lot harder though. So we can easily move an electron. Protons are 1,000 times or 2,000 times heavier, so they're harder to shake. So if you briefly accelerate or shake an electron or a proton, it will create an electromagnetic wave in its field lines, and that we call a photon. So it kind of looks a little like this, where you have the propagating photon that comes along. There's a beginning, there's a middle, and an end to it. And if we then couch that beginning, middle, and end in kind of a bracket, we see that you can think of it as a ripple packet, or a packet of ripples that goes by. And that's what we call a photon. A photon is a wave packet in the electric field of a charged particle that was briefly accelerated or shaken. And it's this wave group that propagates from one direction to the next that we call a photon. Now, when you shake an electron or a proton, it emits photons in all directions. But because of the nature of the shaking, the photons can be polarized or what have you, but as the photons get emitted along these field lines, they propagate out at, of course, the speed of light. and they have a distinct or a semi-distinct wavelength, because which is the actual wavelength inside there? You can see that there's kind of heights and widths, but there's to the thing, but the waves are, they're not like easily discernible waves inside of each packet, but they're there. So what we can do is we can look more closely at the photon, and we say that since it is a wave packet, we can describe the wavelength of the photon as the distance between successive wave crests inside the ripple packet. So we see we look at the highest and the next highest one to the left. Now, if the universe expands and stretches the photon, then the distance between these two wave crests stretches. Now, this is actually an extraordinarily tiny effect. It's really, really, really small. But if we add up all of the effects of the photon from its emission from, say, a distant galaxy to today, very far, and let this occur over an extraordinarily long period of time without changing the photon itself, then or having it impact, get absorbed, get re-emitted, or anything, it just simply travels. And as it travels is affected only by the expansion of the universe, then all of the little tiny stretches that it feels along the way will add up. So let's see what that means. Let's see how it actually does that. And so we're going to have to play math games. And so our math game is first, how do we actually measure distance in cosmic time? And the way we measure distance throughout cosmic time in a homogeneous and isotropic universe that only has uniform expansion is with this metric. And this metric describes a universe that is uniformly either expanding or contracting, has uniform curvature, and is isotropic and homogeneous throughout. But our really important thing throughout this metric, which describes distance, which is the left-hand side of this ds squared, which is a little tiny distance in space-time. And that's equal to a little tiny distance in time, dt squared, times the speed of light squared. And then you have this thing in big brackets, which describes the distance that it travels in one direction or left and right. And we have the dr, which is the distance radial direction. Or radial direction meaning, say, straight from the electron that's vibrating that we saw earlier. Well, let's make this simpler because we really don't care about the left-right movement, meaning we're not worried about photons that get diverted left or right. We want something that's coming straight to us. And we don't want the things that come into our field of view from over there, from the left, and then get diverted for some reason. We want photons that come straight to us and don't get affected by anything. So we're going to cancel the first term, that far right term, and get rid of that. So we only care about things that are coming straight to us and not coming from either side to side or coming in from the left or coming in from the right. We want things coming straight to us. Next, let's actually make our lives a lot easier and assume a flat universe and get rid of the curvature term. Now, we don't have to do this, but it makes the math a lot easier. So it's actually effectively pretty easy to do. And so we just get rid of that bottom term. So now we're simplifying this equation, and our final simplification is the concept of a null metric. And we eliminate the left-hand side, which means we set it equal to 0. A null metric means that light travels, it doesn't go any distance. That's what null metric means. It does not go any distance in space and time. It simply exists and is immediately, to its perception, immediately absorbed as soon as it gets emitted. So they don't really travel any distance in space-time. Well, that's kind of a weird way of talking. We know from our perspective, they go from left to right or from here to there. But according to the photons themselves, they don't travel any distance in space-time, which is fascinating. But when we think about this way, we actually can have a highly simplified equation that looks a lot like this. So that's what we end up with, and it looks really simple. We got a 0 on the left-hand side, we got time dt squared, and we got dr squared, which is kind of some kind of distance. We could have said x, but we said radial distance to kind of mirror the radial nature of the shaking of the photon. And we are left with that a of t, which is the scale factor. That's the a as a function of time, how the universe grows with time. So let's rearrange that equation to look at it. It's extremely simple now. We have c being the speed of light, dt is a little interval of time, and dr is a little interval of distance, and a of t is the scale factor of the universe as a function of time. So what we need to do then is add up all of the little contributions as it goes from here to there in time, and dr from here to there in space. And then we take into account A of t, the scale factor at every moment in this isotropic and homogeneous universe, what the scale factor of the universe is. So what that'll look like is this, and that's what summation, and that's what those kind of curly s's mean. Those long stretched out curly s's mean summary. So in integral calculus, we'd call this an integral, but we're just going to call it a big sum, and we're going to sum up all the contributions from the time it was emitted to the time it was observed. And that distance is 0, at the time it was emitted, it hasn't gone anyplace, and r is the total distance that it goes. And that might be, 100 million light years. R might end up being 100 million light years, and time of emission might have been, say, when the universe was 100,000 years old, and the time of observation might be when the universe is 13 billion years old. Could be anything. So that's the distance it will be traveling on the right-hand side, and the left-hand side is how long, according to the cosmic clock, it is traveling. And c is the speed of light, was a constant, so it gets pulled outside the integral. But really, that's the whole photon. But the funny thing is, we actually want to see the difference in length that happens to a single photon. Remember, we want to see the stretching of the photons, we want to see the distance. So really, we care about erasing between the top peak and the next peak. So we want to see the difference in length that happens to a photon. So we want to say lambda sub naught is the wavelength that is observed at divided by the speed of light, and lambda sub e, which is the wavelength that was emitted at. So we have a tiny, tiny, tiny change, that wavelength, which is the distance between two crests. So we care about just the distance between two crests. It doesn't change the distance over which both crests travel, but we want to see how that distance between two crests change with time. And so we have two equations, and we're going to take the difference between them. So the bottom equation is the first one that shows, well, here's how long it's going to travel. And then that didn't really specify which wave crest, that's the bottom equation. But the top equation of the two specifies the next wave crest in the wave packet. So we have two equations, and we're going to subtract the bottom one from the top one and rearrange it. So after we play around with the algebra and we do some fun with the integral calculus and how integrals work, how summations over lots of things work, we end up with the bottom. And the bottom shows that we only care about two summations. The first is when the time of the first peak was observed, time ob, because it's going the same distance, remember? It's ending the same distance, so we are only left with a time change. So the previous slide showed us that, it's both going the same distance, so when we subtract them, we get rid of the right-hand side. So we have to rearrange it because we have two things, one subtracted from the other, and we rearrange things, so with a little bit of algebra, we're left with this. So we only end up with the time of observation, that's what TOB stand for, and time of emission, which is T emit, that's what we have there. And we only care about the distance between these two extraordinarily short time intervals, TOBs and TOBs plus one wavelength, and then T emission to the time between T emission and the T emission plus one wavelength. So those are two really, really far distances. Now, here's the funny thing. Across two of them, it's not going to, across that very short time interval that we're summing over, from T emit to T emit plus one wavelength, and TOBs to TOBs plus one wavelength, the universe's scale factor will not change that much. So what we're going to do is we're going to treat it as a constant, the A sub t is a constant, as we go from one to the other. So all we really care about is the top equation. As the universe expands, what I've done is I've extracted from those two equations, the equation previously, the scale factor at the time of observation and the scale factor at the time of emission. Because in the tiny, tiny, tiny time interval between the passing of two wave crests, the universe isn't going to change size very much. So it's effectively constant, so we can extract it from the integral, and we're left with the bottom integral after we say, wait a second, that's just one wavelength. So the integrals that are to the right of the scale factor, the inverse scale factor, are just simply the wavelength at either observation on the left and emission on the right. So we have an extraordinarily simple equation that then can be rearranged, because this is what's interesting. If we only have a change in wavelength, then we have the redshift. But that's the redshift. We're just rearranging things. So we take that bottom equation and simply rearrange it, and we get the definition of the redshift. And that's what we defined previously. So 1 plus z, which is the redshift, is simply the ratio of the wavelength of observed to the wavelength that it was emitted at. That's the definition of redshift. We don't have to, that's nothing new. That's completely the definition. But because of the equations that we messed with and the stretching of the universe, we now know that the wavelength observed divided by the wavelength that it was emitted at is equal to the inverse ratio of the scale factors of the universe at those two times. So this is where we get it from. The stretching happens. The stretching of the wavelengths happen because the universe is actually expanding, and all the little tiny bits of expansion add up these tiny bits, but they only really matter at the beginning and the end, because that's the major changes that we actually see. Because we're looking at the effect on two successive wave crests. And as this photon travels, it gets very gently and the tiniest amount of stretching happens at each one. But by the end, it has changed. So when we finally observe it, we see the effect of the stretching. Well, what's nice about this is that we end up with a bunch of linked equations that relate back to the Hubble expansion, which is v of t, which is the speed, like in kilometers per second, is equal to the Hubble parameter, or the Hubble constant, h naught, which is roughly about 69 kilometers per second per megaparsec, and d as a function of time would be, say 10 megaparsecs or something. We know the redshift, which is a speed, is equal to the speed of light, c, times the redshift, z, which we measure by looking at the observed and emitted wavelengths of light. So if we know that it must be hydrogen, and we know the emitted wavelength of hydrogen, and we see the hydrogen observed, if we see what it observed at, maybe it's not 656.3 nanometers, but now it's like 700 nanometers. It's been lengthened, and that is the redshift. And then we can see from the redshift z what the actual size scale of the universe is then, as opposed to what it is now. Luckily, for our advantage in everything we ever do in cosmology, is we kind of define a of now, the scale factor of now, as 1 to make things a lot easier. And then or ago will be some number less than 1. That makes things a lot easier. And that also helps us with the definition of the redshift z. So if we have it equal to, we want a redshift of 0, today we want a redshift of equal to 0. Then if a of now equals 1, and we're looking at things that are really close by, then the redshift is of course 0. So the lesson that we want to really show is that we actually have a way of directly measuring the redshift of a galaxy, which is easy to do because we know what it's emitted at. So we then equate that to a redshift velocity, v, and that gives us the Hubble value, and that gives us the distance. This also demonstrates how we know, according to how we measure space-time in general relativity, using the Friedmann-Robertson-Walker metric, which shows how we measure space-time in a homogeneous and isotropic universe. How redshift itself naturally falls out because of the way photons work. They get stretched. Isn't that really kind of cool? I think so. We'll see you next time. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the cosmic microwave background. Last time we were talking about the nature of homogeneity and isotropy. Then we talked about the nature of the hot Big Bang and how it relates to redshift. Now we're going to look at observational evidence, one of the most amazing and compelling pieces of observational evidence that shows us that the Big Bang actually occurred, and it's the cosmic microwave background. The cosmic microwave background is part of one of the three main pillars of the Big Bang. The Big Bang itself is, of course, a physical model that explains the evidence that we see in the sky that relates to the nature of the universe. So the Big Bang itself has three major pieces of observational evidence, and we are going through them all. Actually, we've already gone through the expansion of the universe. We've talked about the Hubble law. We've seen actually how it works, where it comes from, and exactly how the Hubble law then extends because of cosmic density parameters, the energy density throughout the cosmos. Now we have two left to do, and this is the first of the second left to do, which is the cosmic microwave background radiation, which is the relic radiation from the early hot, dense phases of the Big Bang. So what we have then is a key prediction of the Big Bang. The basics of the microwave background are, and let's just say, I'm going to summarize all five here. The spectrum that we see in any direction in the sky is almost a perfect black body. And the temperature of that black body is 2.725 plus or minus 0.0101 Kelvin. So 1 millikelvin is how well we know the black body. The temperature is nearly perfectly isotropic. Nearly perfectly. Nearly is important. There's a big dipole anisotropy due to the net motion of all of the sun and Earth through the cosmos. And then finally, there are tiny, tiny, tiny anisotropies, differences in the appearance in different direction, but they're so small that they're only 1 part in 100,000 between any 2 points on the sky. So really, the temperature differences are extraordinarily tiny in the sky. All right. The cosmic microwave background is a key prediction of the Big Bang, and so the first law of thermodynamics actually tells us all about it. So first, we have to assume that everything is homogeneous and isotropic and so forth and so on. And then we're going to start with the first law of thermodynamics. And these equations tell us and give us the story of how the cosmic microwave background is a key prediction. So the first law of thermodynamics shows dq equals dE plus pdV, which means a small change in the total heat content of a system is equal to the energy input, meaning some sort of energy input by any form of energy input. And then you add to that, given the pressure on the system, if you change its volume. So what we have is that you have the change in heat is equal to the change in internal energy plus the pressure times the change in the volume of the system. And that comes from, the thermodynamics comes from the studies in the 19th century to understand heat engines. But the box that we're talking about and the system we're talking about is the universe. So we shouldn't expect there to be that they shouldn't expect to be heat flow into or out of the universe. All right, that kind of makes sense. With no heat flow into or out of the universe, the dq, Dairy Queen, whatever, no, not Dairy Queen, small change in the heat content is 0. So we should expect that to be the case. Now the third equation, P sub lambda, is the energy density due to light or highly energetic particles such as neutrinos. So radiation based off of relativistic particles, and that includes light. And so the radiation pressure is related to the temperature to the 4th power. And that alpha and the 1/3 are just scaling powers that relate the pressure to the temperature of the 4th power, which is very interesting, that radiation provides pressure according to its temperature. Yeah, okay, well, it's just an energy density. The pressure due to radiation is very small when the temperature is low, but as the temperature increases, you can have a larger and larger energy radiation pressure. All right, and the energy density that then we care about then is proportional to the if you have a perfectly homogeneous spectrum, absolutely perfectly homogeneous, then the energy density, then the pressure density is proportional to is equal to 1/3 of the energy density. All right, that's fine. So the pressure density equals 1/3 of the energy density. So we can then say, there's the energy density now is equal to alpha T to the fourth times the volume of the universe. So the radiation pressure is equivalent, well, I'm sorry, the P is not radiation density, it's pressure. Radiation pressure is proportional to temperature to the fourth power. But the pressure is an energy density. And so the energy density, the pressure due to the energy density of light is equal to 1/3 times that power. So then we know that if we have the energy of light, the energy density is the 8t to the fourth divided by the volume. Then we have energy divided by the volume equals an energy density, and that's alpha t to the fourth. Okay, so now we do know that the volume of the universe scales like the scale factor to the cube power. That's fine. I mean, it's got to be something like that. So it's not like there's 17 spatial dimensions. There's only 3. So the volume of the universe scales like the scale factor to the third power. So we plug that in and we find that the temperature is proportional to the inverse of the scale factor. So we actually plug and chug these things together. We use the fact that the energy density, we have a relationship between the pressure and the temperature, the energy and the temperature, which is also related to the volume. We take the pressure and energy equations, take little tiny changes to them, which make little tiny changes to both the volume and to the temperature, and that gives us a change in energy and a change in volume at a constant pressure, and that just involves some elementary calculus. And then out falls the temperature as a function of time, and the temperature then goes as the inverse of the scale factor, which is the redshift. So by taking a small shift in the energy, you get a small shift in the temperature, small shift in the volume, or a small shift in the pressure gives you a small shift in the temperature as well. But really, we're talking a small shift in energy and small shift in volume and small shift in temperature. So all of those things combined together give us the fact that the temperature goes as the redshift. So therefore, if you look at the temperature today, T sub naught, and this redshift for that time is 0, then the temperature back in time is higher because the redshift is higher. So the temperature will drop as time goes on. And that's what a key prediction of the Big Bang is. Using relatively simple physics, the first law of thermodynamics, the known radiation pressure due to a thermal blackbody spectrum, the known energy density of a blackbody spectrum, and the fact that the universe is expanding according to the scale factor. And we can use 19th century physics in order to make this prediction. In fact, this prediction came about in the 1930s that this should be occurring, actually 1930s and 1940s, as people were doing studies of nuclear bombs and so forth. So this is an old prediction that if you have an expanding universe and it's described by a redshift, then we should see a temperature rise as we go in the past. And this is why we think that the temperature was hotter in the past, because the size of the universe was smaller, the total amount of energy, heat in the universe stayed the same. The total amount of heat, that's a kind of interesting way of talking about it, the total amount of heat is the same, but yet how it's allocated between internal energy and the volume and the pressure changes. All right, so we then assumed the entire thing was based upon the idea of a thermal blackbody. So the pressure, the pressure due to a thermal blackbody radiation was given previously, and the energy density was also framed in terms of a thermal blackbody. So therefore, if today we see that the current temperature was 2.725, we can still run it backwards in time. Now, there's a reason why we would even think that we could actually predict in a very scary way what the current temperature should be in order to see what it is today. This is really something. We can actually make a prediction. We'll talk about that when we get to nucleosynthesis. But first, let's look at the nature of black body radiation itself. And again, all black body spectra are completely identical. They only differ by the temperature. That's the only thing. So this shape, if you see it, you've got a black body. And all stars have black body radiation. They're relatively so because they're hot, dense, opaque objects. Opaque means that the energy gets bounced around inside of there and thermalizes the entire star. Now that's interesting to say that the cosmic microwave background is a black body because at some point the energy has to bounce around in such a way that it all becomes the same temperature. However, you and I know that looking around in the stars today that the universe currently has multiple different temperatures. In the summertime it's hotter, in the wintertime it's cooler, the equator is hotter than there, and the surface of the sun is hotter, and so there's all sorts of different temperatures all across the cosmos. But yet we're describing the background radiation with one spectrum. So here's the effect of the expansion on the cosmic microwave background. Today it's seen in the radio as a black body. That's kind of letting the cat out of the bag. But if we go back and back and back and back in time until the universe was only 1 second old, the universe was mostly gamma rays. So if it was gamma rays when the universe was 1 second old, at about 100,000 years, it would be invisible light. In about 10 million years, it would go down to infrared, and today it's in the radio. So if you were around when the universe was only 100,000 years old, it would be glowing. The entire universe would be brightly glowing as though it's the surface of the sun. That would be crazy. Okay, so today, though, it's about 3 degrees Kelvin. And that corresponds to a region in the microwave spectrum of approximately 100 gigahertz, which is about a centimeter or so wavelength, and that is longer than infrared. So it's much, much longer than visible light. It's much longer than infrared. It's in the microwave region where things are about 3 centimeters longer. So that's where it's peaking in the microwave spectrum. So it was actually one of the most important discoveries ever in the history of everything. Hubble's discovery of the expansion was catastrophically huge. But then it led to a whole bunch of things to say, how do we explain the cosmic expansion? And then this particular discovery even went deeper into the past. So what we find is that you could make a prediction based on this idea that what Hubble found, that the universe had a hot beginning. And the prediction of the cosmic microwave background was given by Alpha, Hermann, and Gamow in 1948 when they were working on Big Bang nucleosynthesis, which we were going to be talking about. And it was pretty much ignored because nobody figured they could ever see it. But then along come a couple of researchers, and were looking with when they were working around, and this got them the Nobel Prize. So Penzias and Wilson got the Nobel Prize for discovering the cosmic microwave background using the microwave receiver that you see there. So how did they do it? In 1965, they were working at Arnold Penzias and Robert Wilson were at Bell Labs in Murray Hill, New Jersey, which is really right close to where I'm at in New York City. And they were mapping the sky at microwave wavelengths, and they were also doing some preliminary tests with the Echo satellite in order for Cold War stuff, so that we can talk to people over in Manchester, England, by bouncing microwave satellite transmissions off of Echo 1 satellite. And so they were doing some tests with that, and part of their tests were mapping the sky at microwave wavelengths. But they noticed that there was a faint microwave background noise. And that background noise was something they couldn't get rid of. And so they were, they're good researchers. So they say, well, we got to find out where the heck this background noise is. And they thought there were a bunch of equipment problems. They replaced their amplifiers because, who wants that static? So they must have bad amplifiers. They must have bad things in their radio amplifiers. Well, they replaced that and still was there. They went up into the antenna feeling desperate and found that there were some pigeons that had roosted, and they cleaned out the pigeon poop from the antenna because it's a big, big, big antenna. And so they cleaned that out, and it was actually part of their research paper is actually said, okay, this was assured that wasn't a problem. They went out and discovered that no matter what they did, changing the amplifiers, cleaning out the pigeon poop, anything that they could think about, they discovered that it was literally coming from all directions in the sky at once. And what this did is that this gave them the cosmic. This was a discovery that gave them the Nobel Prize, I think in 1978. So I think I got the wrong number there. But they discovered by accident the cosmic microwave background radiation. Now the funny part is that up the hill and up the street in Princeton, New Jersey, there was another team member led by Peebles and Dickey that were building a similar instrument in order to purposefully go and look for the cosmic microwave background, and they were just about to turn on their machine in about 2 weeks. And then Penzias and Wilson basically called them up and said, "Hey, I've heard that there's a cosmic microwave background thing going on. Could you tell us more? Because we got this background hiss that we think is coming from everywhere." And Peebles and Dickey said, "We just got beat with a Nobel Prize by 2 weeks. Grr, snap, snarl." So they both released a couple of papers. Penzias and Wilson released their paper on the detection, and Peebles and Dickey released a paper on the theoretical background. They had hoped to do the paper on the detection as well, but they did not. So Penzias and Wilson won the Nobel Prize. Well, the universe, therefore, as a result of this, because this glow is happening all over the sky, is filled completely with this cosmic microwave background radiation. It's just light. It's light in microwave wavelengths. And it's almost, but not quite perfectly uniform in all directions. Now, for Peebles and Dickey, they thought it was completely uniform in all directions. And this was the first evidence. Dickey and for Penzias and Wilson, this is the absolute first reference of the proof that there was a hot Big Bang that was predicted, and they found it. They found the predicted radiation that should be there if the universe had a birthday and went through a hot, 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 dense phase, just like we described at the beginning. So now, this glow that is there, that is from the Big Bang, shows a specific pattern that would be equal to if you had random hot gas blown up to the size of the universe. They're tiny, tiny, tiny anisotropies or irregularities or differences in temperature between one direction and another, and some of them are on some of them are one size scale and some are on others. And what you do is you find that they actually match what you would expect if you have tiny thermalized fluctuation if you expanded the size of the observable space to what we see today. Now, therefore, this background radiation, they really studied it hard, cannot be due to background point sources. It can't be, because there are too many other things that it's too smooth on too small a size scale for it to be due to that. That would imply extraordinarily tiny, extraordinarily close, extraordinarily dense objects, so it cannot be background point sources. And it is completely the same temperature down to 1 part in 100,000. But the next trick is it really blackbody radiation? And Penzias and Wilson determined that it fit a cosmic background radiation of such and such a temperature, but they weren't exactly certain that it did have that exact thing. So there is a very specific prediction, as we described before, using simple thermodynamics and simple energy conservation equations, and then the expansion of the universe as known by everyone. There's a prediction that it should be a perfect black body, that it should be characterized by a single temperature. But now there was a tantalizing thing that Penzias and Wilson had found, but nobody had the instrumentation in order to do it. So basically, people had to run to the South Pole or go way up high in altitude or get out in orbit to actually determine conclusively whether or not this is actually a black body radiation. And that was one of the main key hunts that was on in the 1970s and 1980s in order to determine whether or not this truly was. And finally, an incredibly important, there's some other data you can go check out and see all the microwave data, the missions that were done in order to actually found that, to detect it. So one of the most important missions to discover whether or not it's actually a black background radiation was done and released in 1992. And this is the Cosmic Background Explorer Satellite, which was a NASA mission to go and actually map the cosmic microwave background. So the COBE satellite, Cosmic Background Explorer Satellite, was the first satellite that would be capable of detecting whether or not it truly is a black body radiation. And in 1994, they published this result from the Far Infrared Absolute Spectrophotometer, which was one of the instruments on board COBE as it orbit in a spacecraft. And they found that it was a perfect black body to within 2/10 of 1%. And the temperature they found was that it was 2.725 Kelvin, or almost 2 3/4 degrees above absolute zero. And normally when you report data, you always say what you expect your error bars are and how well you know it. This data is so incredibly good that they had to use 400 sigma error bars. The standard 3 sigma error bars would be too tiny to actually see. And so when this was published and presented at the American Astronomical Society, there was a long standing ovation for it, because this finally was proof that the cosmic microwave background was a true black body as averaged over the entire sky. So even averaged over the entire sky that they took, it still is a perfect black body to 99.99999%. That's what 400 sigma is. It's even more than that. But basically, we really know that there's a cosmic background radiation, and it's really a black body, and it's really in every direction, and it really permeates every location in the universe. All right. So the cosmic background DMR, so then there's the differential microwave radiometer, looked for anisotropies in the cosmic microwave background. And so what it did is it looked for temperature differences across the sky. And it mapped things. It said, okay, fine, the FIRES is going to go look for specific, whether or not it's actually a black body, and take a high resolution spectrophotometry at multiple wavelengths in order to determine it. The purpose of the DMR was just to say, choose a few wavelength bands, and specifically this was in 53 gigahertz, like 6 millimeter wavelength. And so then you look at those things and look at the temperature differences that you measure across the sky. And so at first, he said, well, what's the base background? And they said, fine, across the entire background, what is an average of 2.275? So this is an early quote, this picture. And so I'm not going to change their early pictures. This call comes from the NASA website from an early data release. The second picture, or middle one, shows the dipole emission, meaning that is because of the motion of the Sun and Earth and Milky Way through the cosmos. The total sum of all of the motions of the Earth and Sun and Milky Way through the entire universe is reflected in the middle graph. And so where it's hot, meaning red, that's where we're going in the sky, and where it's blue is where we're going away from. And so these are all sky maps. So when you remove the dipole anisotropy, you then get the remnant anisotropies, or little tiny lumps on the size scales of about 7 degrees in the sky. So that's all they could really do, is about 7 degrees. And so they found enormous anisotropies, and most of those were due to the Milky Way. But there was some tantalizing things about the nature of the Cosmic Background Explorer, and looking and saying, well, there's galaxy clusters. We're seeing all this huge thing. So once we get rid of the cosmic background radiation, we get rid of the foreground radiation. The anisotropies are on the order of only a few microkelvins. So this is a very, very, very important result. All right. So then in 1992, the data was published in terms of their better, more cleaner data to demonstrate after removing the top one is the anisotropy due to the dipole. The middle is leaving the Milky Way emission in, and the bottom one is after the Milky Way's contribution has been removed. And those are the fundamental background anisotropies that were discovered by the Cosmic Background Explorer. And what that shows is that this then becomes the new holy grail, is to discover all of these kinds of anisotropies, because the shape and statistics of the anisotropies in the bottom thing is the thing that shows you the print of exactly what happened in the early universe, as the cosmic microwave background was being formed. So now we know not just that the universe is permeated with this light, but now we can use this light to actually probe the deepest, the earliest times in the cosmos in order to understand what was going on back then. So what was then later done is that the Wilkinson Microwave Anisotropy Probe was launched, and it had much better resolution. It was able to determine a much greater depth of the cosmic microwave background. It observed in many frequencies, and then was able to make a more higher resolution map of the sky and give much better statistics in terms of the cosmic microwave background. Then the Planck mission from the European Space Agency was then launched and superseded and added to the mix. So there are three main missions that occurred in the past that looked for the cosmic microwave background from orbit, with the Planck mission being the most recent. And so these things all came with the same result, that there is a uniform background radiation, that there's small anisotropies, there's a dipole anisotropy, and the first results for this were announced as recent as 2013. So here's what Planck does. This is what they all did when they mapped the sky. And so I'm going to kind of show you how the mapping occurs of the cosmic microwave background to show it to you. And now the only thing that's really kind of deceptive about this video that European Space Agency put out is that it makes it look like that the little critter is making a beam, like Cyclops in the X-Men or something like that. But no, it's not painting a picture. It is looking to see what is out there. And the beam, rather than coming from the spacecraft, that's the beam that it's looking along. So the light is coming from the thing that's being painted and going to the spacecraft. So it's what is finally being observed. And so it's not being painted, it's being observed. And so then when we spread it out to show a full sky map, we then compare it to the optical image of the full Milky Way, and that's the Planck map that was released. And now we can see that this is what the little spacecraft does. It actually observes in radio frequencies or microwave frequencies. So the three spacecraft show roughly the same results. They all show a tiny variations in the cosmic microwave background. There is increasing resolution of the anisotropies, with the Planck being the highest resolution, COBE being the lowest. All of them provide incredibly important data because these are the three main missions that have done it. And they contributed massively, and without exception are some of the most important missions to have ever flown in terms of understanding fundamental science. So what does this cosmic microwave background really look like, and how do we get it? So from the Planck mission, again, we have, first you take the full sky map that was created, map out the individual sources in the sky, and then remove them or subtract them from that data. And then you make a map of the radio emission due to the Milky Way galaxy itself, and then you subtract that from the data. Finally, you look at dust emission from the dusty clouds that float around in the Milky Way, and subtract that from the data. And once you're done with that subtraction, you're left with the cosmic microwave background. And that is what is in the sky when you finally take into account the contributions from the Milky Way and individual point sources, and spend a lot of time deciding which is what and what is which. And so those all-sky images are provided by the European Space Agency. All right. So we can actually say that these three probes provide spectacular confirmation by amazing observational work by three different groups, two different space agencies, and show that there is a strong case for the Big Bang, meaning there was a perfect blackbody spectrum which was predicted in the 1940s. It's characterized by a single temperature across the sky at 2.725 plus or minus 2 millikelvin. It fills the universe uniformly, and the tiniest structures are only at the 1 part in 10 to the fifth. So those lumps and bumps that we saw in that final thing are only tiny bumps that are differences in temperature of 1 part in 100,000. It's not like something is like 10 degrees hotter or 100 degrees hotter. No, it's 1% of 1,000th of a degree. 1% of 1/1000th of a degree, or 1%, 10% of 1% of 1% of a degree. So it's a really, really, really tiny, small amount of temperature difference that's found. And it's that tiny temperature difference and those statistics on that lead us to understand what happened in the early cosmos. And that's what we're going to talk about right now. So if we go back in time, all the way back in time to when it's hotter, let's go back in time until the universe was so hot that it was as though that the universe was ionized, where there were no atoms, where atoms were not possible to have. Because if the universe was so hot that there were no atoms, then the electrons would be free, and if the electrons are free, they're zipping around, and electrons interact very strongly with photons. And so they can scatter and absorb and re-emit with great ease. So if the electrons are free, they'll scatter with the photons, and the electrons pull on the protons. So basically, the electrons and photons will become all of the same temperature. What temperature does that happen? Roughly about when the average surface temperature as of an M dwarf star, or about 3,000 Kelvin. To get to 3,000 Kelvin, when the current temperature is about 2.75, we have to go back to a redshift of 1,100. So at redshift of 1,100, the entire universe was ionized and glowed like the surface of a star, as though we were in the surface of a star. That was the universe at redshift 1100. So what was it like in that time when the universe was at 3,000 Kelvin? It was too hot for atoms to exist. They hadn't formed yet. So we're going back in time, so we're actually running the clock backwards. So we have some point, so we're close to time zero. We don't know yet how far that is, I haven't described it. But sometime after time zero, it was still far too hot for atoms to have formed. But there were a lot of photons, they had a lot of high energy, and they kept the protons and electrons from combining into atoms. So therefore, everybody was scattering around. And so in this little diagram, I'm going to play a game here, and the yellow squiggles are photons. They are particles of light. The red dots are protons, and protons are the heavy little things that make up the centers of hydrogen atoms. And then the electrons will be the blue dots with the yellow shell. And I use a yellow shell because electrons really do a good job of scattering off of photons. All right, so first and foremost, let's see what the universe kind of looked like at that time, how things moved around. This comes from NASA Jet Propulsion Laboratories as they described their contribution to the ESA platform. And so what we see here is we have little green dots. The little green dots are the electrons, the big red dots are the protons, and the little bouncy doodle whackers, those are particles of light called photons. And so the photons would bounce off the electrons and scatter off of them, and so therefore they would impart energy to each other, and they would scatter, 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 and so because they're all billiard balling around off of each other, they all work out to become the same temperature. And because they're the same temperature, because they're interacting so rapidly and the electrons and photons are interacting so much, they stay at the same temperature. And because the electrons pull on the protons really hard because of the electrostatic force, then the protons get to be the same temperature as the electrons as well. So this is what we call Thomson scattering, and it's the scattering of photons off of electrons. All right. Now then, here's a picture of what it means for a scattering event to occur. So we got this hydrogen atom sitting there. Maybe it got cool enough so that, I got close. So the electron got close enough to make an atom. And along comes an energetic enough photon. And here comes the photon, comes along, boom, and the electron ionizes, it absorbs the energy of the photon, it ionizes, and now it's no longer part of an atom. There is extra energy, then it provides a little bit of a kick, so the electron moves off into another direction carrying that energy. But, another ionized electron then will come along, and boom, it will be absorbed into the atom as an atom and then emit the photon, and boom, the photon will then move off onto its own way and going, and it'll scoot, scoot, scoot over here and over there and over here, over there, and then boom, the electron and photon can scatter off of each other also. So they interact, like a bouncing pair of billiard balls, and off they go, and the electron then comes back, they pull on each other, and boom, they try to create a hydrogen atom. So this process that we see happened over and over and over right around the time that the cosmic microwave background was being formed. And so the light that was there was scattering off of these electrons, and it was as the universe was cooling. Now I've put a background grid to show that the universe is expanding, and so let the universe expand. It's always been expanding, but now the universe has expanded enough that it's made the light too long a wavelength. Now that the light is too long a wavelength, it can no longer ionize the atoms, and so therefore the light doesn't interact anymore. This is called the epoch of last scattering. And it's the last time the photons had scattered off of an electron. Because now the electrons are in atoms, so they can't scatter anymore. So there were two processes, ionization and scattering. So there was a combination epoch where all of a sudden, or it's called recombination, which is really irritating, but it's a combination epoch where where things start to become atoms. They go from free to becoming atoms. So I was kind of doing two epochs at once, the combination, recombination epoch, and the last scattering epoch all at the same time. And so there was a time when nothing was making atoms, and they were just scattering only. And then it got cool enough so that atoms could start to form, but there were some photons that were wandering around that could ionize a few. Eventually, there weren't enough of those, and then there were still some free electrons that could scatter a little bit, but then the universe stretched and didn't have enough energy to keep the electrons ionized, and so then there became atoms, and now the photons streamed freely, and it's now these red photons that you see kind of zooming off to the lower left that is the cosmic microwave background. So that's really something. So there were three basic epochs of the cosmic microwave background. Right around redshift 3570, or when the universe was about 50,000 years old, the average temperature of the cosmos was about 10,000 Kelvin, or just under 10,000 Kelvin. Everything was completely ionized. There were absolutely no atoms whatsoever. They did not exist. However, there were nuclei of atoms, and there were electrons, and there were photons, and it was hot enough that they were all in the same temperature. So at the era of radiation matter equality, prior to this, radiation had the highest energy density, but after this, matter had the highest energy density, and this became quite apparent very soon. So recombination, which is kind of funny because it wasn't like they were ever combined to begin with, and that's a really irritating logism. It should just be combination, but it's not. Thanks, guys, for historical stuff. We call it recombination. That's silly, but whatever. The epoch of combination happened at a redshift of about 1370. The universe had expanded and cooled to a temperature of about 3700 Kelvin, and that was when the universe was 250,000 years old. And decoupling occurred when the electrons and photons no longer were in thermal equilibrium. That's what decoupling means. And so when they're no longer in thermal equilibrium, there's still some scattering events, but now the electrons are no longer have the same thermal temperature profile as the photons. And then finally, last scattering is the time at about a redshift of 1100 when the photons last scattered off of some electron. Now, all of these epochs are, of course, not like momentary things. It takes time for them to kind of smear out, and because there's a lot of electrons, there's a lot of photons, there's a lot of protons, there's a lot of atoms, and so basically the only thing that we can say where it's been traveling in a straight line to us is from the epoch of last scattering. So the last time a photon was scattered, until we observe it, we're seeing the universe as a picture of it was when it was about 360,000 years old, or sometime between 240 and 360,000 years old, if a photon came from one of those regions. So we're looking at the universe as when it was only about 360 or 350,000 years old when we look at the cosmic microwave background, and that is what we see in the sky. That is the last scattering surface when the photons were finally able to stream freely towards us. So this is the high-resolution image of the last scattering surface when the universe was only about 360,000 years old. And compared to Kobe's very poor resolution at 7 degrees, the angular size of that was able to be seen by Planck is much, 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 much smaller. Luckily, Planck can get down to much tinier angles, and the last scattering surface, if you went back, how big was the universe? You could look at the scale factor. The universe was 1,000 times smaller. And what's 1,000 times smaller on this surface? Well, something about 1 degree. So a little patch of sky about 1 degree in size became an entire universe. That's a really scary thought. So every patch of sky that you see here became some whole universe. Patch of sky meaning about 1 degree across, which is really interesting. All right, so what it measured, and this is interesting how Planck actually does its measurements, and the critical measurements of the anisotropies to say, well, how do we know what its anisotropies are, and what is the scale measurements? And I'm going to show you what that is, but I need to show you how it actually does a difference in temperature. And this is what we call a differential temperature measurement. What you're going to do is put 2 circles on the sky. And those circles are the beam of the telescope. And that telescope says, okay, what's the temperature inside this little circle? And then you say, compare that to the temperature of a circle at a given angular distance away in the sky. Then rotate it around and do it for every pair of circles at that angular center. So here's what we look at for a large angular separation. It'll look a little like this. So we have a large angular separation, and we do it over every pair of points in the sky. And then we do small angular separations, and we do it for every point in the sky. And then we do even smaller angular separations, and we do them for every point in the sky. And after we've done every point in the sky, every angular separation from that point in the sky for the beam width at a given frequency, then we make a map. And it's called the power spectrum. The power spectrum is incredibly important because it tells us amazing information about it. So the power spectrum shows how big the temperature fluctuations are at that angular size scale across the entire sky, meaning you take the average of the square of the temperature fluctuations, and you see for 2 degree angular separations, we have this kind of static sort of appearance, but the largest peak of all is centered around about 1 degree, and this is the greatest power of the temperature fluctuations, meaning these are the largest amount of temperature fluctuations inside of about 1 degree. Then we have an important portion that's just about between 1/2 degree and 2/10 of a degree, and that is where we get to learn about dark matter and cold dark matter, as well as normal matter. And finally, way out there, we determine the thickness of the last scattering surface because the scattering surface will knock out the little tiny angular sizes. Combining all of those together gives us the picture of the statistics of the temperature fluctuations across the entire sky, and that's called the power spectrum of the Planck measurements. All right, so Planck's measurements then said the large angular fluctuations across the entire sky, which I give in my little circle diagram on the left, and medium-sized ones in the middle, and tiny, tiny, tiny ones on the right. So the angular size is the separation between the various circles across the circle, so red to blue diagonally across. Not next to each other, but diagonally across, just like so look at not next, but across the circle. So a red to a blue across the circle. And then you say, what's the temperature difference across there? And multiply that temperature difference, take the square of that temperature difference and see where the greatest fluctuations are. And the greatest fluctuations happen at the 1 degree angular size scale. And then you have this strange pattern that occurs across this size scale difference. All right, so what this means is that the universe kind of can be perceived as ringing like a bell, because these are ringing oscillations on the surface of a sphere, and that's another way of looking at it. These are spherical harmonics, and that's how, if you look in the literature and took a cosmology class, you would be talking about the nodes of the oscillations and the vibrations, and you take the statistical version of this, and then they would say, okay, what is the height, the importance of the statistics on various nodes of the vibrations? Okay, so each of these moments, which are the multiple moment, is what they call them. So the dipole is one direction and the other. And so we have moments, meaning sources or points about which the vibrations apparently occur across the sky. The fewer, the more dipolean, or 1 is just pulsing in and out, 2 is ringing up and down, 3 is a 3-pole moment, there's a quadrupole moment where there's 4 points on the sky that things are vibrating around. And then you get larger and larger and larger moments, which tinier and tinier and tinier size scales. So the higher the moment, the higher the pitch, the shorter the wavelength on the spherical surface. The universe could be seen as ringing like acoustical oscillations. And in fact, that's a good way of thinking about it, because remember, the electrons are vibrating, or not really vibrating, but being shoved around by the photons. As they're being shoved around, they're moving. And if they're moving, they're bouncing against the photons, right? So we can actually think of the matter as oscillating back and forth as a result of it. And so the oscillation also applies to the photons. All right. The first peak, the largest peak, is indicative of the universe, the size scale of the universe at the time of last scattering. This is the time when the universe became transparent. And so the size scale of the universe on the sky was about 1 degree. So everything that was 1 degree was the same size as the universe. Take our universe and go back in time. How big was the universe on the sky? It was about 1 degree. So therefore, we're looking out into space. So we're looking back in time at other locations that have expanded away from us since that time. So therefore, we're looking at, for every 1 degree patch, we're looking at a separate universe, a separate one. So we're looking at separate universes, and each of them have about 1 degree. So we now know that there's lots of universes that are very similar to ours way out there, and they all had the same size of last scattering. So the degree of flatness, the peak in degrees, the degree of flatness. If the universe was open, the peak moves to the right. If the universe was closed, it moves to the left. And this peak shows the biggest compression or lump at the time of recombination. The whole universe became transparent. So we can predict whether or not the universe is an open or closed universe in terms of geometry by where this peak occurs, left or right. Interesting. And how that works is, if you have light, you can see like how big things appear to be. The patches, if they are flat, if the universe is flat, then the hot spot has its real size. If it's an open universe, the hot spot is actually smaller in apparent size than it actually is, so it moves to the right. If the universe is closed, then the hot spots appear bigger than they actually are, so the peak moves to the left. So this shows the relationship between the power spectrum and the angular size of the hotspots. Okay, so that also measures the total amount of normal matter in the universe. The more normal matter, the higher the peak. And because the normal matter gives lots of ways to cool off and falls into gravity wells. So the more normal matter there is, the higher this peak will be. And this is a comparison of the results from the W map that clearly shows that if we map with the universe having a baryonic matter of only about, if we look at the different baryonic matter about 5%, just under 0.046, or about 5%. The 0.546 is about 5% of the entire universe is made up of normal matter. Then that is what we correspond. But if you see that if we alter the total amount of normal matter, we make it more, the peak gets taller. If we make it less, the peak gets shorter. And also see how it kind of bounces the other little peaks to the right. And that tells us something too. So really, if we give it more normal matter, the peak goes up. We give it less matter, the peak goes down. So these are all mathematical predictions. All right, so the next two show a ratio of the height of the next two pairs. The dark matter, the ratio of the height between the two is how much dark matter there is compared to normal matter, which we call baryonic matter. So dark matter doesn't slosh around because it doesn't interact with light, so it doesn't slosh around, it doesn't group, it can't lose energy, so it doesn't really participate in that ringing. And so since it doesn't slosh around as much as normal matter, it basically says is that you will have a greater it shows, so the dark matter, so the increases the difference between them. So the second peak shows how far apart big globs got because before they got pulled back together, and the third peak shows the size of how compressed the biggest blobs got when they got smished together. Because, you think about those electrons and protons, they're moving around and they're kind of, on average, behaving like globs that are getting farther apart and closer together. So dark matter weighs all this stuff down, and normal matter kind of acts springy and moves better. So if dark matter, the way to think about it is that normal matter is like a guitar string. If you pluck it outside of the water, it'll vibrate nice and easy. But if you put it underwater, then it will vibrate more slowly. And so it'll change the resonance frequencies between them. So the ratio of these two things is, these two peaks shows you how much dark and normal matter you have. Finally, way out there, there's a tail of stuff that gets damped. And why does it get damped? Because the last scattering surface is not a solid surface. It's not a sharp thing. It takes time for the light to go through the last scattering surface, and the thickness of the last scattering surface, the thicker the last scattering surface is, the more these little lumps and bumps will be smoothed out and become nothing. Actually, there will be fewer and fewer peaks, and it'll just become a smooth curve. So the tiny bumps will get washed out if the transition goes from opaque to transparent. It takes a very long period of time. During the last scattering surface. So that tail actually measures how long the last scattering surface lasted. With all of this information about the power spectrum and doing mathematical modeling of what we know about how matter moves, how the size of the universe works, how energy gets distributed among matter, and how things move around under this course, we can then determine from this data the age of the universe. And the age of the universe from this power spectrum says that the universe is 13.799 billion years old, plus or minus 21 million years. That's really much, the accuracy of that is better known than any fossil in any museum in the world. That is wild. So what's really neat is that we can also determine that we also think, because the shape of that curve also says that at some point deep in the past there was a massive growth. It's consistent with the inflationary epoch interpretation, which we haven't talked about yet, but we'll get to. And that is consistent with it as well. So the main results are, and you don't have to memorize this, please don't memorize this, just look it up. The main result of fitting that curve, there are 6 numbers that are used to fit the curve to the data. See the green curve? The red dots are the data. The green curve is the mathematical model that fits the data. All you need is 6 numbers and the mathematical equations to plug in to fit them. One of the numbers is the Hubble parameter, and they determined it to be 67.31 kilometers per second per megaparsec. Another one is how much dark energy is in the universe. 68.5% of the universe, in terms of its energy density, is dark energy. The next one is baryonic density and cold matter density, and that's the ratio of those two peaks, right? That's about 5 to 1. Is the cold dark matter to baryons about 5.36 to 1. So the total, so of the remaining matter, about of the remaining 21% is cold dark matter and baryonic matter, where only about 5% of the universe is normal matter, baryonic matter. So therefore, we can also plug in the dark energy density, what is the actual energy density, the electron volts per cubic centimeter. The baryonic density is given in grams per cubic centimeter, but we don't give dark energy in terms of mass because dark energy has no mass, it just has an energy density. And then we can also plug in a putative age of the universe of 13.799, and that's what we get for this moment. And the link there, the 2 links below show exactly where all these numbers come from. And if we then add one more parameter to it, We now know how much matter is in the cosmos to within 1%. We know how much normal matter is in the universe to within 1.1%. We know how much cold dark matter there is in the universe to 1.4%. And we also know the total amount of dark energy in the universe to 3.7%. This is really strange. That is incredibly strange. And that number is that's a lot of dark energy. And we'll talk about that later. And if you can look at that, that's a very odd thing. It's called a core problem with the standard Big Bang model, but we'll talk about that later. Actually, it's a problem with standard particle physics. There are lots of areas of research and things that need to be dealt with, but we're not talking about those. We're talking about the nature of the Big Bang, starting from about 300,000 years after the Big Bang, right? So we're starting from this hot, dense place. And given one more parameter to that model, we get that the total energy density of the universe, which is that omega, what is the total energy density? It is consistent with a flat universe, 0.99995 plus or minus 0.0034, which lets it be a flat universe. It also allows it to be a little bit more dense than flat. It also allows it to be a little less dense than flat. But mostly, it says that it's very consistent with a flat universe. So we actually think that it is a flat universe. So this is the evidence that we have for it. We also have there's also some predictions based on neutrino masses and how many neutrinos there are, and the tensor scalar ratio it determines that's best left for you to go look up, because I'll have to go 20 minutes in order to understand that. Okay, so as photons propagate through the cosmos from the last scattering surface, we see a wall of photons traveling through the cosmos, and they are illuminating the cosmos as they go. But as the universe progresses in age, matter falls into gravity wells and forms clusters of galaxies. It forms structures like you're seeing created through time. And so it was very, very, very smooth. And then gravity works and pulls stuff together into clusters of galaxies. We now know there's clusters now, but there weren't clusters ago. And as structure is formed, as the universe ages, we go from the left, which is ago, and the light traverses this and gets deflected by the matter in between, so the cosmic microwave background can be redirected by the gravitational field that it experiences as it goes through the different evolutionary stages of the universe as it goes. So the cosmic microwave background may go through things. It might get a little energy here, might get a little less energy there, and so there's a slight shape of the hot and cold spots in the cosmic microwave background. And by studying that, we can actually determine the actual shape of the matter in the universe, and that map looks a lot like this. So undoing the directional data and the lensing that is apparent inside of the data, and taking into account the microwave, what we can't do because of the Milky Way in the way, we find that where it's darker is less mass, and where it's brighter, there's more mass. So we're looking at huge concentrations of mass that are present throughout the cosmos. And this is the mass through which that the dark matter, this is mostly dark matter that we would be looking at, that the light had to have passed by or through in order to get to us from there. All right, so the real journey that we would have experienced in the cosmos is shown here on this wonderful little video that is given by NASA, and this is called The Journey of Light Through Space and Time. And we can just take a peek at it, and what we find is that this Planck spacecraft busily scanned the sky, and this particular video was created by a NASA group. I think I turned off his sound. I hope I did. Let's see.
370,000 years after
I'm going to try to turn off his sound and make it mute, so it'd be me talking rather than somebody else. What we have here is that here's the universe when it was about 370,000 years old, and this I'm dubbing over Charles Lawrence. Sorry, Charles. I'm taking your thunder. So what happened is that the cosmic microwave background, the light is interacting with all the electrons and photons until the universe expands enough so that it's cool that the electrons could bind with the photons, and then all of a sudden they stream freely. Now that was the last scattering surface. So from that point, the photons are scattering. They go through and they pass by galaxies as they're forming in the early cosmos, past the first stars. They get bent in their direction and get redshifted as they travel. Notice the color is changing from blue to yellow. And sometimes they go into a galaxy cluster where they encounter an electron and get a little extra energy hit and get diverted again. They have been redshifted all the way down to the radio light, passing through the entire cosmos until they enter the Milky Way and then get gobbled up happily by the Planck spacecraft. And after this travel that they did, we then map where those photons came from in their 13.8 billion year journey, and that is the map that we see in the sky. So that is what we've seen, and that amazing view. Thank you, JPL and European Space Agency, for creating that video. That was a fantastic video. I'm sure you can go find it elsewhere. And there's some review questions for you to review if you wish to do so. And there is our amazing talk about the nature of Planck and what we know about the age of the universe. The universe is about 13.8 billion years old. We know the expansion rate, and it's all because of the cosmic microwave background. The cosmic microwave background itself is insanely important in order to understand what the history of the universe was. The cosmic microwave background was predicted in the 1940s, observed in the 60s, and it was refined in the 20-aughts and 2010s. So cosmology went from being stories told around a campfire to now a precision science where we know the age of the universe better than we know the age of the dinosaurs. That's amazing. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're now getting to the first 3 minutes of the universe. This lecture is, of course, based off of, I'm totally stealing the name of Steven Weinberg's great book, The First 3 Minutes, but because it's the first 3 minutes. So you got to go read his book. His book is an amazing book. But what we're talking about now is we're looking at the elements of the Big Bang that led us to that predicted the existence of the cosmic microwave background. So the cosmic microwave background is part of the Big Bang model, but the Big Bang cosmic microwave background was predicted by nuclear physics experiments in the 40s by people working on the bomb. So let's look at what we mean by that, because this is quite practically, from most cosmologists' perspective, the predictions and the physics associated with the first 3 minutes of the universe's history are extraordinarily well known, they're extraordinarily well understood, they integrate a lot with what we already know, and so we can actually see some amazing things that occur as a result. All right, so here we go. Big Bang cosmology. We have the principles of homogeneity and isotropy. Those things dictate to us as with general relativity and cosmology, Einstein's relativity actually said that we can apply the laws of physics everywhere. We then observed that there was a redshift, that all galaxies are rushing away from us, which led us to the idea that the universe was smaller long ago, which then led to us some basic thermodynamic arguments that gave us the cosmic microwave background. But then there's an even more important thing. If we go back far enough and compress in time, we get to a point where the universe is so incredibly tiny that and so incredibly hot that maybe it goes back to the point where the universe was as hot as the center of a star. And if that occurred, then there would be nucleosynthesis just like that's occurring inside the sun. And let's see if we can use what we learned about stars here. And the answer is we can. So the hot Big Bang, we can see again that what we see now as the universe is a cold, low-density place. All the galaxies are getting farther apart. The universe is expanding. It's getting cooler. But in the past, the universe was hotter, smaller, and denser. But is there any direct evidence of this hot, dense early phase? And the question then becomes, hey, where's this helium coming from? It's a really good question. Remember when we looked about the nature of stars, and we looked at the Milky Way? We had two different populations of stars. We had population 1 and population 2 type stars, and this was really important. We found, though, that on all the stars, they had a minimum amount of helium. No star yet observed has less than 25% helium in its atmosphere. Population 1 stars have about 28% and a lot of metals, and so therefore they're later generation stars. So population 1 stars came from older stars going supernovae and depositing their stuff, and that went into clouds and formed new stars. We talked about that a long time ago, yada, yada, yada. So metal-poor stars, though, come from the early cosmos. We know that globular clusters have HR diagrams that sit them at about 10 to 12 billion years old. Some of the oldest globular clusters are nearly as old as the universe itself. So where did the helium come from? Where did it come from? They've got to be already in the first star. So where did helium come from is the exact question we're after. All right, so we now know that the universe has lots of different kinds of particles. We have hydrogen in the upper left, which is a proton with a neutron around with an orbiting electron. So we've got hydrogen, one hydrogen, is basically it's got a proton and it's got a mass of 1. It's got 1 proton and no neutrons. A free proton is just all by itself. It doesn't have an electron orbiting it. And electrons, they're free. They can be ionized too. So protons and electrons don't have to be in atoms. They can be ionized. If you have heavy hydrogen, there's a proton and a neutron. And if it's an atomic heavy hydrogen, the electron is in the ground state orbiting it. That's H2/1. And so that is heavy hydrogen with 2 particles in the nucleus, and one of them is a hydrogen atom. So one of them is a proton, so therefore it's hydrogen. Now, if we look at light helium, it has 2 protons in the nucleus, and it has 1 neutron. And so it's called light helium, and it's got 2 protons in there, but 3 total particles. And because it's got 2 protons, it can attract 2 electrons. And we got photons there bouncing around to do the ionization and just say, hey, would you like some light? And we've got helium nuclei with 4 objects in the core in their nuclei and 2 electrons orbiting them. The universe has got particles. It's got neutrons, it's got protons, it's got quarks, it's got photons, it's got electrons, it's got tons of different kinds of particles. And the standard model of particle physics tells us that together with the 6 quarks, their force carriers, and all the leptons, they make up all the matter of the universe. So the standard model of particle physics that people have been doing on the side, this is not astronomy now, we're talking about particle physics. Standard model of particle physics says that there are 6 objects called quarks, and 6 leptons, that one for kind of each of the quarks, kind of, sort of, and then 4 particles that carry forces. So let's look at those in each of the particular things. Our first thing we look at are what are called quarks. And quarks are fundamental particles. They make up protons and neutrons, and which in turn make up nuclei of atoms. So in order to make a proton, you got to have 2 up quarks and 1 down quark. Okay, that's kind of weird. And so now we got a neutron, which is 2 down quarks and 1 up quark. So what's the difference between an up and a down quark? Well, the mass is a little different for a down quark, as you can see. And the charge is different because the charge on an up quark is 2/3 of a standard charge. But a down quark is a minus 1/3 charge. So if you have 2 up quarks, that's 4/3 of a charge. And 1 down quark, minus 1/3, gives you a +1 charge. However, if you have 2 down quarks and 1 up, that's 2/3 minus 1/3 minus 1/3, so it's neutral, and there we have it. So we have, so that what we have then is the series of objects that put together, and these are and that's where we build them from. So a proton is made up of 2 up quarks and 1 down quark. And that's kind of a funny thing, and yeah, that's their real names, quarks, whatever. And that comes from, I think, Milton, or I believe. Anyway, the next fundamental particle are electrons. They can't be broken down. Fundamental particles can't be broken into little bits. They are unbreakable bits. They're atomic, just in the Greek sense of atomos, meaning indivisible. So finally we're finding those. So electrons are fundamental particles. They have a charge of -1. They have spin 1/2, and they have a very, very, very light mass compared to even the quark neighbors above. So they carry a negative charge. Next are photons. They're particles of light, and those are my little photon packets I used in my first lecture. And they go back and forth between the protons and the electrons and so forth. And how the charge is transmitted between objects, how electric charge is transmitted, is the transmission of wave packets that are called photons. And so photons are the electromagnetic force. It is the traversing of the photon that is the thing that is the radiative how the electromagnetic force is transmitted. And they're called photons, particles of light. Next, we have neutrinos. Neutrinos arise out, just very simply, out of the interaction with the weak force. I'm not going to go too deep into it, but suffice it to say that the weak nuclear force is in play whenever neutrinos come in or go out. So when a neutron comes along and decays into a proton, as it decays into a proton, one of the down quarks becomes an up quark. Then what happens is, as a result, a neutrino goes away to carry away some of the tiny amount of mass that's associated with it, plus some of the momentum, and an electron pops out in order to take the charge away. Because the neutron was neutral and the proton has a positive charge. So you've got to have a negative charge in order to make because you don't create charge out of nothing. So the neutron becomes a proton and an electron. The charge gets divided up between the two of them to keep it neutral, and a little bit of the mass gets spun away and a little bit of momentum gets spun away in a neutrino. And that interaction that allowed that to occur is called the weak nuclear force. The transmogrification of an up quark to a down quark is the weak nuclear force. All right, so now we have the final thing, which is really kind of strange, which is the strong nuclear force, the gluons. And those strong nuclear force says, that's a really strong charge you got, and those quarks, they are going to push against each other, so I'm going to help you keep together, and that's called a gluon. So the strong nuclear force holds the nuclei together. They hold protons next to protons. They hold quarks together inside of the protons. And so we never see quarks outside of a proton. They're never found free. They're either found in pairs or trios. And so when they're in threes, they're called hadron or baryonic matter, such as protons and neutrons. And that's where normal matter comes from. They got 3 quarks. So gluons are strong nuclear force particles that allow protons and neutrons, specifically protons, to live together inside of a nucleus of an atom. Otherwise, the electromagnetic force, the photons, with the charge, would push them apart. And they don't get pushed apart because the gluons are stronger. So the strong nuclear force is much more powerful than the electromagnetic force and the weak nuclear force. All right, finally, there's something that gives them all mass. And this is a very recent discovery. It was predicted back in the 70s, but it was discovered as part of the Large Hadron Collider, announced in 2012 and confirmed in 2013, that the Higgs boson is the thing that gives everything mass. So the thing that we call mass is a particle that's responsible for the masses of all other particles. Now I put the photon in there, but then photon's got no mass. But it rides along. It doesn't interact with the Higgs field. So Higgs particles don't really exist on their own, but there's a Higgs field. And that field is the thing that out of which mass arises, which is kind of a weird way of talking about it. But if you whack stuff hard enough, some of that field becomes particularized, and then you can measure it by how it interacts with other things. So the Higgs boson was confirmed by the Large Hadron Collider in 2012 as an existing thing, and that is a subatomic particle that's part of the standard model of particle physics now. And so we have 17 things. I'm just keeping it 16 because I like 4x4 blocks, but I put the Higgs on top just because. Higgs is there. So we've got all these particles, and we fit them together in various and sundry ways. Things that are made with 2 quarks, they're like muons and so on, things like that. There's all sorts of things that are made by 2 quarks. Muons are fundamental leptons. But they all have got some funny names. But you can make things that have 2 quarks, you can make things that have 3 quarks, you can make things that have 5 quarks. There's all sorts of ways you can fit quarks into things. But leptons don't go along with quarks. They're outside of the quark world, so they stay away from that. But quarks they're never found alone in ways that leptons can be found alone. So quarks must be found in the presence of other quarks. And so you never see a lone quark walking around going, I'm sorry, where am I? So quarks are always alone. But basically, you can take all these things and interact them together and fit them together like little Lego blocks and build all the other matter in the universe up from quarks and leptons, and they're held together by the photon, not the photons, but by the bosons, which are the forces that hold them all together. So the red column is the glue, the quarks make up the heavy stuff, and the leptons make up the lighter stuff. And there we have it. That makes up all the matter in the universe, including dark matter. So if we then go back in time, let's go back to our concept. We say today we see nice in galaxies and everything is all spread apart. But if we go way back in time when everything was closer together and hotter and hotter and hotter, long ago at the very, very, very close to the beginning of the Big Bang, we find that we go back to our original equation of the nature of how hot the Big Bang is. We then say go back really close to time equals 0. How close can we dare go to time equals 0? What does that even mean? So if we go back and back and back in time, the universe is hotter and smaller and denser, and at some point we would find that, hey, it's so dense that it's opaque. It's opaque to photons, and we found that at that time, and that's where the cosmic microwave background radiation came from. So let's use this equation again and see what the universe has been doing. But if we keep going farther and farther and farther back, we then find that when about 45,000 years after the Big Bang, radiation dominates the energy density of the universe, meaning photons are much more energetic than all other matter combined. And so at 45,000 years old, before this time, no matter what before this time, there could not possibly be there were no atoms, no matter what. Too hot, it was on the order of about 10,000 Kelvin on order. So there weren't any atoms at all, but there were some nuclei. But it was still not hot enough to actually do anything except have a whole bunch of nuclei running around with a whole bunch of electrons and a whole bunch of photons, with the photons having the dominant share of the energy. All right. And when we think about radiation dominated, we go back farther than that. Light carries almost all of the energy. And so we can keep going farther and farther and farther back in time. And the temperature, because radiation density is high, the temperature then gets hotter and hotter and hotter. It also means the universe is actually contracting. It will be kind of expanding a little bit faster or contracting faster as we go back in time, because the rate at which the universe size scale is going faster because of the different version of the exponential on the bottom of the radiation dominated part. So we're ignoring all the stuff with pluses, and the energy density according to radiation is the dominant energy density. All right, let's go back in time until the temperature is equal to about the center of the sun, which would be 15 million Kelvin. How far back do we have to go to get there? Well, we can go back until the universe is only about 3 minutes old. Well, we have a really good understanding of what's going on in the center of the sun. We understand fusion. We understand the processes of fusion. So this is still classical physics going all the way back. And there's no stars, there's no planets, there's no nothing. There's just a bunch of atomic nuclei and a bunch of electrons and a bunch of photons and dark matter going, what am I doing here? And that's what's happening in that hot cosmos. So it's really simple in a very certain sense. So let's go back when the universe was only 3 minutes old and the temperature was about 15 million Kelvin, so that you can actually have hydrogen fusion into helium. Okay, so let's review it. Go all the way back to our stuff about the sun and the center of the sun and how nuclear fusion worked. Hydrogen was formed as an early thing. So quarks might have formed, and then they became protons. But now you can slap protons together, and if you smack enough protons together, you get some deuterium, and because with the weak nuclear force interacting, because it makes an anti-electron, and there's the thing, and that reacts with an electron, it makes more light, and then then deuterium smacks into another hydrogen nucleus, and that forms light helium, and that's in an energetic state. The nucleus would start off in an energetic state and says, and I got way too much energy, so I'll emit a gamma ray, emit some light, emit some more light, and eventually that will collide with another light helium nucleus and form heavy helium, and that is part of the proton-proton chain. So when two light helium nuclei collide, they end up with a helium nucleus, a normal helium nucleus, and that. So this happens in the sun when it's 15 million Kelvin, and if we go back to when the universe was 3 minutes old, this also presumably was happening then. So if that happened during the universe's time, when it was 3 minutes old, then how much helium can you get out before the universe cools down, before it cools down too much such that you don't get any more helium? So therefore deuterium is a major key observation for the Big Bang. In the earliest times, there was no helium either, because it was too hot for even the nuclei to stay together. So you had bare hydrogen, bare protons, bare neutrons. That's all you had prior to about 3 minutes. And though they were just bouncing around doing stuff, and they couldn't stick. It was too hot for them to stick together as nuclei. It was so hot they could not stick, which is a really interesting thought. But once the universe got to be about 3 minutes old, it had a couple of minutes, it had a minute or so in order to do nuclear fusion, because there was a time when it was too hot before it, and then it was a time after that it was too cool, because the universe, as it expands, cools off. And so how fast can it make that deuterium, and then how fast can the deuterium be eaten up, and maybe there's some leftover deuterium. So as the universe cooled, and it cooled down enough so that it could do fusion, deuterium was formed. Deuterium got eaten really fast because it's easy to do fusion once you can make deuterium. And boom, 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 boom. Therefore, any leftover deuterium we find in the universe must be primordial. If it's out in clouds in space and never has been engaged in nuclear fusion, because it'll get eaten up really fast in fusion. So any deuterium was a product of fusion, and if it's floating out in space, it is primordial, coming from the Big Bang. All right. So when it's really hot, everything vaporizes, falls apart, melts, unbinds, disintegrates, and goes to the simplest, most symmetric arrangement. What does that mean? It means binding energies. We have to think about the binding energies of objects. I kind of talked about it a little bit. But the binding energies of atoms are about 1,000 degrees Kelvin, 1,000 Kelvin. And that's where we get things like the emission nebulae, like the Orion Nebula or the Trifid Nebula or other things like that, or supernova nebula remnants and so forth. Those are atomic transitions of electrons jumping up and down. And so if you give it too much energy, the electron jumps away. Fine. So now let's say we have nuclei of atoms. And those are composed of protons and neutrons. So those things are really tiny objects, but the nuclei themselves will unbind if you get them to a temperature that's higher than 10 billion degrees, because the light is too intense, as well as the kinetic collisions between them are so intense that they whack. But mostly it's the light. And remember, it's energy dominated by light, so the light, there's a lot more light than there are atoms, and the nuclei of atoms then plays the biggest. It will be unbound because there's too much light in order to keep them together. And if we go back if we get higher and higher temperatures, quarks then become free because the temperatures are too high at about 10 trillion degrees for them to be bound together. So if you get it hotter again, about 1,000 times hotter than 10 billion degrees, then protons themselves will fall apart into their constituent quarks. That's what we mean by the binding temperature. So the hotter it is, the more it melts, right? So then we can work back and say, okay, we can think temperature, go back in time, gets hotter, maybe things melt, and then we can say, oh, then run it forward in time, things go from melted state to bound together state. That's what we're going to do. So the cosmic timeline then says, start hot, go forward. and everything bound, and then things fall into place and bind together. That's what we're going to do. All right. So in the first microsecond, we had what we would call quark soup. So inside, I'm not even talking about that, up to the first microsecond, I'm gonna do a lot of hand waving here. So here's my first hand wave. I'm going to only start with the first microsecond. And in the first microsecond, I'm going to hopefully get to the other stuff later. And we'll get to that, I hope, later in a later message, which of course we will, because we've got to talk about inflationary epoch, which is way before this. But prior to the first microsecond, the temperature well exceeded 10 trillion Kelvin. That means that quarks were free. And quarks not only were free, they were the energy of the light was so great that two photons could interact and create quark-antiquark pairs. They could also create electron-anti-electron pairs. So there was an absolute balance between up quarks and anti-up quarks and down quarks and anti-down quarks, which I've made my anti things black and my normal ones with a white background. Isn't that nice? And so when they collide together, they have a little bip, an explosion, and then that turns into light, and sometimes the photons smack together and they turn into quarks and antiquark pairs. So there was a balance between the light and the quarks and the light and the electrons. And so up to that moment, it was all in symmetry. A photon couldn't go far without hitting another photon and turning into a pair of quarks. A pair of quarks couldn't go far. A quark and an antiquark couldn't go far before they smacked together and turned into light. So antiquark-quark pairs would collide and form light, and light would collide together and form quark-antiquark or electron-anti-electron pairs. So there were like antiparticle-particle pairs being created in amazing abundance, and it was all one thing, basically, because it was like, hey, you got some light, you got some quarks, you got some up-down quarks, and you got some anti-quarks and some anti-electrons and electrons. Very hot, too hot for anything else to exist. Universe expands, cools, and then it freezes out. After 1 microsecond, the temperature cooled, which means that those quark-antiquark equilibrium reactions stop. Now that's done. But the quarks then bind together. So there's a total balance between the quarks and the antiquarks. However, somehow, and it's not understood very well, it's incredibly poorly understood, that somehow there was a tiny imbalance between quarks and antiquarks. And so the remaining quarks bound together into the hadrons, mostly particles. Hadrons are things with 3 quarks. And that becomes protons and neutrons. So basically the quarks join together and say, whoop, okay, now it's cool enough for us to become protons and neutrons, and now they're bound together for all eternity in the future. Up until that moment, there was a balance between those particle-antiparticle pairs and photon pairs. And then all of a sudden there were no free quarks. And we then had, that is where the total number of matter type things, protons, neutrons, and dark matter, all arose at that moment, and then from that moment, the total number of photons was fixed in the universe, and the total number of protons and neutrons was fixed in the universe, as well as electrons and dark matter, which I'm leaving out for the moment. All right. At this point, then, about a very short period by our standards, but a long period by its standards, 1/100th of a second, the temperature finally dropped to 100 billion Kelvin, which is really kind of, still pretty hot. And then the quark-antiquark pair, the protons then decouple from the photons, meaning before that, it was still so hot that the protons and neutrons and electrons bounced against the photons, and they all had the same temperature. So they existed as free particles, meaning they just bounced around and they said, I'm so hot, I'm going to keep with you. But at some point, they cooled off enough, the nucleons froze out to their own temperature profile, their own thermal profile. And the only thing that could react with them fast are the electrons. because the electrons are less massive, and so they can interact with the photons, and so impart energy to a photon and take energy from a photon very, very, very easily. And that's because the ability of an electron to scatter off of a photon is much easier at that point. So then, the weak nuclear force, though, says that the neutrinos interact with nucleons, so neutrinos stay interacting with them. But here's the funny thing, is that neutrinos interact with neutrons. And so the weak nuclear force is still operating to make a balance between the protons and the neutrons at this time. And so there is a balance between the weak nuclear force, the protons, and the neutrons. So we have an equal number of each at this point. So we've got an equal number, and it's still too hot for them to do anything. Finally, neutrinos at 1 second, the weather cools down to below 10 billion Kelvin. And now the neutrinos then say, and I'm going to just do my own thing because I'll stay hotter than the matter in the matter. So they're basically doing their own thing from radiation and normal matter. Radiation still stays pretty hot. Matter is cooler. Neutrinos stay between them, and then they can stream out because now they say, well, I think I'm done scattering off of everybody, and we're done. So since now neutrinos are scattering and they're no longer interacting with protons and neutrons, free neutrons now start to decay. And as free neutrons start to decay, they live only about 11 minutes. So the race is now on to eat the remaining neutrons before they decay into protons and more neutrinos. They decay quickly, and that's what's going to be happening. After they decay, we have about when that is done in less than 11 minutes, we're very, very, very soon to be done with all the neutrons. And after a minute or so, we're left with 1 neutron for every 5 protons. They decay quickly, and that's what we end with in about a minute or so. So, at 3 minutes old, the universe had finally decreased to about 1 billion degrees. That means we are left to beginning of fusion may occur, or tens of millions of degrees. So now we can start the fusion. Fusion of protons now may occur, meaning it's cool enough for them to stick. And it's cool enough for them to stick, but still hot enough for them to do fusion. And the race is on because the temperature's dropping and their energies are dropping. So deuterium forms rapidly, helium forms rapidly, and inside of the 3 minutes, there's a race between gobbling up the neutrons by the deuterium. The deuterium then gets quickly gobbled up by other fusion by hitting other free protons that forms light helium, which then forms more helium itself, and we're done at the end. At the ending, we end up with about 75% hydrogen and about 25% helium. Now the deuterium is easily burned up in this fusion reaction, so there's tiny amounts left. There's also really tiny amounts of light helium left over, extraordinarily small amounts of lithium and beryllium, and almost no boron, but nothing else. Nothing bigger than boron. Nothing bigger than that in the entire chemical element table. This is what was made in the Big Bang. Helium and hydrogen. 75% hydrogen, 25% helium, and tiny, tiny amounts of the other 5 things that we see there. So, if we look out deep into the universe and look for the influence of, say, hydrogen, because hydrogen is the most prevalent, and traces of that hydrogen will be deuterium. If we can look for hydrogen clouds and find deuterium evidence in them, we will find the evidence for primordial nucleosynthesis when the universe was only about 3 minutes old. And that time is way, 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 way back there when the universe was about 3 minutes old, and deuterium and helium were formed about when it was about 1 billion Kelvin. And so we go way out. And so let's look at the beginning. Here's my hand wavy stuff. I'm going to present this in a new way to present it. The beginning, it was all compact. Less than a second, everything was here. And now, boom, we expand the universe. And the universe expands. At 1 second old, it was 10 billion kelvins, too hot for nuclei to exist. There were about 1 neutron for every 5 protons. And so in my little diagram here, the squiggle lines are photons. And then the little tiny blue things, those are Those are my electrons. The red things are my protons, and the gray things are my neutrons. So you can kind of see that there's about, I actually did this. This took a long time to actually do this sequence, so I'm kind of proud of it. So we got a little cartoon going on here. I got 5 protons with the 5 red dots for every 1 gray dot, and there's approximately 1 blue dot for every red dot to represent the electrons, because they're roughly in balance. Now the photons are energetic enough to keep everybody apart. Eventually, though, it cools off in about 2 minutes. The temperature drops to 1 billion degrees. Neutrons immediately fuse into the deuterium nuclei, and that's where we see them bound together. The photons have been stretched just a wee bit, and so we've got photons that are still energetic enough in order to keep people separated. Nothing to see here, but that results in about 1 deuterium atom for every 4 protons. So they get absorbed rapidly in this process. Basically, all the neutrons get either decay or become deuterium, and that's what's happened by 2 minutes old. Now, by about 4 minutes old, the deuterium fuses to form helium nuclei. There's a tiny amount of helium-3 and very, very, very lithium, beryllium, and boron in tiny amounts. So by the time the universe was 4 minutes old, it had cooled off, no more fusion had occurred, the light cannot rip it apart, and that left only tiny amounts of trace deuterium, and the trace deuterium is shown all throughout here as the little couples. So in this part of the cartoon, we have helium nuclei, helium-4 nuclei, which are 2 red dots and 2 gray dots. That's a normal helium nucleus. The red dots are protons. We've got a deuterium nucleus, which is 1 red dot and 1 gray dot on top of each other. That's a nucleus. And we got some protons in the red nuclei. They didn't participate in any of the fun, so darn it, they got left behind. And then you have electrons, which are the blue dots, and the light, which is the green little arrows. So this is the situation at the age of the universe of 4 minutes, and this is what the universe was. There were no planets, there were no stars, there were no people, there were no structures bigger than a nucleus of an atom. That's what it was. And so as time goes on, just after 4.5 minutes, things were locked in place. Predictions from the nucleosynthesis using our arguments from knowing nucleosynthesis from stars and from nuclear reactions and nuclear physics, we predict that there would be between 20 and 26% with the ratio of deuterium to hydrogen being approximately 1% of 1%, up to about 10%. So it's a pretty big range. And the actual observations show it's roughly about 22 to 25%, the ratio of helium-4 to hydrogen. So this is really good. So there's basically 4 hydrogen nuclei for 1 helium nucleus. That's what that observation shows. That is the prediction from the modeling, and the observations match the predictions. In fact, the deuterium-hydrogen observations are much tighter than the predictions, which is really interesting. The predictions can't really give a fantastic prediction for what the deuterium to hydrogen ratio should be, but the observations are even tighter than what the predictions are. All right, so now we go back, and days and days and days and weeks happen. After that's done, the universe stayed a lot hotter than 3,000 Kelvin. So this was the situation for a very long time, up until about 200,000 or 300,000 years after the Big Bang. So from about 3 minutes of age up until the universe was about 360,000 years old, it was a fog of mostly protons and electrons with a smattering of helium nuclei and a smattering of deuterium. And it was a fog where the photons bounced back and forth, scattering off the electrons off and go, and then the electrons would drag on the other nuclei to keep them all at the same temperature. So the electrons were at the same temperature as the photons, and the photons kept cooling because of the expansion of the universe, so the entire system cooled and cooled and cooled all at once because they were all scattering off of each other. And eventually, at some point, we had the epoch of combination or recombination, that now the electrons bound to the nuclei to become atoms. So now the electrons finally said, and it's cool enough for me to make an atom, thank you very much. And once they did that, the photons could stream freely because now they didn't have enough energy to ionize the electrons, and this is this time of the source of the cosmic microwave background. All those photons came from the time of the universe when the universe was much, much younger, and they were a balance of, they come from an imbalance of the photons to quarks, way back when the universe was a microsecond old. And now then, a much longer time, the cosmic microwave background gets stretched and stretched and stretched to much, much longer wavelengths. And now we see, instead of it being 3,000 Kelvin, which would have been the black body at the time of recombination, now it's a temperature of 3 Kelvin black body, and it has not interacted with anything since then. And so these atoms then, from a long time later, eventually became stars and planets and galaxies, and they fell together by gravity and so forth and so on. The end of the tally, after all of it was done at the end of nucleosynthesis, there was one helium atom for every 4 hydrogen atoms, and one leftover deuterium particle down in the lower right for every 100 hydrogen atoms. So what I did is I put 100 hydrogen atoms on this little diagram, and a bunch of those. But because of the imbalance of quarks and antiquarks at the earliest moments of the cosmos, there are over 10 billion photons for every single particle that exists. Every single one. And we're not just talking about, the helium nuclei, we're talking every single particle down to the quarks. So the ratio of, these particles actually at this point, there's 10 billion photons for every one of these normal pieces of normal matter. So photons vastly outnumber the normal of the particles. And so you can see why if they have the energy, then they're going to really have much higher energy density. But they also get stretched faster by the spreading of the cosmos as the universe expands. So the universe would stretch them into the infrared and down into radio. But it doesn't stretch atoms. It only stretches light, which has an actual length associated with it. So that's where we ended up with at nucleosynthesis. And this is a key prediction of the Big Bang. And this key prediction is something that is observationally testable. And the key reactions are not many. We can form hydrogen and way down the lower left is the beginning ones, where we have hydrogen in balance with neutrons, or protons with neutrons, and they can form deuterium. They can form heavy hydrogen, really heavy hydrogen, or light helium, and then form helium. And then there's really, 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 really small numbers that go up from the helium reaction. Though everything above helium-4 is extraordinarily rare, but yet the tiny fractions of them that may have occurred, especially the step to boron, were also key predictions. So what this is, it illustrates the only chain reactions that can occur inside the circle, inside the red ellipse, that can occur in the Big Bang. We didn't create anything more than that, and the vast majority of it was just the simple little group in the lower left. All right, this leads to amazing predictions. And what you can say is, what in the lower, on this graph was provided by, the abundance graph was provided by Stegman et al. And this comes from the NASA WMAP science team. So you can go look, you can find it there. And for various densities of normal matter, counts of normal matter relative to photons, where it's very underdense on the left and very overdense on the right. And then you can say, what are the element abundances that get predicted by the relative abundance of photons to normal matter as a result of normal nucleosynthesis? And where the photon abundance comes from, remember, it comes from the quark-antiquark imbalance in the early cosmos. So if we measure the density of matter compared to photons, and what that means is that how much normal matter is there in the cosmos, how much dark matter is there in the cosmos, and what is the energy density of photons in the cosmos. And that's exactly what the cosmic microwave background measures by measuring the frequency, the temperature fluctuations, and that's exactly what it measures. So the WMAP team pinned it down to the width of that red line, which is amazing. The width of the red line is the prediction, is the WMAP observation, is what they observed. And so that pins down what the relative elementary abundances should be of all the helium. And so the WMAP observations will actually match what is seen in the sky with the helium abundance and the deuterium abundance. So the WMAP observation said, well, this is what we've got for the red line. The red line is the WMAP observation, the relative abundance of matter to photons. And the green curves are what you get by nucleosynthesis experiment, or by nucleosynthesis predictions by physics. And so then what you do is you go out into the universe and look to see if your theory, the green, blue, green, yellow lines, where they intersect the WMAP observations inside those little circles, does that actually match what is predicted? And if it doesn't, then you've got a problem with your theory. You don't have a problem with your observation, you'll have a problem with your theory. Funny thing is, though, the theory matches the observation. So the observation that needs to be matched, meaning the abundance of helium and the abundance of deuterium, is what is seen. So that's what's amazing, is that the ordinary matter has been predicted to have a certain amount by nucleosynthesis. Then what's done is said, okay, given that the universe had this amount of stuff, do we think we understand nuclear fusion? If we think we do, then we can predict the total amount of helium to hydrogen ratio. That gives us the total amount of normal matter, roughly, in the universe, and that also, and the cosmic microwave background is the dominant reservoir of photons in the universe. In fact, the cosmic microwave background has more photons in it than all the stars in the universe combined. So we say, how many photons are there compared to normal matter? And all of it falls inside the little circles that we see here. The actual observations by checking how much deuterium there is, checking where it is, actually falls exactly where it's predicted, which is astonishing. So how you actually check that is to say, hey, we got this quasar thing. Remember we talked about quasars a while back? They got these really, 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 really bright quasars. And quasars are extraordinarily bright objects from deep, deep, deep in the past. And so their light had to have passed through enormous numbers of clouds of hydrogen on its way to us as it traversed from the ancient times, when maybe for 5 to 10 billion years of traveling. So as it does so, it emitted huge amounts of ultraviolet light. That ultraviolet light can be absorbed by hydrogen. As it gets absorbed by the hydrogen, some of that hydrogen is deuterium. And so you make a model of the relative abundance of hydrogen and deuterium and see if you can match the forest of lines that you get in a quasar. And guess what? They match, which is astonishing. So the prediction, what you need to do in order to make a model of the hydrogen and deuterium abundances matches what is observed by the cosmic microwave background observations that are predicted by primordial nucleosynthesis in the first 3 minutes. So globular clusters contain the most ancient stars. They do not have anything less than 25% helium. All of the helium that is seen in all the most ancient stars of globular clusters, that comes from the Big Bang. That comes from the first 3 minutes of the universe's existence. So after the epoch of recombination, at 300,000 years or 360,000 years, it drops, and that is where the cosmic background radiation comes from. And we see then that the cosmic microwave background was incredibly important. It has predictions that give us information about the cosmic background radiation itself, encodes the information about the relative abundance of matter to light. The amount of matter to light was fixed by the cosmic primordial nucleosynthesis. So we go way back in time and we say the physics of stars, the nuclear physics of stars says when the universe had this temperature, it made helium. When it made helium, it only had a little bit of time to do it before it cooled off. How much could be made inside that time, given that the temperature was dictated by just the light, not by the matter, but by the light? The light then said, oh, I'm cooling off now, so now you can't do this anymore, so everybody's going to have to stop. So nucleosynthesis could only occur for just for a minute or so, a minute and a half, or 2 minutes, from minute 1 to minute 4.5. And then that was fixed, and it was observed in the relative abundance of matter versus light in the cosmic background radiation. So what's interesting is after the epoch of recombination, there were no stars. For a long time, there were no stars. It's just gas cooling off and cooling off and cooling off. And hydrogen and helium are neutral, so they don't glow. And eventually, the universe was opaque to ultraviolet, and that's where the Lyman forest alpha lines that we see in the quasar lines really come from. And then matter was really falling together because there's nothing to do but, fall together under gravity. And so the matter density really drops very, very quickly. And in fact, material becomes stars really fast, becomes quasars. It starts to organize itself rapidly. And then about 300 million years after the Big Bang, you get galaxies. Galaxies start to appear between, say, 300 million years up to about 700 million years. That's the era of the creation of galaxies. And the cosmic microwave background has dropped after about 1 billion years to 30 Kelvin. And stars had formed, ending the dark ages, and those things then reionized the primordial interstellar hydrogen. And that reionization epoch is also seen in the cosmic microwave background because the electrons get hopped up, and that can affect the cosmic microwave background too. So the first quasars formed, the first metals are formed by the first supernovae, and then we get our first generation of population 1 type stars, and then population 1 are the young stars, population 2, and the most ancient ones would be the population 3 stars, which would be being formed during this time. The major piece of evidence we have is the 2010 discovery of one little galaxy, which light comes to us from 480 million years after the Big Bang. And it goes on till today. Not nucleosynthesis, but the universe expanded until the universe was about 2.7 Kelvin, 2.75 Kelvin today. We can sum this all up. So we have really fantastic evidence for what we call the Big Bang. The Big Bang is a story of how the universe grew. The universe expands. Hubble's law shows that the universe expands. Isotropy and homogeneity are consistent with the cosmological principle. We're not at the center of the universe. That's why everything's not expanding away from us. The universe is expanding from all points at the same time, and that's the cosmological principle, and Hubble's law shows that. And the age of the universe is consistent with the most ancient, oldest stars. Primordial nucleosynthesis was predicted back in the 1940s when people were doing the initial test for the atom bomb with the Manhattan Project. And they said, well, what would happen if the universe were a star? And they made some predictions, and that prediction led to the idea that there would be nucleosynthesis that then would have made a background light profile that could be seen today, and that background light profile was the observation of nucleosynthesis. So primordial nucleosynthesis makes hydrogen and helium. It actually takes hydrogen, forms deuterium and helium, and those elementary abundance ratios are determined at the time of nucleosynthesis. That also determines what light was and how hot the light was, and that prediction of nucleosynthesis that started from the 40s was then found in 1960s by Penzias and Wilson and refined with greater ease with the COBE, WMAP, and Planck satellites to show that the cosmic microwave background really truly exists. This is amazing empirical confirmation, meaning actual evidence that really exists, that can be taken by other people with money and time, if you wish, that says that the universe began in some extraordinarily hot, dense state 13.8 billion years ago. And this is such settled science that we actually think it really happened. If it didn't happen, if the Big Bang, as I just described it in the last few lectures, did not happen, then something almost identical to it did. So really, the universe is 13.8 billion years. I don't care what creationists say. They're kind of dumb. But hey, we can, how can I edit that out? I can't. And I'll just leave it there. So the Big Bang really actually did happen. And these are the major empirical evidences that say it did. And there's some review questions for you to go over because, what the heck. But that's what we're really talking about is the Big Bang and its major piece of evidence, which is the expansion of the universe, primordial nucleosynthesis, and cosmic background radiation. Finally, we're going to be talking about, we'll look at the earliest aspects of the universe because there's some problems with this elementary model, which we call the standard hot Big Bang model. And so there's some extensions to the Big Bang model, which are incredibly important that deal with the earliest epochs of cosmic time. But this model is very consistent, starting with a microsecond. We pretty much know the physics all the way up to a microsecond of age. Prior to a microsecond, things are a little weird. Things are very weird. We really have a lot of stuff to talk about there. And we have other things we'll talk about with respect to the evolution and formation of galaxies and the formation and growth of cosmic structure with time. So we'll see you next time. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're continuing on our quest to understand the nature of Big Bang cosmology. We've gone through the nature of what homogeneity and isotropy are, which balance the concepts of what we can expect across the cosmos. Then we went and looked at the redshift of the universe and how it's expanding with time. We've even seen how the cosmic microwave background informs us about the nature of what the universe was like when it was 300,000 years old. And Big Bang nucleosynthesis shows us where the helium all came from in the early cosmos when the universe was only 3 minutes old. However, since all that time, the universe gets older from the beginning, and gravity works on everything that's inside the cosmos. It pulls things together and makes them clump and form groups, and therefore changes how galaxies appear as they look through time. And so that's what we're going to talk about, is the formation of structure, large-scale structure in the cosmos as a result of Big Bang cosmology, the last pillar of Big Bang cosmology. Well, first, we see that this particular cluster, the Virgo cluster, is one of the closer clusters of galaxies. It's rather massive. It's about 67 million light years away and composed of a few thousand galaxies with a couple of supermassive giant ellipticals in it and numbers of other galaxies. It's the largest group of galaxies in our neighborhood, and we used to be called the Virgo supercluster of galaxies upon which this was centered. Other clusters of galaxies are prominent, such as Abell 2305, and this is a Northern Hemisphere galaxy cluster. We can see there's lots of elliptical galaxies and a couple of supermassive giant ellipticals in them. And we see that matter is condensed together to form these structures of clusters and groups. And here's a no more distant galaxy cluster, much more distant, Abell 2352, and we see that there's lots of little galaxies way in the distance that look very, very, very faint and very tiny, but you can definitely see them clustered together. Now, if we then look more locally, we see what's called the Laniakea supercluster, and the Laniakea supercluster encompasses many, many, many of the local clusters of galaxies around us, centered roughly on the local group. There's also the Virgo cluster, as well as other clusters of galaxies that make up this supercluster of galaxies, where there's roughly about 100,000 of these things stretched out almost over approximately 500 million light years. And there's approximately 10 to the 15th solar masses. There are 4 subparts. Each of them were considered separate subclusters, but the Laniakea supercluster has been shown to be gravitationally bound. And so this is a large, large cluster that is bound gravitationally. So how do we know that things like this, that are this large, are bound gravitationally, especially with masses of 10 to the 15th solar masses? Well, that's an open question. So our next question is, we can then say, well, looking at the centers of these galaxy clusters, say the Virgo cluster or any of these others, like the ones we just saw before. And if we look in X-ray light, we see that there's a huge amount of hot gas dominating the starlight. In fact, there's much more of hot gas surrounding these inside the dense clusters than there are actually stars or starlight. So we only see about 1% of the mass of the galaxy when we're looking in visible light, because vast majority of it is this hot intra-cluster gas. If we look at some of these groups, we see that some of them can be on like the cluster 7047. These various clusters show that there are giant ellipticals in the center of them, surrounded by this hot gas. And there's lots of little globular clusters as well, at globulars, which would be barely visible in this. But all the spherical objects aren't globular clusters, but separate galaxies that are clustered together. And so where does this hot gas come from? How does that appear? And here's another view of it. This is a view of galaxy cluster Abell S740, and it's about 450 million light years away. These things are incredibly distant. They're on the order of hundreds of millions or tens of millions of light years away. Not tens, hundreds of millions of light years away. And the center of it is dominated by a massive, giant elliptical galaxy that has maybe 100 billion stars in it. But what we see more importantly is this diffuse halo, which the diffuse halo is actually the X-ray bound cluster is the diffuse halo of X-ray emitting light that it surrounds it. It also tries to map the dark matter as well. So let's talk a little bit more about the nature of dark matter in the universe, because there's a lot of it. Most of the normal type matter is actually dark matter, and it's elucidated not necessarily by this head-tail radio galaxy, but that's usually intercluster gas, which doesn't necessarily push back against it, but that's the evidence of the hot intercluster gas from, say, an active galactic nucleus that's jetting stuff out the sides. So there's a large amount of dark matter that we saw previously, where dark matter makes up much more than like 90% of all the normal matter in the cosmos is dark matter, and we still do not know what that stuff is. Okay, so the next thing we can do is we can say, well, if we probe the universe on large scales, we can actually map this intercluster gas, because quasars are incredibly luminous. Quasars, remember, are active galactic nuclei that can be up to 10 or 100 trillion times the luminosity of the sun, all coming from something incredibly small, only a few tens of astronomical units in size. And this particular one, which is 3C273, is about 5 billion light years away. And it's incredibly bright. We see this jet of material coming off the side from the active galactic nucleus. However, we can map the intercluster medium, or the medium of gas between us and it, by looking at the spectrum. So if we take the spectrum of, say, 3C273, which has a redshift of 0.158, we see it has a bright emission line at Lyman alpha, which is hydrogen emission. That's due to the hot gas that's falling into that supermassive black hole in the center. And we also see some absorption features along the way. However, if we look at a much higher redshift object, something at a redshift of 3.62, this quasar 1422 plus 2309, which is kind of designated by its location in the sky, we see roughly the same shape to the spectrum, except it's got all these absorption lines at specific wavelengths. And so we call this the Lyman alpha absorption line forest, or the Lyman alpha forest. And this is a result of intervening gas clouds between the quasar and us at different redshifts. So it absorbs the ultraviolet light at that specific wavelength of Lyman alpha, which is the transition in hydrogen between the ground state and the first excited state. That's where that comes from. And so this is a spectrum from M. Rausch et al. They're looking at high resolution quasars in their study. In any event, this Lyman alpha forest is characteristic of the quasar light passing through these clouds intervening. So there's many clouds in between them, And those gas clouds are because of the distribution of hot hydrogen gas that is all throughout the cosmos in these clumps and bumps along the way that absorbs the light. And so we can then say, well, how does that affect the production of the structure? And we look then see and say, well, we've got these enormous structures, and here's from the 2DF Galaxy Redshift survey. We can see these filamentary and loops and sheet type structures with large voids. And so there must be these enormous gas clouds that permeate all of these filaments, where there's nothing in the void-like structures, but there's sheets and walls and filaments, and that's where the gas clouds are, and that's also probably where most of the dark matter is too. So we can map that dark matter distribution by looking at the path of light as it's being bent by the light coming from distant galaxy clusters as it passes through, say, like some distant far galaxy. As the light passes through a foreground galaxy cluster, the light's path gets changed. Remember, general relativity says that the shape of spacetime is made by the curvature of spacetime is made by mass. And so light then follows the shortest path, which is a curved light. But to us, it would look curved, but to light, it's the straightest possible path. And that curvature in spacetime is due to the incredible mass of a galaxy cluster, which might be 10 to the 15th solar masses. And as light from distant background galaxies passes through, it is lensed and distorted. And we can see that in this image of galaxy cluster Abell 2218 lensing background galaxies. And we see a phenomenon of strong gravitational lensing. And this is a Hubble Space Telescope imaging. We see lots and lots of gravitational lenses throughout this thing. We see these arcs and bendings of light that come from background galaxies. And so the galaxies act like some crazy lens, which then distorts the images of the distant background galaxies behind them. And we can see these, there's like in almost to the left-hand side, we see this reddish sort of arc, and we see a bluish sort of arc. And then we see outer thin arcs. And those arcs are what we mean by the distant background galaxies whose light was going in one direction, but because of the mass of the galaxy cluster has redirected the light so that we see it. Otherwise, we wouldn't see it because it's going through the galaxy. It would be going over there, but the light gets bent in its path such that we see it. And basically, we can think of this as galactic astigmatism, because that's exactly how ophthalmologists study astigmatism in the eye. They say, what's the thing that's causing the crazy redirect of the eye? And so they make glasses to affect that. Much more graphic representation of the same thing was done by NASA as part of that public release. And we can see the foreground galaxy cluster, which is a big ball between us and the Earth. And then what we see in the sky is that kind of fuzzy image that's kind of in the background. But the far more distant galaxy is in that wedge behind. And so the light leaves the far more distant galaxy, comes through the galactic cluster, and then bends around. And then we see it as where we think it's coming where the red arrows come from. That's where we see it to come from, because we don't perceive the bending of it. We just see where we see it. And so it got bent and got put into those positions, but it's not actually at that position. In fact, those things are mirror images of the same exact galaxy that are far in the distance. So we see one galaxy, two images, and that two images are both distorted because they pass through the gravitational field of this massive supercluster of galaxies. So where did this mass come from, and how did this all occur such that we can map it? In fact, doing this kind of de-astigmatism allows us to actually map the total mass of the cluster. That's how we know it's like 10 to the 15th solar masses and such forth, because you have to have that much mass in order to make those shapes. Next, we can see that there might be, say, not just like galaxies, but maybe even far more distant quasars. So sometimes people say, well, there's a foreground galaxy in the middle, which is those two spots. But then we see that there's two bright spots on either edge, and those are quasars. And they vary at exactly the same time. Every quasars have variability on the order of a few days or weeks, and they can vary in X-rays on the order of hours. And so if these two objects change and they look like they're very far apart in the sky, the two blobs in the upper left and lower right, they are being gravitationally lensed by the two big galaxies in the center, which is probably a galaxy cluster. And those are just the two brightest objects in the galaxy cluster that we see in invisible light. So the galaxies themselves in the foreground are in the middle, and the quasar is in the background. And in fact, the quasar gets to look a little bit brighter because more light gets to us from these locations because of the lensing, so it concentrates the light. And how we can explain that is sometimes we find four images like around some sort of galaxy. So we got these blue dots. Those four blue dots are the distant background quasar, and the red splotch is the foreground galaxy. So we get the much more distant background quasar that then has its light going around the distant galaxy in the foreground, and as it does so, it redirects the light. And that can be seen here in this particular galaxy area called HEO 4352031, which is a fantastic example of a cross-like gravitational lensing. Those four spots are a single distant quasar, and the galaxy is almost directly in front of it, and it's distorting it and lensing it so that we see four spots around it. And notice this galaxy is itself in the middle of a group of galaxies, but the quasar that is the four spots is far, far, far more distant than all the rest. And this is, of course, a Hubble Space Telescope image that was taken a while back. All right, so where does this mass come from? Where does the gas come from? Where does the structure come from? And how do we know that there's dark matter and all that kind of jazz? All right, so the formation of large-scale structure is interesting because cosmologists and astronomers have known that galaxies can't have formed just from instabilities in normal matter starting from the early cosmos. And this is known because it takes too long for galaxies to fall together. So it was just plain old normal matter, what we see with our eye. If you then say we have 13.8 billion years to create these structures, they do not go fast enough. They can't create the structures we see fast enough. Simulations have been run, computer simulations saying take a whole bunch of dots, see how long it takes for them to fall together, and it takes more than 13 billion years for them to do it. So it can't be the case that there's only normal matter. And so the background radiation before decoupling, meaning at the cosmic microwave background, before that decoupling, radiation kept it in balance. So you have to start the gravitational collapse after the last scattering surface. So from the last scattering surface of the cosmic microwave background to today is all the time you get. And that's certain, and there's a certain smoothness to the cosmic microwave background and a certain lumpiness to the local distribution, and transforming from smooth which is smooth to 1 part in 100,000, as we saw with respect to the cosmic microwave background, to today, which is incredibly lumpy with lots and lots and lots of galaxy clusters and quasars and things like, well, quasars are distant, but very dense galaxy clusters nearby. That's not smooth, and that's not seen in the cosmic microwave background. It's only seen locally. So they must have happened. The problem is that the overall expansion of the universe would have wiped away. So it could only have had 50 or 100 times the density of its surroundings, just normal stuff. So that's not enough to actually do the job. However, the dark matter doesn't care, because remember, dark matter doesn't interact with light in any way. So dark matter could have started forming lumps well before the last scattering surface of the cosmic microwave background, because normal matter like protons and helium nuclei and electrons would certainly feel the light and be thermalized by it. But dark matter doesn't do light, so therefore it can collapse, so it can start clumping a long time before. So here's where we got some kind of good cartoon to kind of show it. The vast majority of the cosmos is dark matter. So in the early epochs of the universe, started from, the universe is 3 minutes old, till when it's 300,000 years old. That's what we're going to talk about here. So in the early universe, maybe when it's 3 minutes old, the normal matter and the dark matter were all kind of smoothly distributed. And then, because dark matter doesn't interact with light, and once the temperature dropped enough, the dark matter could start forming clumps around it. And those clumps would form waves and lumps inside of the dark matter. But the normal matter is not bumpy yet because it's still bound to the light. Once it becomes, so the dark matter can make extraordinarily deep peaks and deep gravitational wells into which the normal matter can then fall. So as time goes on, after a few hundred, say a few thousand years, and then after about a million years or 100,000 years, then you can get these galaxy clusters and lumps that happen much later. So you can create the perturbations in the dark matter and let it run, and then by the time that you get to the cosmic microwave background time, the last scattering surface, then the lumps and bumps in the cosmos can then fall into the hills of the dark matter and form galaxies. So let's kind of see what that looks like in a real good check. So if the universe is 1 second old or a couple minutes old, it's all smooth, mostly dark matter with a little bit of normal matter. And the normal matter then the dark matter starts compressing at about 1,000 years or so. Now, remember, the normal matter has to wait for 300,000 years before it can start playing the game of fall together under gravity, and it does so after about 300,000 years, and then by the time we get to 100 million years, galaxy clusters have formed, and then billions of years later we get lots of stuff going on. So at about 10 to the 8th years, which is 100 million years, we start seeing strong dark matter clumps, and normal galaxies and clusters start to form about a billion years later. So that happens at extraordinarily high redshift, a redshift of about 10 or so. Remember, the redshift of the cosmic microwave background is about 1,000 or so. And so when we look at the nature of when things begin with galaxies, that's redshift 10 or 20 or 100 or so. So that's when those things are happening. Now, structure can be then modeled using computer simulations. And these simulations were performed at this particular one was performed at the National Center of Supercomputing Applications by Andrei Kratsov at the University of Chicago, and one of my thesis advisors, Anatoly Klipin at New Mexico State. So there's a big shout out to one of my thesis advisors who was on my defense committee at New Mexico, Anatoly Klipin, creating a wonderful little simulation that shows us from well before the epoch of reionization at Z roughly about 30, which corresponds to very far back in time, less than 100 million years after the Big Bang, is where this particular simulation begins. And what they're showing is that we're showing filaments, clusters and filaments of cold, dark matter, and with some dark energy in there. Now, the frames show, each frame shows about structures that can go across to about 140 million light years, and so the box goes from redshift 30 to about redshift today, meaning now. And what this means is that we start the universe when it was 1% of its current age. That's pretty long ago, 1% or less than 100 million years old. And the distribution of matter seems to be uniform. And then the seeds fall in really rapidly. The matter falls in together rapidly at that time. Now they grow incredibly large to form filaments and structures. And so the entire box from left to right becomes more and more prominent with time. So these filaments form extraordinarily rapidly. All right, so at some point, the contraction seems to be halted because as we get closer and closer and closer to our time, we deal with we're looking at the co-moving space of the universe as it expands along with. So this box actually is co-moving with the expansion of the universe. So you actually have to kind of think that this box is also expanding at the same time as the material is falling together. So that's a very complex simulation. I'll place that web link online for you to see. Right, but more recent simulations, such as the Millennium Simulation Project, look at very, very, very large distributions of matter, and it starts in a cubic region with the size of a box. That's 2 billion light years on a side, and this is called the Millennium Run. There were over 10 billion particles in it, and it was used and the supercomputer at Max Planck Society's Supercomputing Center in Garchberg, Germany. It took about a month to run the simulations I'm about to show you, and they applied some really sophisticated viewing techniques to model this of 25 terabytes of stored output. So they've run this enormous simulations, figuring, well, there's some dark matter, there's dark energy, we input this way of gravity behaving, these particles are in this way. And then what they find is that they say we're looking for exactly how things distribute each way. So we see inside of here the redshift start at about 18, not as far back as the previous, but starts at about 200 million years after the Big Bang, and it goes to the present day epoch. So we're looking at something that might be approximately 500, see they use 500 megaparsecs is how big that little line is, but they divide it by h, which is some fraction of 100 compared to the Hubble constant. So 500 megaparsecs divided by h means the size of this thing is about 700 megaparsecs. So that's what that line indicates, about 700 megaparsecs. Anyway, as we let this thing progress through time, we see by redshift of 5, some structures are forming at the sizes of about 500 or 500 megaparsecs, they're beginning. And by redshift of 1, which is when we start seeing quasar activity, actually quasar activity starts earlier, right about redshift 10 or so. But what we see is that by the time it's redshift 1, where most of the quasars have turned off, we have very strong filamentary structure inside of the box. So then by today, we have extraordinarily tight structures, and this maps the dark matter distribution. That's what this is showing. This thing is showing the dark matter distribution throughout the cosmos. So now let's zoom in and zoom in by a factor of 4 and look at it again. We're going to look at that central region again and zoom in by about 4 times bigger and 4 times closer. So again, we see a smooth distribution of matter with some seeds in it, as the galaxies are roughly smoothly distributed at a redshift of 18. And by a redshift of 6, most of the quasars again have turned off, and so we start to see the beginning of the formulation of dark matter lumps into which galaxies can fall. By the time we get to redshift of 1, the dark matter filaments have been very fully created, and there's something bright going on in the center. And by redshift 0, we've got something really tight going on. So let's take a quick look into just that central region as we go for, again, something only about the size scale of the Laniakea supercluster. So this is about the size scale of the Laniakea supercluster, which is really interesting. So by the time we get to today, we've created something that's about the same size as a supercluster. That's really interesting. So other simulations, such as the Eagle simulation, and this was done by Rob Crane and Jim Geach over at Durham University in the UK. And what we're looking at here is the intensity of cosmic gas and dust. And the color indicates the temperature, and red says it's about 100,000 Kelvin. And that's considered warm. And then the white is about 10 to 100 million Kelvin. So this is the evolution of the hot gas inside of the cosmos as it's going. As time evolves, we can see the redshift and the age of the universe in the lower left. And what happens is that as the universe evolves, supernovae are exploding in galaxies, and they heat the gas such that now you have all this intra-cluster super hot gas. And so this simulation is showing us where the super hot intra-cluster gas comes from that we saw in all the Chandra X-ray images. And this comes from the massive formation of galaxies and starburst galaxies, and as the stars blow up, they form this gas that then doesn't cool off. There's no easy way for it to cool off. And this particular simulation is approximately 25 megaparsecs across, and it's a co-moving volume, meaning we're following along with the expansion of the cosmos. So we're actually stretching the box as the universe expands with this particular thing. So it's a 25 megaparsec co-moving volume is what they call it. Now, this particular simulation was run again by Rob Crane at Leiden University and Jim Geach at Hertz University at the UK. All right, but they have other versions of it, and they just say, please credit us. So here's another one of their fantastic simulations. And we're showing now the distribution of cold dark matter. We're going to show a large number of how things move. So cold dark matter is the stuff that doesn't do light. So at the early epochs, there's a whole bunch of cold dark matter that's falling together. And now we zoom in and look at how gas is cooling. So now we're looking specifically at hot gas. It's cooling around some rotating disk at the center of some big dark matter halo. So the dark matter halo is making gas fall into the center that makes a hot rotating disk. And we can see some outflows, some puffy gas as stars explode. And now we end this thing by looking at starlight, and we've basically modeled a Milky Way. And that's what they've done, is by fusing together a bunch of models for stars and gas and dust, they've created a model that actually can create something that's very similar to what we see in the Milky Way and the local cosmos. And that's the idea with these simulations, that's to show how galaxies form, how they grow, how the black holes at the centers of them can grow, and that's their big, big idea. So their goal was to show something that starts about 7 billion years after the Big Bang, and we can see that we formed a disk-like structure, and that's one of the more interesting things about the Eagle simulation. So I'll pop those and you can go check them out on their website, which shows how the dark matter distribution now ends. So galaxies are at the centers of dark matter distributions that once was smooth and then fell together, and that's what that's showing. Next, they have another really fascinating thing where we're looking at an amazing thing. So looking at this large-scale distribution of gas that's colored by temperature. Blue is about 10,000 Kelvin, and red is about 1,000,000 Kelvin. So this is actually showing how the gas evolves, and you can also see stars and galaxies inside of this. So it's kind of a mixed thing of all these things. And at the object that we're going to get to at the end, there's a massive, supermassive galaxy cluster that's being formed in the center of this thing. And that's about the mass of the Laniakea supercluster. Again, we're creating supercluster size objects that are in the centers of these things. We can see how gas is being funneled along into the shapes that are being channeled by the dark energy content. So now we can see where the Lyman alpha forest comes from, because here's all the dark, the hot gas that's in between the galaxies, and now we've got a Laniakea supercluster inside. And as time progresses, we then can model the idea of nearby. We can model the idea of how gas forms. Now this also explains why nearby quasars like 3C273 don't have a big Lyman alpha forest, but things at redshift to say 3 or 4 do. Because things that are redshift 3 or 4 have to pass through many of these clouds, but something at smaller redshift only passes through a void because the clouds have been cleared out by this time. Notice in the deep past, before all this structure forms, the clouds are very evenly distributed. And now once you get to the later portion of the simulation, the clouds are confined to these filamentary structures. And deep in the center is something the mass of the Laniakea supercluster. And that's what these simulations try to show. Next, we actually kind of look at their simulation again, and this shows 3 different views of the simulation that we just were flying around in. The left-hand 2 images on top and bottom show the dark matter distribution. The middle, pardon me, the top one shows, the top row shows that if the stars that explode as supernovae don't interact and don't push as much gas out into the cosmos, then the gas can stay put and form galaxies. The bottom row shows that the supernovae that occur in these early galaxies has a big effect, and the gas gets spread out really massively very quickly. And on the far right-hand side is the visible light due to galaxies. So now we see more massive gas. So the visible light is on the far 2 right-hand sides of stars in galaxies. And we can see that we see more galaxies in the top row than the bottom. The bottom row, though, shows that dark matter doesn't really get affected by these supernova explosions, but the visible light component does, and the X-ray component would. So these different simulation runs actually can be used as test models and compare them against observations of, say, X-ray emission by galaxy clusters, as well as the distribution of the Lyman alpha forests in distant quasars. And also you can say, well, how many galaxies do we expect to get out of the lower simulation compared to the upper simulation? And if you get fewer galaxies than observed, such as the bottom row, then that might not be the correct way things are going. But if you get something more similar to today, which might be the top row, then at the end, on the upper right, you say, yeah, the simulation must be in the right track because we're making Milky Ways, and that's what we see. Finally, this is another look at how dark matter evolves with time, and this is again the Eagle simulation Once again, this is about 100 megaparsecs on the side, this particular box. And at the end, this whole box is large enough to contain the mass for 10,000 galaxies like the size of the Milky Way or bigger. So this is basically simulating the formation of a supercluster of galaxies such as Laniakea. So that's what we're getting. So this is an enormous computer simulation that took a month and a half of computing time on the Dirac 2 supercomputer. In fact, it took 4,000 computer cores on a supercomputer to do it for a month and a half with 7 billion particles falling together. So this isn't just some movie that was made up at Skywalker Ranch or something like that. No, this was made by a massive supercomputing facility over in Durham, UK. And that's what the Eagle simulation is, and so you can give those guys over there a big howdy-do, because those are some amazing websites, and I'll post them on my YouTube channel. Finally, we can then take a look at the comparison between what those simulations do and take slices through those simulation results and compare them to what we actually see. And so when this Millennium run, which was something I looked at very early on, was run, it was one of the largest simulations. And it used about 1 billion particles to follow dark matter. And the goal was to see exactly how things formed as things starting from about the size of the small Magellanic Cloud up to extraordinarily large objects like giant elliptical galaxies. And what we find is that these particular galaxy clusters, and there's the real one, there's the data taken by the CF2A, the Center for Astrophysics, that's the Great Wall, there you see it, and the Sloan Digital Sky Survey shows wall-like structures. And those wall-like structures, these can actually be simulated. And so let's go take a look at what they kind of look like. So the Millennium simulation creates those wall-like structures. So you then do statistical analysis on the actual appearance of the simulation versus the appearance of what you see in the sky, and you try to get them to be exactly the same. It's amazing that the Millennium simulation basically creates what we see in the sky. And finally, we can go look at, say, something like the 2D-FGRS survey, which is in the different directions of the sky, and we can see the foamy structure that is there, and then compare that to the Millennium simulation. We see the similar foamy structure that exists there. And this is part of the Millennium run, and it's used looking at a particular kind of cosmology, meaning most of the universe is dark matter, where it's about 75% dark matter and about 25%, they call it 60, 70% dark matter, 75% dark, in that range, and about 25 to 26 or 20% dark matter, 70% dark energy, and about 25% matter and dark matter. So that's called the Lambda CDM benchmark model, and that's what creates these simulations, is that if you have matter, dark matter, and dark energy in the right proportions and let things go and make the simulations, you create what we see in the sky. So where did we get the idea to use 70% and so forth? Because this computing time, you don't want to spin that up. That comes from looking at the formation of large-scale structure can be deemed and dictated by the statistics on the cosmic microwave background. So the ripples and lumps and bumps that are on the order of 1 part in 100,000 on this thing, the temperature differences between the hot red and the cool blue, are 1 part in 100,000. So they're really tiny temperature differences, and that means they're very tiny mass differences. And that means there's tiny, tiny, tiny asymmetries, which then get reflected later. So this is called the last scattering surface, where light was interacting directly with matter, and from this time, when the universe was about 300,000 years old, at this moment, the universe then expands away, and the atoms, the hydrogen, the protons and electrons combine to form hydrogen atoms, and the electrons combine with helium atoms, helium nuclei to form helium atoms, and all of a sudden, the light can stream freely from the cosmic microwave background to us. But as it does so, it passes through a huge amount of material from the cosmic microwave background formation at the last scattering surface until it reaches us. And so as structure forms, we see in this simulation of how structure forms, we take the say the Millennium simulation, and we plow it across, and there we see larger and larger structures forming as time progresses. And this is also the dark matter map, so dark matter simulation, since dark matter is most of the matter in the cosmos, and dark energy is very smooth, so it doesn't actually form lumps. Dark energy doesn't form lumps, dark matter does. And so once we've created a map of the dark matter path through it, the light then traverses through that dark matter path and gets bent in its directions from then to now. And there are slight asymmetries that can be measured on the cosmic microwave background as it does that. So here is the path that the cosmic microwave background photons take as they traverse the cosmos to us and pass through all of the structure that's being formed. In the early parts, after they first become free, the through which they pass has almost no structure. But as they travel more and more and more, before they reach us, they get redirected more and more frequently because of the structure that has formed. So the path gets more and more wiggled, which distorts the appearance of the cosmic microwave background. And since it distorts the cosmic microwave background, you can actually measure that effect. And how you measure that effect is by looking at hot and cold spots on the surface of the cosmic microwave background and analyzing the statistics of how hot and how cold it is at given angular size scales between two patches of the sky with the same size, but different temperatures for different orientations. And as we saw in the previous thing, as these lumps and bumps get changed from the original last scattering surface appearance by the intervening dark matter and normal matter, because sometimes the normal matter interacts just by scattering it through an electron, scatters it off that hot gas. But that actually can be measured statistically, and this is the power spectrum, or the amount of the degree of bumps and lumps or waviness in the cosmic microwave background. And the two arrows that I'm pointing out show that the ratio of these two peaks, and every pair of peaks like that, every pair of peaks, not the first peak, but the second and third, and the fourth and fifth, the ratio of those two peaks, how high they are, and what the amount of what the power is, which is the temperature fluctuation in microkelvin squared, what that amount is, gives you the amount of dark matter in the universe. Because dark matter, as we saw, doesn't slosh as much as normal matter does. So it actually forms these, it just kind of falls together and doesn't bounce around. It just simply falls together. So it increases, so there's this difference that as it falls together, it doesn't recoil as it falls. It simply falls together slowly. Now, the second peak shows how far, but then you got blobs of material, of dark matter, or normal matter actually, so that there's blobs of normal matter, and they kind of rattle around inside of the peaks that we saw earlier on, that are created by the dark matter. So those things rattle around inside there. So sometimes they get close and sometimes they get far. And so the second peak, which is not the tallest peak, but the second peak, shows how far apart the biggest blobs of normal matter got, and that's the angular size scale of about 8/10 of a degree. And the third peak shows how compressed the biggest blobs of matter got, and that is about 3/10 of a degree. So there's a lot on the sky. So we see how that these two measurements show the springiness and movement of big blobs of matter that would eventually become superclusters were moving around in response to the dark matter distribution that we saw making those peaks in that earlier slide. So we can then think of this as like saying, well, okay, the springiness of it is that the normal matter is like a guitar string, and a guitar string vibrates, right, in air, and that's why we hear it being plucked. But if you pluck a guitar string underwater, it dampens rapidly. And so the amount of dampening, it vibrates slower. And the ratio of these two peaks it demonstrates how much dark matter there is. Meaning if one peak is much taller than the other, then they dim out rather rapidly. Or they're very close together in terms of their size scales. And we see, well, the power on one size scale is much less than the other. And then we could use those two measurements to actually give us the total amount of dark matter compared to normal matter. That's what those two peaks show us, in the ratio of the heights of the two peaks. And as a result of that data that was gathered by looking at the cosmic microwave background, the important things were discovered by looking at that. And one of them was that the Hubble constant, or the today's value of the Hubble parameter, is 67 kilometers per second per megaparsec, with an error of about 1 kilometer per second. But the more important thing is that we find that the energy density compared to the critical density for dark energy is about 68.5% of the universe. Roughly 70% of the universe is dark energy. Now, the baryon density and the cold matter dark energy density is basically the rest of it, because by that time, by today, the cosmic microwave background forms practically nothing of the energy density, even though it's lots of photons. Remember, it's gotten redshifted down to microwaves, so it doesn't contribute much. So we've got dark energy, normal matter, which is baryons and the baryonic density, and then cold dark matter, which is density. And if you compare the numbers between how many grams per cubic centimeter the dark matter is compared to the normal baryonic matter, we see it's about 5 to 1. So cold dark matter outnumbers the normal matter by 5 to 1, or there's like 80% dark matter and about 80-90% dark matter energy density compared to about 10 to 20% normal matter. So the other two parameters that can be derived from just that curve alone, with the green fit curve to all the dots, which are the data points. The dots are the data points taken by the Planck probe, and that's where this particular curve comes from. And the green line is the best fit values that give these numbers. So from this, we learn how much dark energy density there is in the universe, as well as the age of the universe is 13.8 billion years. Finally, we can extend that a little bit and find something really fascinating about it to tell us what the total amount of energy in the cosmos is that we know the total amount of normal matter is known to about 1% precision, and dark matter is known to about 1.4% precision, and dark energy is not as well known, to about 3.7 or about 4% precision, but that's really good. And that together, combined with the other data, shows that the total energy density today of the universe is 0.099995 plus or minus 0.034. So that means it's basically flat. So 0.9995 plus or minus 0.034 or minus 34 is consistent with a flat universe. And that's what we gather from that. So we say, oh, it must be a flat universe composed of dark matter, mostly dark matter, dark energy mostly, and then dark matter makes up the rest of the cosmos with a small sliver of normal matter in there. And plugging this stuff back into those simulations and then having the normal matter show and do normal things, we saw that the simulations can create Milky Ways, they can create the structures that we see, they can create the clouds of interstellar gas that we see, that create the Lyman alpha forests, they can create the dark matter distributions that make the galaxy lensing that we saw. So this is an incredible triumph of basically confirming the Big Bang as a concept. So we say that why is it part of the Big Bang? Because if the universe had a birthday, then it had a baby picture, and it had an adolescent picture, and a childhood picture, and it had an adult picture. And so things change with time. If the universe did not have a beginning, then we should be able to look 13 billion light years away, or maybe 20 billion or 100 billion light years away, and see something exactly like the Milky Way. And that concept was called the steady state theory. But the Big Bang says that, well, if you look farther back in time, you don't see that stuff. You only see smooth distributions. You see galaxies in these primordial forms, and that's what we saw in the Deep Galaxy Survey video that I did, is that early galaxies are tiny and misshapen. But now we can actually utilize simulations to actually demonstrate the structure of the galaxies combined with the cosmic microwave background to confirm that we actually have all this back stuff that actually can show combining the cosmic microwave background with computer simulations and what we can learn by that, we can compare that to what we see for distributions, simply where galaxies are in space and time. And that tells us basically that the Big Bang actually did happen. And if it didn't happen, something an awful lot like it did. So if it didn't happen, something really close to it did. And this is one of the more important features, and that's why people love running these simulations, because they look pretty cool. All right, so we'll see you next time as we look at very soon at these odd elements of the cosmos, such as cosmic inflation and what's going to happen to the end of the universe. See you soon. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were looking at the nature of the cosmos, how it grew from such forth, and we elucidated an incredibly important thing, how the Big Bang works in the standard Big Bang model. We looked at the hot Big Bang, we looked at how it expands with time, but now we're going to actually see some important elements to it, meaning what happens in the earliest moments. We know that the universe has been expanding since it expanded yesterday, so it'll expand again tomorrow, which is kind of a tautology, but hey, here we go. What we find is that the earliest moments we have incredible amounts of information about. Without the knowledge of the abundances of chemical elements in distant and ancient stars, we wouldn't really believe it. But there's some problems. So let's actually go take a look and see what they are. And find this kind of shows what we're going to be looking at, which is the cosmic microwave background we've seen. Then we have this weird epoch we can see in this cartoon called the inflationary epoch. We also can see this strange little thing called a quantum gravity era. We'll see what that means in this lecture. All right, so the successes of the standard hot Big Bang model, which was the idea of the primeval fireball of the cosmos, it has a number of major successes, and all of them are observational. The first is that galaxies and quasars and supernovae at redshifts less than about 6 tell us, which means that this is since a billion years after the birth of the cosmos, or the last 12 billion years. They can tell us about the universe at later times. So we really do understand how things evolve, and that time since about a billion years after the Big Bang tells us a lot. And so that's also part of it, is the evolution of the universe since that part. The cosmic microwave background tells us what was happening right around 300 when the universe was about 350,000 years old, and it was a key prediction of the Big Bang at a redshift of about 1100. And so then we also look at the abundances of light elements, such as deuterium and helium, in the intergalactic medium, as well as in the presence of ancient stars. Not deuterium in ancient stars, but definitely intergalactic media that absorbs light at deuterium wavelengths at different redshifts. And so we can get deuterium abundances throughout the cosmos, and the predictions from that are and what we see from that is actually predicted by the Big Bang nucleosynthesis, as we saw from the measurements of the WMAP probe and the Planck probe. And so that gets us to a redshift of about 300 million, and when the universe was only about 3 minutes old. So we actually know pretty much, without getting into general relativity or anything like that, except for the expansion of the universe, and also just some assumptions about the nature of the universe, that it's isotropic and homogeneous, and that it's expanding. If we start from that, that's all we need in order to predict pretty much everything we've seen. So that's classical physics all the way down. And even then we can look at how much, what the primordial gas clouds give us, how much helium and hydrogen are in the cosmos. The ratio of hydrogen to helium tells us what happened at roughly the time of neutron-proton freeze-out, meaning when neutrons and protons were in balance. And that's about when the universe was 1 second old. And that's about a redshift of 4 billion. But the freeze-out time when neutrons and protons were out of balance happened about 1 second. So we pretty much can answer almost every aspect of the cosmos observationally down to about 1 second after the Big Bang, which is an amazing triumph. But that amazing triumph has some problems, and there are 3 problems that occur with the standard hot Big Bang model. The first is called the flatness problem, and it can be stated that the universe is nearly flat today and therefore must have been even flatter in the past. Because gravity works, and since gravity works, it deflattens things. You know, the Earth is kind of lumpy, galaxies are lumpy, galaxy clusters are lumpy. So we're looking at the largest size scales, and on the largest size scales, it's pretty flat. So lumps do not extend to the entire cosmos in terms of size scales. So the universe is nearly flat today on the largest size scales, and even flatter in the past. The horizon problem states that the universe is isotropic and homogeneous today. Wait a second, that's what we've been using as an advantage. Uh-oh, now it's a problem? And so it was even more isotropic and more homogeneous in the past, which is really quite scary. Before we've been looking at that as a bonus, as an intellectual starting point, as a touchstone, and now we're calling it a problem. Finally, there's the monopole problem, which says the universe has no magnetic monopoles. Well, okay, that's a little weird one. Maybe there weren't any to begin with, but we'll just start with it as a concept. So this is something that arises out of particle physics. All right, so here we go. And the first one is we call it the flatness problem. Today, the critical density, or the density of the universe compared to the critical density, is almost equal. The universe is almost perfectly equal to the critical density for the cosmos, meaning bound right between an open and closed universe in terms of geometry. If it is not perfectly flat, it is really close to it. But the universe expands, the universe only expands, and the universe only gets farther and farther away from flatness, as we can see from combining the 2 equations. So we have the equation that governs the Hubble time, which is the upper left equation. Actually, the omega as a function of time on the left, 1 minus that. If it is going to be perfectly flat, that would be equal to 0, so that kappa is 0. So if kappa is not 0, say it is +1 or -1, and it is not a perfectly flat universe, meaning kappa is not by definition 0, but let's just say it's got some tiny amount of curvature. That tiny amount of curvature grows with time, and only grows with time. So there's many ways for it to be curved and only one way for it to be flat. So let's assume for just a moment that it isn't flat, that it's tiny, that it's very, very close to unflat. Maybe it's an open cosmos, maybe it's a closed cosmos. So let's see what happens. So if it's a closed or open, then kappa, that k, is not equal to 0. It's either equal to +1 or -1. C squared is the speed of light squared. R is the radius of curvature of the universe, or the scale factor associated with that radius of curvature. A is the scale factor of the universe, meaning how big the universe and how fast it grows with time. And the Hubble H parameter is how the rate of change of that of the scale factor grows with time. And on the right-hand side in the top right shows the current value for today. So if the current value for today is where omega naught, which is the current density of the universe compared to the critical density, if that's equal to 1, then somehow R naught and H naught combined with the C squared are really small, meaning the radius of curvature must be extraordinarily large, because h naught we know is like 70 or so, 67 kilometers per second per megaparsec. C is a number, which is 300,000 kilometers per second. So R naught has R sub naught, the radius of curvature, or the scale size of the lumpiness of the universe, has to be extraordinarily large in order to compensate for those things. So the middle equation shows how things evolve with time, and if we ignore for now the curvature, curvature contribution, omega sub k, and dark energy contribution in the early universe, and in fact we can eliminate it for now. We can just put that away for just now, and look at times prior to say 6 billion the first say billion years of the universe. Dark energy is a tiny contribution. Curvature wouldn't be that big a contribution, but we know that radiation and matter would be the big things. And so we can eliminate those 2 things out of what constitutes the Hubble parameter and get the equation at the bottom. So if we then say what is the Hubble parameter as a function of the scale factor, we plug that middle equation with the 2 pieces lopped off into the upper left equation, and then just simply take those 2 that are above now and equate them. we find that no matter what, the scale factor grows. Currently, we define the scale factor of today as 1, so A of today is 1. So therefore, A of ago is less than 1 and smaller. So no matter what, that thing grows. So 1 minus omega as a function of time, meaning the scale, the density, energy density of the universe compared to the critical density, that veers away from the critical density as a function of time. So no matter what, it gets bigger. Flatness goes away. And no matter what, it always gets more and more and more lumpy with time. So for today, then we just go take that last equation and say, for it to be 1 today, then as we look back in time, A gets smaller and smaller, gets closer and closer to 0. It's always between 0 and 1. So it's always some tiny fraction of that. So it gets bad. And by how bad, we mean bad. If we go back to the time when radiation and matter had equal amounts of energy density, which is about 50,000 years after the Big Bang, we find that's a redshift, then it has to be, the omega sub t has to be 1 to within 1 part in 10,000. If we then go back to z, which is a redshift of 3750, that means which is when this would be, the scale factor is really tiny, which is like 3/300ths of 1%. So that's really small. So that's roughly 1 in 10,000. If we go back and further in time still, and we go back till the time of nucleosynthesis, when the universe was 3 minutes old, then the difference has to be, then the scale factor now is really small. The universe is incredibly tiny at about 3.6 times 10 to the minus 8th. So it's that much smaller, or 60 trillion times smaller than it is today, which is astonishing. So the scale factor, the universe was more than 1 billion times smaller than it is today, more than 30 billion times smaller than it is today. And therefore, it has to be really smooth at that time, such that as it grew to today, it is still close to 1. If we then go back to the earliest possible time that we can possibly think of, which would be the Planck time, which we'll discuss later, then that would mean about 1 part in 10 to the 60th. So to get some ideas of what we really mean by that, the first thing, radiation matter inequality, it's another way of saying it is that imagine you have 10,000 people. And this is the radiation matter inequality. So everything's the same except one. So it's the old game from Sesame Street, which of these things is not like the others? And imagine you have 10,000 people all go to one place. Maybe there's 10,000 people all going to okay, so they all go to a big concert or something, and there's 10,000 people at the concert. And every one of them is exactly the same height, exactly the same, maybe they're all women, they're all wearing the exact same dress, the exact same dress color, the same hem length, they're all the same height, they all have the same hair, they all have the same everything. Everything's the same, down to their purses, down to the shoes they wear, everything, except one of them is wearing a flower in her hair. And that's the only difference. So that's how rare that would be. It was like, oh, one person's different. The next one, with thermonucleosynthesis, is effectively, now think about it this way, to have it be the same as in 1 in 33 to 3.3 times 10 to the 14th. So now imagine there's 10 billion people on Earth, and they're all exactly alike. And then imagine there's 33,333 Earths, all with 10 billion peoples, all identical, all except one. That's kind of scary. There's 10 billion people, so pretend, so there's roughly 10 billion people on the Earth, and for some reason, some crazy alien comes along and makes everybody exactly alike. And then he does that to 33,000 Earths, 33,333 Earths. Each of those Earths having 10 billion people. So they're pretty busy aliens making everybody exactly alike. But somebody dodges the alikeness ray, 1 out of 33 times 10 to the 14th. So the last part, the Planck time, is even weirder because to have 1 part different in 10 to the 60th is a really strange thought. We can just think that the sun has roughly 10 to the 60th electrons. The sun is a big star. It's made up of a lot of stuff. And it has maybe 10 to the 60th electrons. For it to be perfect to what, let's say, the difference is, take away or add or take away 1 or 2 electrons from the sun. and say, oh, we've noticed that difference. That's the differences we're talking about. Like, take away one electron out of the sun, and the sun is 10 to the 60th electrons. So it's kind of a wild thought. So what does that effect have? The effect is that if the density parameter is not fixed, if it's not really close to 1, and doesn't matter how tiny that difference is, that as time progresses, so the Big Bang is to the lower left of that graph, as time progresses, stuff's going to happen. So you can have an accelerating universe where all of a sudden, oop, I've got less stuff than I need, and all of a sudden the universe accelerates, or it's got more stuff and it closes, and maybe it's a critical density universe and there's only matter in it, or maybe it's an open universe and it is just not just matter, but maybe radiation and dark energy, and we have the other one. So you have all these different paths based on what the universe is made up of. But down at the Big Bang, at the very beginning, they're almost completely identical, except for maybe one electron less or more in the sun worth of difference. And then that, as time goes on, differentiates them between the various paths in the future. So Big Bang is time equals 0 in the lower left, and as time goes on, the tiniest differences that become larger and larger and larger. It's much the same way as thinking about, trying to balance a pencil point on its tip. So if you take a pencil point and balance it on its point, it has to be perfectly balanced. So imagine that you've perfectly balanced a pencil point on its tip and it doesn't fall over for 13.8 billion years. The longest possible time that any reasonable person can make this pencil balance. And you can try this if you get really bored at work, right? Just like I did. So you can try this, and you'll find that it takes the longest it'll stay up is half a second at the last. But imagine you balanced it perfectly, so incredibly perfectly, it still hasn't fallen over after 13.8 billion years. That's the equivalent of the flatness problem. All right. So yeah, that's going to be kind of a tricky one. That's a hard one to do. Okay, so here we go. That's the flatness problem. If it's not, it was flat ago, and if it wasn't flat, it would the end result would be a closed universe. It would collapse on itself, or it would be an open universe and it would accelerate away. So there had to have been really close to flat at the beginning in order for one of those two things not to have happened to give us the universe that we see today. All right, next is the horizon problem. Well, first and foremost, we stated that the universe is homogeneous and isotropic on all the size scales. Apparently, this is a problem because, what the cosmic microwave background map shows is that no matter which way we look in the sky, the universe has the same temperature. Meaning, if you measure the blackbody spectrum of any patch of the sky, it can be characterized by a 3 Kelvin background blackbody. And we got that by saying the following. We assumed the first law of thermodynamics, and when we look back in time, we said, we assumed that the first law of thermodynamics applied, and that the universe was thermalized, meaning that everything in the universe was at the same temperature, and nothing could enter the universe, and nothing could leave the universe, and heat can't come into the universe, and heat can't leave the universe. So everything that's in there, including all the heat and all the energy, is part of the universe from the very, very, very beginning. So if that's the case, then it should all be at the same temperature. If it's all the same temperature, then it all has the same blackbody spectrum, and that was the idea behind the Big Bang. However, this ends up being a problem. Why? Let's look closely. The horizon problem says that, at 2 points across the sky, 2 points completely across the sky, A and B, the light is only getting to us now, which means that in order for A and B to have been in contact, the light is arriving now at where we are from diametrically opposed places in the sky. That's the first time the light has ever had a chance to interact. That's their first chance. Otherwise, we would see something different. So the light took about 15. It's just an old dumb thing. 13.8 billion years to get to us from here, and 13.8 billion years to get to us from there. And we're seeing it first for the first time, just like this. So we see everything from every direction at a 3000 Kelvin gas. That's what we see the temperature being. And each of these patches are just getting to us now. That light is only getting to us now, which means that light has only had the chance to mix, to influence itself, to have that light influence any other particle at that moment. So in direct opposition to each other, they're the same temperature. So how could they do that if they weren't in contact? Because in order for there to be thermal mixing, remember the idea was that they have to be all at the same temperature. In order for everything to be at the same temperature, the light has to be in a dense area where it can't get out. The light can interact with, say, the electrons and protons, and then the protons and electrons can interact with the light, and everything becomes the same temperature, the light and the matter. However, if this is the first time the light is interacting with matter since it left there, then how do these two things across the sky have the same temperature? This is the first time they've had a chance to interact. And it's 13 billion years, 13.8 billion years later? That's a problem. In fact, it's a big problem because this patch is also out of contact, which is, okay, it turns out that those two patches right next to each other on the right-hand side are out of contact. And it gets worse. Every single one of these patches is out of contact. So basically, everything's out of contact. There's almost nothing that is in contact. And if we then get all the way over to here, we look at the cosmic microwave background, then all of these patches on the sky that are about the size of the red dots are out of contact with each other at the time that the cosmic microwave background radiation was formed. So each of these dots, and there are about 200,000 such patches across the sky, because each patch is about a degree in sky. So any patch that's more than 2 degrees away, more than a degree away from something else in the sky on the cosmic microwave background, has never had a chance in the past to actually thermalize with the patch 1 degree away from it in the sky. So therefore, there's 200,000 independent patches in the sky. Whoops. Now that's kind of weird. How do you get 200,000 patches in the sky to have exactly the same temperature when they never had a chance to be in the same context? So it's like, you can basically, another way to look at it is you're all going to a potluck party, and or I liken it this way. Everyone is going to meet at Times Square for New Year's Eve. And so New Year's Eve, Times Square comes along. And then 200,000 people choose to go to Times Square. When do they choose to go to Times Square? They choose to go at noon on December 31st. Let's say nobody is going, nobody's chosen. They've all been given magic tickets, or actually, let's put it this way. Nobody knows that they can go. And all of a sudden, you get a magic ticket that says, you can go. So 200,000 people across the world are chosen at random to go to the Times Square on New Year's Eve. And so they have 12 hours to get there. And so they run. Now imagine that when everybody arrives, they are the same appearance. They're the same height. They're the same sex. They wear the same clothes. They all have the same funny green hat. They all have the same funny everything. Some people, though, are coming from Dubai. Some people are coming from Rio de Janeiro. Some people are coming from Brooklyn. Some people are coming from Helsinki. Some people are coming from Toronto. A lot of people apparently are coming from China, maybe even the hinterlands of China. Some people are coming from India. A lot of people are coming from India. And a few people, of course, coming from Togo, wherever we're coming from. But all of these people, no matter where they come from, are exactly the same appearance, exactly the same clothing, exactly the same height, build, everything, except for one person. They're all the same. That's wild. Actually, there's no difference. There's 200,000 people that arrive in 12 hours without having a chance to talk to each other to figure out what you should wear. Because they didn't tell you what to wear. You said, you can come. So how do they get all the same clothes? How do they get the same bags? How do they get everything? Nobody knows, because there's no way for them to interact inside the time frame from when they got the ticket to when they arrived at Times Square for them to actually know. And that's the horizon problem. There was no time for the light and matter to get to the same temperature before then. All right, next we have what's called the monopole problem, which is a weird one because it's one of the predictions of grand unified theories, is that the universe undergoes some sort of crazy phase transition as it drops below some incredibly high temperature. And that's kind of like freezing water or something like that. So the major phase transition occurred when you have this question mark time at the time roughly equal to 0, and then you have a time when there was like gravity was interacting with gravity, and all the other forces such as the strong, weak, and electromagnetic forces were all one, and then they broke apart. And that break apart then would cause strange things. So that goes from a symmetric state to a non-symmetric state, where the grand unified theories, the strong, weak, and electromagnetic forces were all one, and then they break away from gravity, and that creates a phase transition. And when that does, there will be strange appearances throughout the universe. And it's as though it's kind of like it is a phase transition, and it is a spontaneous loss of symmetry when the temperature is lowered. So just like water, what you have with water is that when it cools down, ice crystals form. And so it goes from being a symmetric thing inside of water, where all the water molecules can be oriented any which way. So that's symmetric. You have no idea which way they are formed. So symmetry has a certain sense of chaos, but it's also and disorder. But yet it also is symmetry, meaning there's no way to tell there's no preferred orientation in a liquid water except for, say, up and down. But if you put the drop out in space, then there's no up or down to water, so there's no preferred orientation. As soon as you cool it, though, ice crystals form. And when the ice crystals form, there are preferred directions along the crystals of the ice, or at least something that shows you a symmetry, that shows you a new asymmetry. And that's what we can see here, is the idea that when ice crystals form, they form and create non-symmetries. Notice how water as a droplet is the same no matter which way you look at the drop. But ice crystals look different no matter from different ways, different viewpoints. So that means they are asymmetric, and water drops are symmetric. Now the other thing we can remember is that as ice crystals form, they actually stay at the same temperature as the water around them. So there is a binding heat that says that must be released in order for it to create the solid known as water. So it can't get any colder until the liquid state of symmetry is lost and becomes asymmetric, and that releases heat going from a state of symmetry to asymmetry. So there's heat involved in this phase transition of organization. So then we can say that the monopole problem says that there would be a lot of magnetic monopoles, meaning strange places. Let's go back a second. So we have points on this. So there are places where the rods intersect, and there are places where the walls intersect of these crystals. And so you can have all sorts of crazy defects inside of ice. So we can make an analogy to say there will be domain walls where big pieces of ice push against each other as they're forming out of water. We can have line-like defects where two walls intersect. And then we can have point-like defects where many of these things intersect into a point. And the point-like defects are what we call the monopoles. So magnetic monopoles, then, are when these point-like defects would occur throughout the cosmos. And this would happen during the phase transition from the theory of everything, or TOE time, to the grand unified theory, or GUT time, when gravity broke away from the other forces. So that would be where the magnetic monopoles would have occurred. Strangely enough, it should have made a heck of a lot of them, like an enormous number of them, like 10 to the 87th of them. So that's because there's a huge amount of energy that would have been created during this phase transition. We do know that as everything breaks up, as asymmetries are broken, it can release an enormous amount of heat when you go from one phase to another. And so that phase transition can release heat in the form of particles. And so the particles can be created out of that heat, out of that energy. So the expected particles are magnetic monopoles, and the idea is that there's 10 to the 87th of them. Assume that this idea is correct, that the forces are all together and that they actually do this thing, then something like the monopole problem is occurring in the standard model of particle physics, but it only happens during the time of the universe, when the universe was 10 to the minus 43 seconds old, till when it was 10 to the minus 36th seconds old. And it goes from a temperature of extraordinarily high, 10 to the 32nd Kelvin, down to 10 to the 28th Kelvin. My goodness, it's cooler, right? It's a cold day as it drops by a factor of 10,000. The total energy per particle goes from 10 to the 16th tera electron volts to 10 to the a trillion tera electron volts. Once it cools off down to about 10 to the 16th Kelvin, and at about a trillionth of a second later, that's when the electroweak and electromagnetic forces break apart from each other and separate from the strong nuclear force. So there's some very strange things that occur in the first between 10 to the minus 43rd seconds and 10 to the minus 36 seconds of the cosmos. And that would be when these strange effects like domain walls or cosmic strings or magnetic monopoles would have formed as a result of the phase transition of the early universe. So let's actually kind of look at what we are. That's a lot of words. Let's see what we meant by that. So the fundamental forces of nature, there are four. And the first one is the electromagnetic force, or the photons. And it's a long-range force because a photon is a particle of light, and it's radiative energy, so it can impart energy from here to there from radiation. And it's incredibly strong compared to gravity because you can levitate things with electromagnetic force, meaning, have you ever seen people pick stuff up with a magnet? Yeah, you can pick up a paper clip with a magnet. So if you can pick up a paper clip, it's very strong compared to gravity, so you can pick it up. The strong nuclear force, which is bound by the gluons, is even stronger than the electromagnetic force because we know that protons can exist inside a nucleus, so that force has to be stronger. But yet it only acts on a very tiny range, 10 to the minus 15th meter. That's the only time range that it works on. The weak nuclear force, though, is not as strong as either of the other two, and its range is even smaller in terms of its interaction. And that's why we think in terms of the neutrino, because the neutrino is still something that is the force carrier for the weak nuclear force of the W's and Z's. And so the neutrino is indicative of the weak nuclear force interaction. So gravity is not shown in here because it's the weakest force of nature, so we only have four forces that accelerate particles that can cause the Newton's F equals ma. So only the strong nuclear force, weak nuclear force, gravity, and electromagnetic force exist in nature, and those are the only things that can provide an F to F equals ma. Everything else that we've ever heard of that makes a force on something is some derivative there too, with the vast majority of them being either gravity or the electromagnetic force. We really don't encounter the strong and weak nuclear force in daily lives at all. But if we go back in time, to a time when the universe was only 10 to the minus 15 seconds old, we get to what's called the electroweak force. The electroweak force is when the photons and the weak nuclear force basically are at high enough energies you can't tell them apart. And this earned a couple people of New York the Nobel Prize for realizing this and dealing with the math and understanding that this is actually true, that they actually they're the manifesting of the same thing, but you have to have extraordinarily high energies and high densities and over short periods of time. And when you actually look at extremely high densities, temperatures above 10 to the 15th Kelvin, then you can't tell the difference between light and the weak nuclear force. They're the same thing, which is a very strange thought that light can be the same thing as those things. It becomes one force, the electroweak force. And that's what we mean by a unification of the forces, is that these two things become the same thing in the same sense that you have, what is the difference between steam and water? Well, at the very boundary between water and steam, at the right temperature and right pressure, there's almost no boundary that molecules can go back and forth between water and steam if the temperature is right and the pressure is right. And they just can go, oh, now I'm steam, and I get close to this area, but now I'm water, but now I'm steam, but now I'm water. So at the boundary area, there's no difference. It doesn't take any energy to go back and forth between them. And that's what we mean by the electroweak force unification. You can still have these two objects, but they actually act as one, meaning steam and water act as one under certain pressure and differences. Same with the electroweak force. Now we can theorize that there is a grand unified theory that says that at some point that the strong nuclear force binds into the electroweak force at much, much, much higher temperatures and higher pressures and higher densities, so that that becomes one force. We left out gravity, though. There's no experimental basis for the grand unified theory yet, but people make up stuff and they try their best. But it's going to be very difficult to actually find these things because it's very hard to isolate a gluon. which is the mediator of the strong nuclear force. So at this point, the grand unified theories are not experimentally verified. They're just a theoretical way of saying, well, they should get balanced as they get closer together at higher temperatures. But then we then say, fine, let's extend that one more time. Gravity itself is thought to unify because all forces, things that make things do forces, it's thought to unify with the grand unified force at even higher energies. That's a pretty big maybe, though, because now you have to have, because there are theories of the grand unified theory concept. There are numbers where you can do the quantum chromodynamics and quantum electrodynamics get you there. But the nature of the grand unified theories don't yet include a quantum theory of gravity. So quantum theory of gravities are not exactly ready for prime time. People posit that there must be something called a graviton, or a particle that is a particle of gravity, which is a very weird concept. So let's just think that that's an odd thought to think what a graviton is, because there are two big camps on what exactly is gravity. General relativity says it's the shape of space-time itself, but particle physicists call it a force that is carried by a particle. So there is some, and so far experiments have only been able to confirm the theory of relativity as the description for space-time. And the attempt to discover space-time quantum foam effects has been made more difficult because the Fermi Gamma Ray Telescope has looked at the arrival times of high energy and low energy gamma rays, which should have felt the effect of quantum foam effects, or tiny bubbly gravity effects over a course of 10 billion year travel across the cosmos, and they don't see it. So gravity as unified with the strong nuclear force, weak nuclear force, and photons into one theory of everything, one force of everything, it's not well known. So there is at this point no quantum theory of gravity, and people are hunting for it because that would be really cool and it would be a big help, but there isn't one yet. So next what we say is that, fine, let's assume that we can get a quantum theory of gravity. So at the Planck epoch, we don't start anything at zero. So we're not going to start our time thinking at zero because we want to do physics, not metaphysics. We can't really say anything meaningful about time equals zero, but we're going to start our moment at 10 to the minus 43rd seconds. And this is right after the Big Bang, time equals zero. Well, 10 to the minus 43rd seconds is effectively time equals zero, but there's a lot of time between 0 and 10 to the minus 43rd. There's 10 to the minus 43rd seconds. A lot of things can happen inside that time, apparently, because a lot of things apparently did, or a lot of nothing. So we would say that at this moment, right at 10 to the minus 43rd seconds, let's say that all the four forces are unified into what we call a single superforce, and you'll find that this is actually something that's talked about in the literature. No matter where you go bounce around, it seems to be it is the current paradigm that there should eventually be a quantum theory of gravity. So all of them would be formed together into one big concept called the Planck epoch. And the Planck epoch is up until 10 to the minus 43rd seconds. So why would we have this concept of 10 to the minus 43rd seconds? Because that's the time when we expect the size of the universe to be about the size of a wave packet of the particles that would have existed at that time. That's a wild thought. And so the Planck time is where we combine, say, h bar, which is characteristic of a Planck of a quantum effect on wave size scales, and g is the Newton's gravitational constant, and c to the fifth power is the speed of light. So g indicates we're talking about the gravitation, and h bar represents we're talking about quantum effects, such as, remember the energy of a photon is h bar times the frequency, gives you the energy of a photon. So if we then say h bar times g over c to the fifth, which is a space-time measurement frequency sort of thing, and then take a square root of that, we get a time. And that time is 5.391 times 10 to the minus 44th seconds. That's the Planck time. And at that time, the wave packet size of the universe, remember we talked about the wave size of electrons and the wave size of photons? Now we can say the wave particle size of the entire universe would be this thing, so the size of the universe would be about the same size as a wave packet inside it. That would be the top Planck time. So how big was the universe at the Planck time? Well, it wasn't very big. So if we take the speed of light, which is the time that it would take for information to travel across that universe, it's not very big. It's about 1.6 times 10 to the minus 35th meters, which is really tiny, called the Planck length. And the Planck length is just simply equal to the speed of light times the Planck time. So nothing can get information across the universe faster than the speed of light when at the Planck time. So the distance that light can travel in a Planck time is 1.6 times 10 to the minus 35th meters. And that would be the size of the universe at that time. All right. At that time, we would call it the grand unification epoch. So at 10 to the minus 43rd seconds, the temperature is a staggering high, 10 to the 32nd Kelvin. And at that moment, that's when the gravity would separate from the superforce. So the end of the Planck era instantiates the grand unification epoch, where gravity then separates away and the strong and electroweak forces are still unified together as the grand unified theories force. So then there are two forces ruling all of physics inside of this very short early universe time, gravity and the grand unified theories. At this time, the universe is just very hot, as you can see by the temperature, and very, very, very dense. And the only thing that exists are quarks, antiquarks, protons, and photons. And they're all in equilibrium, meaning they all have the same temperature. They all have, because they're interacting inside of the universe. And as they are interacting, they get to be the same temperature. And that was key to an earlier concept. However, not long after, at a time of 10 to the minus 35th seconds, or 10 to the 8th Planck times later, the temperature drops to 10 to the 27th Kelvin. The strong force now separates from the grand unified force, which then is the end by the end of this time, from there to there, they have separated out, and the electromagnetic force and the weak forces remains unified. So at the start of the grand unified theory time, you have the separation of gravity from the gut objects, and by the end it has done. There's a rapid separation. That triggers some strange rapid inflation of the cosmos. All right, so then this is what we mean by the inflationary epoch. So the Planck epoch has everything bound together. During the grand unified theory epoch, or the gut epoch, then the gravity separates from the grand unified force to make two forces and some quarks and photons and photons, which are kind of like photons with electroweak photons is probably the best way of thinking about it. And then that's what exists in the universe. During that time, the universe expanded about 10 to the 43rd in size. The size scale A went big, really big. At that time, then, the cosmic microwave background gets smooth, everything gets shoved apart, and we get at the end of that, it stops. So let's see what this is all about. So during the inflationary epoch, there was something that dominated all the other components of the rate of expansion, and that was something like the dark energy component. Curvature, radiation, and normal matter didn't really matter for the energy density of the cosmos. It was just something that pushed the cosmos apart between 10 to the minus 36th and 10 to the minus 34th seconds. That pushed the universe apart so that the scale factor at TF, which is T finished, compared to the scale factor of TI, which is T initial. And that's an exponential expansion. And it's the time times the Hubble time. It gets you about e to the 100 or so, which gets you about 10 to the 43rd times of an expansion. That's an enormous growth rate inside a staggeringly short period of time, and that's wild. Of course, that's much larger than the speed of light. Much, much larger. But space-time itself can expand at the speed of light because it's not a thing. So no thing can go faster than the speed of light, but space itself can because it's not a thing. Remember, we're no longer dealing with quantum gravity anymore. We're just dealing with space-time, and space-time can still expand at that space. And now it's doing its own thing based upon the energy density of the cosmos, which is some crazy energy that's pushing it apart, some inflationary epoch. So when the inflation stops at 10 to the minus 34th seconds. The universe is really cold and really empty, and that's caused by the decay of energy density called the inflationary epoch, and that creates new particles such as quarks and leptons and light. So that's what's created at the end. So it just really empties the heck out of everything. So by that time, 10 to the minus 32nd seconds, until 10 to the minus 12th seconds, which is a still short period of time, but very long for it from its perspective, if you're considering tiny steps. Then the temperature drops rapidly, and the electroweak then force separates into the electromagnetic and weak forces, and now they're all separate. And so all you have in terms of matter at this time are quarks, leptons, meaning like electrons and anti-electrons, such as they are, as well as muons and other objects in that tree. But now you have all four forces. Four normal forces are finally coming into existence: gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force. Notice that we've broken the symmetry from going from one thing that is the same no matter how you look at it to four things which are different depending on their size scales and their strengths. So we have broken the symmetry of the cosmos as it cooled off. So now we can get separate photons. You can get matter and photons, and then all sorts of things can happen from that point. So how does this solve the problems of the early cosmos? So the cosmic inflationary epoch solves the flatness problem by expanding the universe. So imagine we have a balloon, and the ant is on the surface of a balloon, and the balloon might be, say, 10 centimeters in radius. So the ant can easily say, wow, this is a nice little curvy balloon. I can walk all around it and find all sorts of curvinesses and find a little place where people inflated the balloon that I'm walking around on. But now, instead of kicking the ant off, we inflate the balloon extraordinarily rapidly until it's 10 to the 48th meters in size. Well, the ant's never going to see the curvature. The curvature is so incredibly large now that the ant's going to say, this is perfectly flat. Or if it's not flat, it's really close to flat, and I can't measure the curvature of it. So the radius of the balloon now is 10 to the 48th meters. He's never going to see it. So effectively, the inflationary epoch wipes out all curvature, because the curvature now is so big that it's impossible to see inside your little world, which is the square box. It's impossible to see it. All right, so how does that work in terms of the numbers? Well, in terms of the numbers, we have the omega sub t that we saw at the beginning, which is the density compared to the critical density. It grows exponentially with time, and if we compare the final t sub final compared to t sub initial, which is the initial time, we would then pretend that even at the initial time, that there was a strong amount of curvature, really curved, really lumpy, such that the difference between them was about 1. So maybe it was twice as large as that. Maybe the curvature was huge. So it's pretty much the size. Curvature was the size scale of the cosmos. In our ant analogy, the ant could be walking around on the surface of the balloon before it was inflated. It'd be very, very lumpy. So now inflated extraordinarily fast, and that goes up to e to the curvature then drops by a factor of 10 to the 87th. And that's so incredibly large that there's no way that we'll never actually be able to see any curvature. That allows for a lot of things to happen. So the flatness doesn't go away. In fact, as the universe expands for 13 billion years. Why not? Because it's just too big. The curvature is simply so large that there's no way for it to ever catch up. So the tiny, tiny, tiny non-flatnesses that probably exist, that may have existed during the Planck epoch and the Gut epoch, those things may have occurred, but they were smoothed out incredibly rapidly by the inflationary epoch. And they can't grow fast enough. The lumps can't grow fast enough in order to be measured. Even to today, where we find the critical density, the current density compared to the critical, which is omega sub naught, we find that to be equal to the critical density contributed by matter, and the critical density and the density parameter contributed to it by dark energy. The sum of those things is equal to 1, to the best of our ability to measure. Now, it could be that the current best of our ability to measure means that it's 10 to the minus 16th, because the universe has caught up a little bit to the inflationary epoch, which we expect it to have done, as we see here. So in the early universe, before the inflationary epoch, the universe was really tiny, 10 to the minus 35th meters or so. And so everything inside of there can be the same temperature. Then it blows up rapidly. All that tiny thing that's all at the same temperature blows up huge. However, remember, the speed of light is finite and much smaller than the rate at which the universe grew. So light can only get to you from a place that's deeply embedded inside this newly large area. So now it's really big, everything's at the same temperature. There's practically nothing in it, but that's beside the point. So everything's been cooled off, everything's been made to almost temperature of practically zero, and then you get more heating and stuff later. But the universe now becomes all the same temperature, all at the same time. And eventually, the universe's horizon that we see starts to catch up to the boundary of the rate of expansion of the universe. So there's two horizons, right? So this solves the horizon problem. The horizon problem is solved because now everything's the same temperature inside a really big volume, and we just our horizon then grows because of the age of the cosmos. The horizon now we see is about 13 billion light years in every direction, about 14 billion light years in every direction. So now we have 2 points on opposite sides of the sky that can be seen to be the same temperature, because a long time ago they were, but then they got shoved very far apart, and now we're just getting the light from them today. And that's what we mean by that dashed line in the third one over to the right. We're finally seeing the light from them today, because that light now is just getting to us, and it has the same temperature. All the other particles of light have either gone by us or not yet gotten to us from outside of there, because the horizon is not yet expanded for us to get to them. And by expanded horizon, I mean the universe has to have a certain age for that light to get to us from there. That's what we mean by the dashed line. That's where the universe has had a chance to get for light to get to us from there. So these points, A and B, were in thermal contact, then they got shoved really far apart, and now we're finally seeing them after we can find that the light from them is now finally reaching us after they emitted it 13.6 billion years ago. All right. The inflationary epoch also solves the monopole problem in a rather normal way, because we would say the universe expands exponentially, so it became 10 to the 43rd times larger, but then the number density goes as that size cubed. So now the number density dropped off like e to the 300, so we would expect after the grand unified theory epoch, if there were 10 to the 82nd, that's a huge number. If there were 10 to the 82nds per cubic meter formed in the gut epoch, just at the beginning of the inflationary epoch, then after inflation, there would be 15 per cubic parsec. And then the universe expands and expands and expands and pushes them farther and farther and farther apart. So now we would expect only one in 1.1 times 10 to the minus 61 monopoles per cubic megaparsec. So basically the universe is expanded such that they're all so far apart that we'll never see any one of them. And the chances for us of having one inside of our horizon are practically zero. So we shouldn't expect any of them in the universe at all. Even if 10 to the 82nd were formed, we won't see any. If we did see one, it'd be one big thing, and we'd probably notice it. And if there were many formed, we would really be noticing them and people would be talking about them. But the fact that nobody talks about, today we have a bad magnetic monopole day, so don't go outside today without your jacket, that doesn't happen. So since that doesn't happen, there's almost none in the universe, and for that, because the universe, even if it did form them, they're all really far away. So how did it do that? Well, the universe at that time, prior to that epoch, was in a state what we call a false vacuum state, meaning it had energy. So the Planck epoch, universe itself had a certain amount of energy associated with being itself. But that's a false state. There was nothing in it, so it's a vacuum of space-time stuff. And if there was a strong enough another strong enough hit, then it would push over that hump and then drop from the false vacuum state to a true vacuum state and release that energy. It is that releasing of the energy that creates the inflationary epoch itself, going over that hump with a big enough bump, and then oscillating at the bottom, like a little ball rolling backwards and forwards at the bottom of the true vacuum state in order to get that. And that so we can think of it as being supercooled. Just if you Google supercooled water, what I'm showing here is water that's been supercooled. So as you pour the water out, it actually freezes as it hits something. So the water is super cold. It's colder than ice. So if it hits any kind of thing upon which it can nucleate and form ice, it goes instantaneously from a water state to a liquid, to a solid state. That's the same thing as this. It's been super cooled, or the universe has been put into a false state of liquid. So all you need is a perturbation, a little lump, a little bump to push it over into the true state that it should be in, which is less energy. And when it does that, it releases that energy in the form of heat. And that's what you get. So what does that heat do? That heat creates bubbles. So as the universe bubbles and bubbles, during the inflationary epoch, as it rolls around, as it tries to come to a stop, and the energy of the inflationary epoch is effected into the cosmos, the energy that gets released as it bumps back and forth along close to the true vacuum releases energy in the form of particles and perturbations. Those perturbations then are dragged larger and larger by the expansion of the cosmos. And that's what this graphic is showing you, is that each of the perturbations, which is a lump of space-time that is growing, creates little pockets of energy density or mass density in the grand unified epoch. And they grow and grow and grow and grow. And the energy density of those perturbations then can be modeled. And as we model them, we find that, okay, from our viewpoint on the very right-hand side, is today, we look back in time and we see on the two red lines where the cosmic microwave background should be viewed, the two opposite the sky lines have the same temperature. And the reason they have the same temperature is because the thing in the middle has the same temperature. And so each size scale gets smaller and smaller and smaller of angular difference between them. And so we can then look at that as our resolution of looking at the Planck probe, meaning we had some really, 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 really tiny thing on the left-hand side. It exponentially expanded and then grew normally, and the horizon eventually caught up to it. But the middle band is the horizon crossing, which is when we actually see the objects, when we actually see the lumps and bumps. So those arrows that are called horizon crossings are when the lumps and bumps are moving back and forth across the cosmic microwave background. So the cosmic microwave background imprints the data of the early Planck epoch. And this exact set of patterns, the statistical analysis of the cosmic microwave background, is the shape of how much intensity or power there is at different angular frequencies or angular sized separations in the sky. That is determined, or at least there's a predicted thing that comes about from what I described before, which is the inflationary epoch occurred. There were little lumps and bumps that occurred during the inflationary epoch. They all were forced apart and forced to grow exponentially as they grew. And then once the universe stopped growing exponentially and all that latent heat of the false vacuum is done, then those perturbations, which were random and forced to become, they forced to grow exponentially, that will create lumps and bumps and waves in the early epoch of the energy distribution of the cosmos. And those will provide tiny anisotropies that will then grow. And when they grow, they will grow to a certain size. And when the universe is 350,000 years old at the time of the cosmic microwave background, and the appearance of the cosmic microwave background that we see in the sky is directly consistent, is completely consistent with that interpretation being the inflationary epoch did occur. So then let's hunt for it specifically. What are some other things that could have done? So they actually hunting for the signs of the inflationary epoch in the cosmic microwave background. And this is a team down in Antarctica that looked at with a microwave telescope called the BICEP 2 crew. And they were looking at specifically for cosmic microwave background to see if they could see a particular signal from it. Now, in the cosmic microwave background, there are two ways that light can be polarized. And we can see that the electrons in the top one, if they're density waves, the electron gets kind of shoved back and forth. And so it'll be shoved either towards you or away from you, and you get this E-mode polarization, which is very standard, and you find that in the cosmic microwave background. However, if there's a gravitational wave, then the electron gets squeezed and stretched. And as it gets squeezed and stretched, its electromagnetic field gets squeezed and stretched, and that changes the polarization of the light into what we call a B mode, or a kind of a curlicue mode, or something that has curls to it, like rotational. The E mode is just back and forth or up and down, but the B mode is rotational, and such gravitational waves should occur in the early cosmos due to the inflationary epoch. And this was their signal that they claimed, which was anomalous because they did not take into account the foreground Milky Way, but we can certainly see the attempt to show the curlicue-ness of that. Unfortunately, this can also be masked by the Milky Way doing the same thing. But this was an anomalous paper that came about, and they had to retract it later. But in any event, if once we model the nature of the Milky Way and go look for really clean areas of the sky that don't have that, or at least know exactly how the foreground Milky Way affects the background, then maybe we can see it. Maybe the B mode signal can be seen. And that would have occurred during the Planck epoch. So if you can get this, you're actually looking at the inflationary epoch. That's a big thing. So a current research topic to do is to create a polarized map of the Milky Way so that it can be subtracted from the cosmic microwave background to find this signal in truth. And that's what we mean by it. There's the different kinds of polarizations that we have. Okay, so inflationary epoch solves the major things. It solves the flatness problem, it solves the horizon problem, and it solves the magnetic monopole problem. There is observational evidence for it, and there are observational tests for it. Finally, then we ask, what about the beginning? The Planck epoch is a time. What about time equals zero? What about the absolute beginning of the universe? The Planck epoch would be a time, and there wouldn't even be this thing called time, because space-time and gravity, which defines this nature of length and time and space, doesn't even exist yet as a thing. All there would be during the Planck epoch would be essentially black holes, wormholes, white holes. Space-time itself as a concept doesn't even exist. It's quantum space-time, so we don't even have a concept called space-time yet. So quantum gravity means there is no such thing yet as space-time, which is really weird. So how can you talk about time when you don't even have a thing called time yet? So it would be this perfectly chaotic, purely symmetric, unchanging, because there's no time, pseudo-meta-uber epoch, where everything is just these wormholes and black holes, and it's incredibly small, incredibly high density, and eventually some perturbation breaks off to form the rest of the cosmos. If there's a tiny phase state, then there would be a tiny change and then accumulation of some wibbly-wobbly, timey-wimey stuff, and then you go off you go to the gut era, and gravity breaks away, and boom, and all of a sudden everything occurs. Prior to that, there wasn't even a thing called time, so we really don't even know if there is a thing called time, or even if the time equals zero as a concept even has any meaning. That's a very strange thought, to think that there was no thing called time, so we can't even say that time equals zero is a thing, because we have to start from a time equals first step, which is a weird thought, the first step being the Planck time. So once there is a time, then the first time is the first 10 to the minus 43rd seconds of time. It's more like to say it's all a mess, and then the first step occurs. So the first step is a breaking of symmetry such that time exists. That would be the first step. A breaking of symmetry such that time exists. So you can even think of it backwards and forwards in time. It doesn't even matter. There is no such thing as time yet. So once you do that, you break time, you break the symmetry, time begins, and then you get the Planck epoch. Prior to that Planck epoch, nothing we can speculate. There's some quantum gravity. We don't know what this is, but it can't look anything. General relativity must break down because general relativity can't really apply on the quantum size scales. It must be something like that. So people really think that there must be something like quantum gravity and that spacetime itself becomes unified with the other forces in some weird way, and spacetime as an object itself must go away on the highest timescales. On the smallest timescales, the highest energies and the highest densities. However, nobody has a quantum theory of gravity at this time, so nobody can really answer it. And therefore, a lot of things are happening inside that first minute of the Big Bang. You have the quantum epoch. You have the earliest times when it was just this supergravity, space gravity, timey-wimey, stuffy fluff prior to 10 to the minus 43rd seconds. And then gravity breaks away from the grand unified epoch. You have the inflationary epoch. That then occurs up until 10 to the minus 36 seconds. And during that time, you have like crazy black hole-y type things that are creating perturbations. They then separate out after the inflationary epoch and reheat the universe to make a light and photons and leptons and so forth. And then the electroweak breaks away, and you have matter and so forth breaking apart. Eventually, by about a minute or so, you have simplified down to protons and neutrons and electrons and photons and neutrinos and things like that. And you finally have four forces once just before you get to a second. And then you can actually form normal matter. So a lot of things happen inside the first second of the cosmos, and we have a lot of knowledge down to the idea of what we think is happening inside the first second. Much of the ideas that I talked about what the first second are the source of incredible research, but the picture is probably pretty good. It just needs to be fleshed out more, and the hard part is to actually get observational evidence, and hopefully B-mode cosmic signals inside of the cosmic microwave background can show that. However, the cosmic microwave background itself shows evidence in terms of that the inflationary epoch, if not correct, then something an awful lot like it happened. So if the Big Bang did not occur, something really much like it did occur. And just to make a more simplified appearance, here it is. We have some crazy thing happening at the inflationary epoch, and when quantum fluctuations created the cosmos, there was a major afterglow of light from the universe from 350,000, 380,000 years after the Big Bang. Then light, there were no stars until about 400 million years after the Big Bang, when the first stars form, and then galaxies form, and then galaxy clusters and planets and other elements and heavier elements, and eventually we get us on the right-hand side. But the early cosmos, whatever happened in those first few moments, meaning 10 to the minus 36 moments, is imprinted on the cosmic microwave background. And detailed studies of that demonstrate that the Big Bang as a thing did occur, or if it didn't occur in the picture that we've been talking about in the last few lectures, if that didn't occur, then something almost identical to it did occur. And that's kind of it for the nature of the origin of the universe. All right, we'll see you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Well, this one's going to end the entire series. It's about the end of the universe. So this is a good way to end the series on introductory astronomy, and this is going to go a lot of really crazy spots. So let's see what happens. So this time we're going to be talking about the way the universe will end. And so this is, again, the class could be entitled A Million Ways to Get Killed, but this is the way the universe gets killed. So let's see how it dies. Isn't this interesting? Okay, so next, first things first, we're going to talk about we have to incorporate and reincorporate the concept of general relativity as applies to the entire cosmos. As we learned before, we know that general relativity says that space-time tells mass how to move and mass tells space-time how to curve. And from our previous discussions about the Big Bang and all sorts of things, the expansion of the universe, we learned that if the universe is isotropic and homogeneous, and it can be described by a relatively simple metric, and that metric says how the universe will expand and with time. And so how it expands with time depends on what's in it. So the mass and space and energy that's embedded inside the cosmos will tell the universe how it should curve and also how it should expand as well. All right, so the fate of the universe depends upon its contents. As we said, it has to be homogeneous and isotropic, and it will, if it is homogeneous and isotropic, there's only two possibilities. Actually, there's a third. It can expand or contract uniformly across the entire universe, and that's the nature of the assumption underneath the Friedman-Robertson-Walker metric, which posits an isotropic homogeneous universe on the largest size scales. Now, of course, the flow of the expansion is halted because inside of like the Earth, because the Earth is gravitationally bound, such also is the Milky Way, so is the local group, so is the local supercluster. But when you get size scales much larger than the Hanukkah supercluster, then you are experiencing the expansion of the cosmos. And that's uniform and uniformly across the cosmos. All right. The other way of possibility is if it was completely standing still, then it would stand still forever, but that's an unstable situation. So if there was a tiny, tiny, tiny change, then the standstill would either expand or contract. So the contents of the universe dictate what's going to happen. And in the simplest possible models of the universe, in which I grew up with and dealt with when I was in college and grad school, was that the universe was only considered to have matter in it, matter and light. Those are the only things that people thought they were. And in fact, people understood that the energy density due to light and radiation, or more specifically ultra-relativistic things like neutrinos and so forth, contributed not as much energy density to the cosmos as regular matter and cold dark matter. So if cold dark matter and normal matter were the only thing, then the destiny of the universe would depend 100% on the density of the matter. And for a high density universe, for a very, very high density universe, greater than the critical density, then it would collapse back down eventually to a big crunch, meaning the expansion would slow down and then reverse if the density of the universe were greater than the critical density and it were completely made of normal or dark matter. If it were lower density than the universe, than critical or flat, then the universe and composed only of dark matter and normal matter, then the universe would eventually get larger and larger and larger and expand and expand and expand and in fact expand forever. And its rate of expansion would gently increase, but it would certainly expand forever. And that's called an open universe. And that would mean a big freeze. So pretty much the idea was, when I was in grad school in the 90s, people were trying to measure the matter density of the universe and therefore how fast the universe was decelerating. And that was the big idea, is that the matter was what was in the universe. So the density is the destiny. So people wanted to know how long in the future it was before a big crunch, or how long it was in the future before a big freeze. That was the ultimate concept of the 1990s. And that was one of the reasons why the Hubble Space Telescope was launched to determine what we're going to talk about today. So this particular graph shows the scale factor. Now remember, the scale factor shows the rate of shows the expansion of the universe now as opposed to then, or later compared to now. And so the y-axis on this graph could be the scale factor, meaning how much bigger tomorrow how many times bigger it'll be tomorrow than it is today. And that's what we define to be the scale factor. Today at now, we define the scale factor to be 1. Remember, the scale factor, though, was defined by the redshift. So the redshift itself, remember, Hubble went back and looked at the expansion of the universe and discovered that every galaxy had a redshift. So this v of redshift, meaning the speed of the redshift, or the recession velocity, that is the v in redshift, is equal to the speed of light times the redshift value that was measured. where the redshift value here is defined to be the ratio of the scale factors of now and ago, so that high redshift means smaller scale factor. Remember, redshift is directly related to the change in wavelength compared to the original wavelength. That's the definition of redshift. But we also then related the redshift to then the scale factor. So if we look, we find that importantly, the expansion velocity then is related to what we call the Hubble parameter, which is h of h as a function of time, and d, the distance between two objects, as a function of time. So the velocity, the recession velocity, as a function of time, that's what that parenthesis t means, is equal to the time derivative of a, meaning a dot, and a dot simply says, how does the scale factor vary as a function of time as the universe ages, or what was the scale factor's change, how has it changed with time compared to today? So that's what the a dot over a means. How has the scale factor changed with time compared to the scale factor itself? So whatever the scale factor is at a given time, how is it currently changing with respect to that moment? And that gives you the Hubble parameter as a function of time, of distance today to a given object. All right, so we can then say a very interesting thing. We really don't know a priori how the universe scale factor changes with time. We really don't know that. So the scale factor itself is kind of unknown, so we don't know it. Since we don't know it, we can use a mathematical trick. And this mathematical trick is called a Taylor expansion. And this is commonly used all throughout mathematical physics, where what you do is you say, I have no idea how this particular thing is a function of time or distance or space or what have you. You just have no idea. But what I can do is I can say, well, I know it doesn't vary wildly. I know it doesn't vary crazy time. So what I can do is I can take first and second derivatives of that function with respect to time, multiply it by the time it is changed by, and we can see, okay, so we take the scale factor, a as a function of time, and say, well, what is it today? A is a function of t naught, and t sub 0 is the time today. So we can say it's equal to that. Fine. So how has it been changing as a function of time now? How is it changing now? And then multiply that by the difference in time you're trying to measure, meaning t minus t naught, meaning ago compared to today. Then you add on to that the second derivative with respect to time, and that's usually called an acceleration, times the difference in time squared. And this sum goes on forever. It's an infinite sum, and it's called a Taylor expansion. I invite you to look it up if you want. However, what we can do is we can say this is just a way of saying we have no idea how a as a function of time actually works, so we're going to do a mathematical approximation of it, assuming that it doesn't vary very crazily, and that's called a Taylor expansion. It still is a function of redshift and time and so forth, but right now we say it has a function of time, but we really don't know what it is. All right, so then we assume it is smooth, it's not wild, and so we can shorten the infinite sum to just the first few terms, because if it's not wild, then those little terms are going to vary very, very short period, very small, because a very tiny difference in time, say the t minus t naught, will become really small as time goes on. And the higher derivatives, meaning the change of scale factor with respect to the change of the scale factor with respect to the change of the scale factor with respect to time, you mean like so how it changes multiply with respect to time. Those things are very small changes, so we don't really notice them. So there's not a really big acceleration, there's not a really big change in acceleration, there's not a really big change in the change in acceleration. So basically it's moving really smoothly. So if we do that, then we can approximate that infinite sum with this very simple little equation. And that's what the twiddle is the a is approximately equal to. That's why we make the bendy line equals. The bendy line equals says that we're making it approximately equal to. And we're saying that the scale factor of today equals 1. So that's okay. We've known that. We've done that all the time. So if we have the scale factor today, the scale factor of any time is approximately to 1 plus the Hubble constant, which we measure today, times the time compared to today's time, minus a half times this new thing, Q naught, times the Hubble parameter squared times the time squared. So we kind of keep that Hubble thing squared. So we have this one thing there, but we square it. But then the Hubble, the Q naught is a new thing. And notice we changed the plus to a minus, but all right, that's fine. So we can make a new definition, and this is an approximation, and we define a bunch of things based upon that. So what's this Q naught? Q naught is called the deceleration parameter, and it came back. It arose because back in the 1950s, people knew that the Hubble constant wasn't necessarily constant, or they said, well, perhaps it isn't constant. Perhaps the scale factor and the rate of change of the cosmos expansion has changed with time. So what they did is they said, fine, let's do a Taylor expansion. And somebody figured, well, the universe should be slowing down because it's got a bunch of matter in it. So this was back in the 1950s. And people said, so if the universe is going to be slowing down, we want to see how fast it's decelerating. So Q naught was called, back in the 1950s, the deceleration parameter. And people thought the universe back then was closed, that it was going to collapse back in on itself. It was more philosophical than anything else, and also because they didn't understand the size scale of the cosmos at the time. But it seemed to make sense at the time. So they defined it to be the deceleration parameter. So they wanted to know when the big crunch or when the deceleration would turn around and how long the universe would live. So Q sub naught is defined to be, and that's what the 3 bars mean, is defined to be the negative of the second derivative of the scale factor, that's what the A double dot means, times the scale factor divided by the first derivative with respect to time of the scale factor squared. And that's kind of a weird way of talking about it. It's a very strange definition, but it allows us to then say, look at, that actually ends up being the acceleration of the scale factor is a unitless number, so it's not actually a distance. It is a factor that you multiply a distance by in order to see how big it is tomorrow as opposed to today. So the scale factor then has a double dot over the A, and that means it's an acceleration. It's a change of time and the per second, per year, what have you, compared to the scale factor. And that's divided by the Hubble parameter, and that's how it's all been defined. And so that's been inserted. That Q naught goes back into that equation. And this is the definition of the deceleration parameter. And it measures how quickly or how slowly the universe is changing its Hubble parameter. Right? Remember, the Hubble parameter said that Edwin Hubble said it is going at roughly 70 kilometers per second per megaparsec. And that's a linear relationship. That's what he found. But back in the 1950s, when people really had no idea, they said, fine, if the universe is expanding, there's a scale factor. If that's the scale factor, then maybe there's a change in the scale factor. So let's create the deceleration parameter because it's got to be slowing down because matter pulls on matter. So it's expanding. It's probably slowing down. So let's define it this way. And so they did. Now the deceleration parameter can then be plugged back into another very important equation from general relativity. And that is one of the other fundamental equations that arises from general relativity and cosmology, and the simple concept of an isotropic, homogeneous, expanding universe is that the acceleration parameter, A double dot, compared to the scale factor, so on the left-hand side we call it acceleration equation, is equal to some crazy bunch of numbers, 4 pi times the gravitational constant divided by 3 times the speed of light squared. And that big sigma, that big letter E, which is a Greek sigma, means the sum of. And the little w means a bunch of things like w, sum of all w's, where the sum is the things to the right. And E is the energy density of one parameter of W. So maybe energy parameter this or energy density of that. And then times 1 plus 3W. So every energy density does something different to the acceleration parameter. Now, for normal matter, like atoms and molecules and even dark matter, the W is 0 because it doesn't do it doesn't do anything different to the acceleration. Either it's there or it's not. It pulls by gravity. It does nothing any different. So it just behaves like normal energy density that we perceive. For radiation, like light or neutrinos, W is equal to 1/3. So that changes the little thing to the right, so that becomes 2 EW, right? So you get this 1/3, and it's what, 2 times EW. So whatever the energy density E sub W is for radiation, whatever that is, that's what it is. It's twice that. So it contributes twice as much to the acceleration as normal matter. And then if we say some concept like dark energy, or more specifically what Einstein called a cosmological constant, we would plug in W is -1. So then that becomes if W is -1, then that thing on the right becomes -2. And then the acceleration, if you look closely, it becomes positive. And that becomes instead of a deceleration, this whole thing's been defined in terms of a negative acceleration. A negative acceleration is a deceleration. Everything is a deceleration. So matter provides deceleration because on the right-hand side it stays negative. Radiation, like light, provides a deceleration because everything on the right stays negative. However, for dark energy, if you plug in a -1 into W, and you see just the components, so make it just like the only W component. The big sigma says we're going to add together normal matter and radiation and dark energy or anything else. We don't even care. We just have to know what its W is. Maybe there's some crazy sort of thing where the W is equal to like 4 or minus 1/3, or maybe it's equal to like 1/2 or something. Maybe there's a different W. So you have to say, oh, the energy density of the stuff that is W equals 1/2. But so far, there's only really 3 things that we care about: normal matter, light, and maybe dark energy or cosmological constant. So notice that if you plug in -1 for W and consider only that and get rid of the sigma with the W below it, then it becomes positive, and it's an acceleration as opposed to deceleration. And that kind of helps because when Einstein first created the cosmological constant, remember, he thought it was done to balance against the pull due to matter, because matter would pull as a negative. So he said, let's throw in a cosmological constant and have it be this stuff that pulls, that pushes. And so he said that would be a -1. And that's where it comes from. That's why even anybody was even thinking about it. Now, the acceleration equation can be twisted and turned around, and something can be done slightly differently. We can define it in terms of the deceleration parameter. This equation can be defined that way. So let's see how we can do if we do that. If we define that equation in terms of the deceleration parameter, Q0, and instead of energy density, we use the density parameters, those omegas, which means how are they compared to the critical density. And we would say the sum of all of the omegas of different components, W's, times whatever that fracting off is to the right. That gives you the deceleration parameter. So let's see what that equation looks like more simplified. The deceleration parameter for normal matter, remember W0. For radiation, it's 1/3, and dark energy or cosmological constant is -1. Now, cosmological constant I graded out because that lambda would make the cosmological constant. And that's what Einstein did to put in there. And he said, oh, there's no evidence for it. And once he found the Hubble's expansion later, because Einstein thought the universe had to be static, so he plugged that in order to give something to keep the universe from collapsing. It's because he figured, oh, the universe is out there, it must be collapsing, so I'm going to put this thing in there to force it apart. And that's the cosmological constant, which has a W of -1. So what he did is he tossed that in there. And so in Einstein's tradition, when he found out about the expansion of the universe, he said, oh, this is terrible. This was the greatest blunder of my career. So he disavowed the cosmological constant. But he wrote about it and talked about it, and the mathematics was done. So people kept it around just as, put it on the shelf. So, but after Einstein, people said, well, they didn't think of that anymore. They didn't think the universe was static anymore, so they didn't see a need for it. So they only thought of the first two that are not grayed out. They said, what is R for radiation, and what is M for normal matter? So that is the deceleration parameters for both. And so it's like, well, okay, what constitutes how much of the critical density is there? Because if the deceleration parameter is positive, then it's decelerating. And if it's negative, then it's accelerating. So that's how we would look at this. So the question is, how much deceleration is there? How much matter is there in the cosmos? How much energy density is there from the cosmos? Because looking just at this equation, normal matter doesn't provide a negative energy density, which is what the omega can never be. It can never be negative for matter, and it can never be negative for light or neutrinos. So the deceleration parameter must be positive if the universe is only composed of normal matter and light. And that's why I grayed out the thing to the right, because it's not yet discovered yet. So let's see what it is. So the next big question for everyone was like, we got to figure out a way to measure how much stuff is in the universe to determine the deceleration parameter. And that was consumed most of cosmological study from the 1950s all the way through the 1990s. It was a 40-year quest to understand both the Hubble constant and the deceleration parameter. I remember that from college. It was like the quest for two numbers. H naught and Q naught, what are they? That determines the future of the cosmos. That was a big deal. It still is, but it's not as big a deal today as it used to be. We'll find out shortly why. So what are these things? Well, there are three sources of matter and energy density in the cosmos that we know of, that we can easily measure, or for the purposes right now. Radiation, which is photons and a lot of cosmic neutrinos. We know neutrinos are out there in scads because of supernovae and the sun and so forth. But all of that, the neutrinos are swamped by the energy density of the cosmic microwave background radiation. But that's an incredibly tiny part of all the energy density, because the universe has stretched the photons to the point where they're microwave photons. Now, if you went back in time, there'd be the same number of photons, but their lengths would be not as long, their energies would be higher, they would actually be much more dense. And that's why when we look at the early cosmos, it's radiation dominated, but the later cosmos becomes matter dominated and otherwise dominated. So the cosmic microwave background and all photons from all stars, actually photons from all stars in the universe that have ever been made, and all neutrinos that have ever been made, are less energy density than the cosmic microwave background. So light doesn't do too much. And so we can basically ignore that part of the thing. So our next step is, what is normal matter? And normal matter can be called baryonic matter. And that's kind of a weird word, but I'm not going to get into why it's called that. But baryonic matter is like gas and molecules and stars and planets and people. So that's baryonic matter, normal stuff that you stub your toe on and that you eat for breakfast. That's baryonic matter. So the current measurements of normal baryonic matter across the entire universe are about 5%, or 4.9% of the critical density of the universe is in the form of baryonic matter. And that is interesting, because if we say then most of the baryonic matter that we would encounter, planets are really small compared to stars. So if we then say, what is the contribution of baryonic matter from stars, which is like the sun and Sirius and Betelgeuse, that's really tiny. That's 4%, 0.4%. So most of the baryonic matter is in the form of hot interstellar and intergalactic gas. So stars make up almost just like only 10% of the normal stuff. So most of the baryons are formed of intergalactic hot hydrogen and iron gas permeating the galaxy clusters. And that's what we saw in cluster physics previously. However, we found that dark matter, because of cluster dynamics and how the Milky Way is rotating and how galaxy clusters fit together, that actually galaxy clusters show that dark matter constitutes about 26%, or is 26% of the critical density. So essentially adding everything up there, so dark matter dominates the total matter content of the universe today. So of all matter, if you add it all up, it gives you only 27% of the critical density. So it's not enough to make the universe flat. It's less than flat. So therefore it is under it's an under critical density universe. So what does that mean? So the universe would be matter dominated. If the universe were matter dominated, then the total density of the universe right now, that's what omega sub naught means, is basically equal to the matter density, which is 27% of the critical density. That means it's less than 1, and it's too little to stop the expansion. That means the universe would have an open hyperbolic geometry. We saw that with that weird saddle shape. There's no funny effects like the spherical geometry. And it would be open, and it would expand forever, and because there's matter in it, that expansion forever would decrease very steadily, and that's if you only have that in it. And during the 1990s, when I was in grad school, that was exactly the state of affairs. And the main goal of cosmology was to actually determine this deceleration parameter and prove whether or not this is true, and see by looking at the global deceleration parameter across the entire universe whether or not this was going to hold up everywhere. Because cluster dynamics were one thing, Milky Way rotation was another, but let's look at the entire universe and see if we can figure that out. All right, so how can we detect the deceleration? Well, first things first, we've got to have a couple things. We're going to now write, we can say, the proper distance. So we want to know, to get deceleration, we need to know how fast two things are rushing apart or falling together. We want to say, how far are they now? How far were they then? How fast are they going apart? And that concept relates to an idea of farness. And the base idea of far is called the proper distance. And the proper distance in cosmology is to say, stop the universe. Imagine you could stop the universe's expansion. Just imagine you could do that. Just put on the brakes for as long as it takes and lay down a whole bunch of sticks to determine the distance to something. And that's called the proper distance. So what you do is you'd stop the universe's expansion for a short period of time, and then you'd say, what's the redshift to that object? And that's the z in this equation. And what is the measurement of a bunch of z's? And you'd have a proper distance to all of those things. Maybe you know how bright something is in there. Like somebody put 100 billion, exactly 100 billion watt light bulb in each galaxy. And because each one is exactly 100 billion watts, you know how bright it should be. So since you know how bright it should be, you know the distance, the proper distance, because how bright it is. All right, so that would give you this. However, we can't stop this. So the proper distance assumes that we can do this. But if you could somehow measure down the ruler sticks, that would be the proper distance, and then you'd measure the redshift from that galaxy to that galaxy at that moment that you laid down all the meter sticks, and that would give you, for a large number of objects, a statistical study that would give you H0 and Q0. However, what we can actually use that's better is called the luminosity distance. The luminosity distance is actually related to the proper distance, which is what you really want to get. You really want to get the proper distance. But the luminosity distance is related to the proper distance. Luminosity distance is what I just said a second ago. Imagine you know how bright something is. How bright does it appear to be? Now, that is dependent upon the distance. Remember, the distance is changing. Since the distance is changing, then it is affected by the redshift. The redshift, the expansion of the universe, actually affects that. So you have to take that into account. So the brightness, or the distance you would measure by knowing how bright something is and then measuring how bright it appears, is affected by the redshift. So you have to fold that in. That's where that 1 plus c comes from. And that's approximately equal to a slightly different equation. They're almost identical. You can see how the minuses and pluses are swapped. So they're almost identical. So that's the approximation equation. And so when you measure something, you want to find something that is where you know how bright it is. And that's what Hubble did. He knew how bright the Cepheids were, because Henrietta Leavitt created the period luminosity relationship. And so if you have a period luminosity relationship, you're measuring the luminosity distance. However, at very small redshift, they're the same thing. I mean, if you look closely at this thing, you see a z squared in there. So a small redshift, a z times a z, is going to be even smaller. So it's approximately just the thing that Hubble did. And Hubble only looked at small redshifts. So he could never have perceived the deceleration parameter at all in anything, because he was looking at things that were simply too close. Tens or hundreds of megaparsecs is simply too close to measure the deceleration parameter. Isn't that wild? We have to get something larger than 100 megaparsecs to begin to see this. So we need something really, really, really bright. So Hubble measured a very small, measured close by, and that's why we see the little equation down on the right. Because we take a z, because in the approximation that we have in the middle, the z times a z is going to be really small. So the deceleration parameter basically gets hidden by looking nearby. So what do we got to do? We have to look at high redshift, very large redshift, so that we can actually perceive the deceleration parameter. How do we do that? Well, first, we're going to find a population of things called standard candles that we know their luminosities. Hubble used the Cepheid variables. We can use other things when we talked about the Tully-Fisher relationship in the past. We talked about type 1a supernovae as well. And supernovae and brightest red stars, surface brightness relationships, any number of things, the brightness of the core of a galaxy, the rotational speed, the profile of an elliptical galaxy. There's many ways to do this. Some are better than others. Some are really good, some are really bad. But these things are millions or light years away, and they're looking at stars in large numbers, so it's going to be kind of a trick to get anything anyway. But let's pretend we can. So you measure the redshift to that thing, and measure the flux, which is the brightness that you get for every standard candle, whatever that standard candle is. And then you compute the distance, the luminosity distance, d sub L. And then you know what the luminosity of the thing is a priori because you know how bright it is from physics. Physics says this thing must be this bright. Okay, you compute the distance based on the measurement you take with the flux and the redshift you take, and that gets you that for every single one of your standard candles. You then make a plot of the redshift, c times the redshift, versus the luminosity distance, and that gives you the slope of that line. Gives you when it's very, very, very low, that's going to give you the h sub naught when it's low redshift. And this process that we just described, those 6 steps, that's what Hubble did. That's how Hubble did this with the Cepheid variables. And that gets you out to about 100 megaparsecs. To get farther than that, to see deviations from a straight line, the plot CZ versus DL, it won't be straight, or it's not necessarily straight once you get farther than 100 megaparsecs, because we want to see that deceleration parameter. So let's see if we can find it. And let's use a particularly bright object called a type 1a supernovae. And we know that these type 1a supernovae are good standard candles because these supernovae, these white dwarfs explode when they reach their Chandrasekhar limit. They explode when they get 10 atoms too many, so they're extraordinarily luminous, and therefore we can see them from when they're really, really far away. They have a specific kind of spectrum, and they're different from type 2 supernovae, and they also have a different light curve, so we can distinguish them. So you can distinguish a type 1 from a type 2. However, it's also expected that binary stars would actually be more common than supermassive stars. So an extraordinarily bright type 2 supernova should be less common in general than a type 1a. Why? Because remember, 60% of the stars in the sky are binaries, and a significant fraction of them are spectroscopic binaries. And as we saw way early in the course, is that binaries are really common, but supermassive stars are not. So a star that would become a white dwarf is common. A star that will become a neutron star is not. So you can have a binary star pair, one of them becomes a white dwarf, and then the other one dumps stuff onto it. So you should, in general, expect to see, if it's a supernova, it's more likely than not to be a type 1a supernova. So even if you make the mistake, it's still a pretty good mistake to make. All right, so this was a big search. This was an enormous undertaking. And because, here's some images. This was taken by Rees et al. With his process using the Hubble Space Telescope as well as stuff on the ground. But these are Hubble images showing supernovae in distant galaxies. And the arrows indicate where they are. So there's befores and afters where the supernova was discovered. Basically, point a very sensitive telescope at lots of different galaxies in the sky, make a big search, then go back to see if anything has appeared there that's different, and go back repeatedly. So you're going to go back and forth amongst many, many, many galaxies and try to get as many as you can and see if you can find any. Well, the answer is they did. And here's some more. Here's some more ones, those little dots in the center of each one, those are some. And then there's more. And there's a bunch of them floating around, and there's even more. So there's a lot of these things that we're seeing. And so the type 1a supernovae, there's roughly one every 1,000 years or so in a given galaxy. So all you have to do is go hunt for enough galaxies. If you look at 1,000 galaxies, you should see one. So if you look at 10,000 galaxies, you should see 10. That's kind of the idea. So now we actually ask the question, are they really the same? Are all these exactly the same thing? Because if they're not the same thing, then they're not a standard candle, and we can't do that. So what we do is we say, let's look at the light curves for all of these standard candles. And each of the colored dots indicates a time that they were looked at and when they were caught at their brightness. So brightness is up and down, and time is left and right, with the time progressing from left to right, and brightness going up and down. And if it's the same color, it's the same supernova. So you can see that there's many different colors. They all follow the same curve. Since they all follow the same curve, they must be the same kind of object. Now, I do mention something about a stretch factor here, and that's because the time gets stretched too. Remember, there's that redshift stretches times too, because it's stretching the frequency as well as the wavelength of the light. So it'll stretch the length of the curve, but once you take that into account, they're all the same. So type 1a supernovae, this curve showing a plot of the type 1a supernovae over a large group definitely tells us that yes, we're actually onto something by saying these actually are standard candles. So let's keep going. So here's what you can do. Let's go all the way back to our first thing. We talked about brightnesses and distances and things. Remember this is called the distance modulus equation. So we're digging this way up from way back in the first section. We talked about distances and magnitudes. So the first things on the left-hand side are the apparent magnitude and the absolute magnitude. And then there's the logarithm base 10, and there's the distance, the luminosity distance to the object in megaparsecs. Now we're not just doing parsecs, but we're doing in megaparsecs. Because we're doing in megaparsecs, we instead of adding 5, we add 25. So we then get a distance modulus, which is m minus m. So we just get that distance modulus is the thing that we care about. And because the capital M is the absolute luminosity or absolute magnitude, that's going to be our thing that we say, oh, this is what the absolute magnitude is. And we can say, what's the apparent magnitude? So m minus m gives us and knowing the luminosity distance based on the redshift, we can get a lot of information. For example, though, we can say what's the distance modulus to the Large Magellanic Cloud is about 18.5, and the distance modulus to the Virgo cluster, since it's 15 megaparsecs, that's distance modulus is 30.9. So clearly, the farther things are, the larger the distance modulus number is. So we can get a whole bunch of distance moduli for things at different distances. So the distance modulus is then only dependent on the apparent magnitude, right? So if you measure the apparent magnitude and you know what the distance is based on by that, we can get the absolute. We know that we can curl everything around to make sure we got the right thing. But that's not 100%. Because we're not measuring distances, we're measuring redshifts, right? We're associating redshift with distance. We're trying to, at least. So let's see how we can do that. So we measure brightness and we measure redshift, and we posit the idea of absolute luminosity. So we're going to combine this extragalactic distance modulus equation, not just the normal distance one, but for extragalactic distances on megaparsecs or more. And then we can plug that distance modulus equation, or specifically the d sub L, which is the luminosity distance, into this equation. Just combine these two things, plug the dl into the equation above, and make some approximations and yada yada yada. And then what we get is that we find that the distance modulus equation with respect to redshift, as opposed to d sub L, is rather simple. we have for that, well, it looks kind of complicated, but it's a sum of terms. And we have the Hubble parameter in there, we have the deceleration parameter in there, there's our Q naught and our H naught. We try to get a handle on the M, the capital M, which is the absolute luminosity, and we measure the apparent magnitude, which is little m. So if we know the absolute luminosity, capital M, and we can measure the redshift, z, we can measure little m and measure z, and do this for a huge number of things. It's basically a linear plot. Notice this looks linear or logarithmically linear in the redshift. Notice there's a log base 10 of the z, and then there is also just a linear relationship with respect to z as well. That's dependent on the deceleration parameter. So if you have enough stuff, you can make a line and see what numbers for H naught and Q naught fit. That's all you do. And that's what was done. So here is the plot from Rees et al. And Adam Rees and his team with the High-Z Supernova Search Team in 1998, as well as Saul Perlmutter and his team with the Supernova Cosmology Project in 1999. These two things were published together. And this distance modulus as a function of redshift for these objects for extraordinarily high redshift out to about 1. On the right-hand side is almost a redshift of 1. And what we're looking at here is that there's 3 lines going through the graph. And one of them is the critical mass density. Remember, we related the deceleration parameter to the content of the universe. We could have put that in there too. So we just went the deceleration parameter, just did that. But if we then say, what's the best fit deceleration parameter to this stuff? It's kind of hard to tell from this graph, but let's say we remove or normalize it to what we thought we knew. Because remember, the expected amount was about 30%. So the middle thing with the triple dots, 0.3 and no cosmological constant, which is lambda, omega sub lambda. There's no energy contribution from that. And the matter contribution, omega sub m, is about 30% of the critical density. That's the thing that everybody thought from the 1950s through the 1990s. So getting the exact value of the deceleration parameter is tricky. And as you can see, it's very tricky from this, because each of these dots is a data point, and the little bars up and down from it, those are the error bars associated with it. But let's normalize this to the look when we just say, let's just go around the 0.3. So let's actually take a slightly different view of it. And the dotted line again is the total matter density compared to the critical density, which is 0.3, and that's the dotted line going across the middle. The flat universe with mass made a flat universe is the deep dashed line that arcs to the bottom. Notice it kind of goes across and across and across and then arcs down at the bottom. So it's the one that meets the right-hand side really low, the one I have not indicated with a green arrow. The best fit for the data that they have is one where we have a flat universe and that the omega sub lambda is 0.7. So the best possible fit to all that data, it kind of looks scraggly, but it certainly isn't. There has to be something there that's different than matter. That's kind of scary. So their best fit to the data, and this is the data from the 1999 and 2000 papers and so forth in 98. This is the discovery papers, where they said the best fit includes an energy density of 70% of the critical density for the cosmological constant. And this is the data that they showed. So what about a cosmological constant? Let's go back to that equation that we had where we demonstrated. We find, okay, what do we get? Well, what does that mean? It says that if the matter and energy density is close to 0.3, and if the density of the vacuum energy or the cosmological constant is 0.7, then the deceleration parameter is negative 0.55. A negative deceleration parameter is an acceleration. That's an acceleration because it was defined in terms of deceleration. So a positive Q naught is a deceleration and a negative Q naught is an acceleration. So the best fit to the data was one where their deceleration is an acceleration. Now this is important because there are a lot of different ways that the deceleration parameter could have been measured. There's lots of different possibilities for how the universe can go in the future and how it can go in the past, but only measuring it can get you there. There are some toy universes, and we call them toys because they don't really happen, where we have a negative cosmological constant, it recollapses, or maybe there was no Big Bang and it just went down to a minimum size and came, well, like it started big, collapsed down to a minimum size, then re-expanded, so there just didn't get to zero size. Or maybe it had a Big Bang really long ago, and it didn't do anything for a very, very, very long time, and it coasted and then expanded. And maybe there's no cosmological constant and so forth. But what the measurements are showing is that there is a positive cosmological constant which makes the universe expand forever and accelerate. So that is the discovery of dark energy. And so they're best fit to the data, and that's what those arcing curves are all about. Remember how the data points were there? They tried to do their best statistical study to say what is the highest likelihood, and Reese and Perlmutter were competing teams. Perlmutter's team was called the Supernova Cosmology Project, and Reese's team is called the High-Z Supernova Project. And their values overlap quite well. And the old idea that I dealt with when I was in college is on the green line, where there is no cosmological constant, and so it would be in the decelerating universe parameter space. See how that decelerating is below the dot dot dot, and the accelerating is above the dot dot dot? So if there is a positive cosmological constant, and it is larger than zero, then the universe will likely accelerate. I mean, if it's not too big and there's a lot more matter, then it could decelerate eventually. But the funny thing is it lies right on their measurement lies right on the flat universe line, which is between closed and open, but it definitely lies above the accelerating thing. So we find that it's definitely not a no Big Bang, like a bounce universe. It's definitely, because that's way up high. So you have to have a huge cosmological constant, which is not seen in the measurements. So that did not happen. So there was some Big Bang. However, the universe has some component that is causing it to expand and expand and expand. The ovals show their best statistical fit to the data, and that's what that means. So here's something that they wrote up that came out in Physics Today, and this shows more about the nature of when the redshifts were dot and where their dots are, and you can see that the higher the redshift, the farther back it goes. And looking at that, we can see that the universe had first decelerated, then accelerated, or basically has been accelerating since about 5 billion years ago. It's definitely in the expanding forever category as we look in the farther and farther past, and it also is definitely in the farther ago. So really, when you look at the distance modulus, all it said was that the things were dimmer than they should have been. The supernovae were dimmer than they should have been. So that meant they're farther away now than expected. So the universe must be accelerating. That's basically what was found with the distance modulus. They were fainter. At a given redshift, they were fainter. And the bigger the redshift, the fainter they were than is expected. That's what that means. So if we found their galaxy's redshift in there, we could discover that basically that the universe has some sort of vacuum energy and it's likely accelerating. And that's what was found by Perlmutter and Schmidt and Reese. So Brian Schmidt and Adam Reese were the supernova, I'm sorry, I kept omitting Brian Schmidt from it. But Schmidt and Reese were the supernova team, High-Z Supernova Search Team, and Saul Perlmutter led the Supernova Cosmology Project. All right, so the next thing we see is here's from the Supernova Cosmology Products data themselves. And zooming in a bit, I have a slightly different view of that. And we see from Supernova Cosmology Product, only from their material, they say that it's about 0.28 and 0.72. No matter what, both teams agree that there must be something like that. And there's a very interesting story that you can find if you go hunting around about the nature of how this was discovered. Basically, there was an illicit email that caused quite a kerfuffle between team members who communicated to each other without going through the highest end people. So basically, one person tipped the other's hand. They were competing to get this information, and they basically tipped each other's hand. And as a result of it, Both teams got the Nobel Prize as opposed to only one. So if one guy or a few guys had kept their mouth shut, then likely only one of these teams would have gotten it because they would have announced it first. In any event, because they essentially jointly announced it, they jointly won the Nobel Prize in 2011 for discovering the acceleration of the expansion of the universe and opening the window into the new physics of understanding what the heck this dark energy stuff was. So that's not just from supernovae. In fact, the supernova results combined with other things, constraints by the from the cosmic microwave background missions such as Planck and WMAP that look at the cosmic microwave background, as well as extensive studies of galaxy clusters like BOSS, give and specifically later and much more accurate, much more precise results of being about 0.32% or 0.3166 of the critical density for matter, and this comes specifically from the from June of 2018 from the Planck team. That's what that archive link is for. Is 0.6847. So if you add those two up, it's almost exactly 1. They give almost exactly 1, which is really nuts. It's 1 plus or minus. I didn't get the error bars in there, but when we add the error bars in there, it's pretty much 1. So the cosmic microwave background studies, as well as galaxy cluster studies, support the idea that was found in this, which is a completely independent concept. Looking at the background light of the cosmos, it's very different than studying the other. And cosmic microwave backgrounds does that by looking at the distribution of lumps and bumps inside in there. And galaxy clusters look at how fast galaxy clusters appear to be, how the size and scale of galaxy clusters across the cosmos. So all of these things taken together say the same thing, that there is something called dark energy, which nobody knows what the heck it is. Nobody knows what dark energy is. Nobody has any freaking clue. What it is, no one knows. The simplest concept is it's probably a cosmological constant, and that means it's a W of -1. And that cosmological constant would simply mean that there's a vacuum energy component, meaning that the thing that we call space, the thing that we call spacetime, has energy associated with just being space-time. That is a constant, and so there's just so much stuff of energy that is part of it. And that's what a cosmological constant is. So as the universe expands, there's more space. So therefore, since it's constant, it doesn't dilute. So every box of space has the same amount of cosmological constant. So once you get diluted, once the matter gets diluted, you're only left with cosmological constant. So that's what's happening in the future. It's a very strange thing, and nobody knows what it is. It could be some other kind of dark energy, though, and people have tried to figure out exactly what the W is for dark energy. What is it exactly -1? Is it a little less than that? Is it a little more than that? Remember, W doesn't have to be -1. It can be something else. So that's another thing that's been checked. There's all sorts of weird things that it can be called, that it can, maybe the nature of the cosmological constant changes with time. Maybe it's only -1 over here, maybe it's -0.5 over there, maybe it's a whole bunch of things. So you can call it scalar fields or quintessence or lots of different things. A lot of them have to do with it changing with time or being different at different locations in the cosmos. But the Planck team, looking at their data, this comes from the July 2018 paper I referenced, says that they measure that the W, or what basically the equation of state, what the equation of state is for it is that it's pretty close to -1. And they're hoping, and the other thing is, it could be that if it's not -1, if it's less than -1, say it's like -2 or something, then we would call that a phantom energy, and that's a really weird thing. But right now, the current consensus is that the universe is composed of a cosmological constant, which takes up 70% of the universe's material, 68%, and matter and dark matter compose 32%, and that the universe is flat. So our universe is geometrically flat. It's not hyperbolic shaped, it's not spherical shaped, it's neither open nor closed, it is flat. And it is accelerating. It is a flat, accelerating, and infinite universe. And that's what we live in. And so dark matter composes 26.8, at the current date, 26.8% of the energy density of the cosmos. Normal matter is about 4.9%, but dark energy composes about 68% of the cosmos's, the entire universe's energy density. And as the universe expands, dark matter and ordinary matter will be diluted, and so those numbers will drop until dark energy becomes everything. So that's our current energy budget. Only 5% of the universe is ordinary matter. And of that ordinary matter, only 10% of it, or 0.4%, half a percent, is stars. So the rest of the ordinary matter is just intergalactic gas, of hydrogen gas, or basically hydrogen at extreme heat. So ordinary matter is not even planets. Ordinary matter is mostly intergalactic gas. The rest of normal matter is dark matter that doesn't interact with light in any way. And dark energy, we have no idea what it is. All we know is that it's forcing the universe apart and forcing it to accelerate in its expansion. All right, so that's where we get and so there is what we get from all these strange things. And really, no one knows what dark energy is. It's presumed that you can't actually make a box out of dark energy, and you can't box it into anything. But even though it's everywhere, and it's inherent to space-time itself. That leads us to say, what's going to happen in the future of the universe? So what will happen? So today in the future of the universe, because if the universe is going to do that, it's expanding, accelerating, what's going to happen? Well, today there's stars that are metal rich. More stars explode. If they explode, they make stuff, and then there's a little less hydrogen as time goes on, but there's pretty stars and planets and things like that, and white dwarfs are made, and neutron stars and black holes, but things get locked up in those things. So in about 6 billion years or so, the sun is going to be gone. It'll become a white dwarf, and that's going to be sad. But right now we're calling this the stellariferous era. Stars can be made and born in galaxies. And there multiple generations of stars can be made. And that's the current day, 13.8 billion years after the start of the Big Bang. However, in about 1 trillion years, which is a long time from now, about 1,000 times the current age of the universe, 1,000 current universe ages from now, the matter will be locked up in white dwarfs and neutron stars and black holes, and that will be all done. All star birth will come to an end. There will be no free hydrogen gas anywhere, and the last of the red dwarfs, those little tiny M-type dwarf stars, will burn out and become really, really, really low-mass white dwarfs. They will become the tiniest, coldest objects, and all the rest of things will be in black dwarfs or cold neutron stars and black holes. And all the stars will fade into a deep, deep night, and that will be the end of the era of starlight. All stars will go out. There will be no galaxy light. There will be no light from galaxies that come from starlight. So star formation will be done in 1 trillion years. Needless to say, that pretty much puts the kibosh on pretty much everything. In fact, we can go about 100 times farther if you wish to kind of think about it. The cosmos won't have any sources of energy in about 100 trillion years, in 10 to the 14th years, to support any kind of complex interplay of life. So no matter what, after the universe has become 10 to the 14th years old, currently it's 10 to the 10th, so 10,000 times the age of the universe today, there will be no capacity for life to exist anywhere in the universe because of the loss of energy. After 1,000 times more of those times, the solar system would evaporate due to interactions. Not evaporate like stars, like the planets themselves would come apart, but simply random interactions between the moon and dust and asteroids and Jupiter and Saturn and Mercury, or whatever's left in the solar system, and every solar system in the universe, of which we know there are many through the Kepler Space Telescope. They eventually would be scattered, so planets would be scattered out into the galactic medium that is now very dark, or if they didn't get scattered, they get swallowed up by the white dwarf or neutron star that makes up whatever they're at. So wide binary systems are broken apart, so everything is now evenly distributed, and they're all, or anything as close, gets pulled together, anything that's far gets flung apart. And so the expanding universe just means that these rare things where a planet might go by another planet get flung out. It takes a long time for something like that to happen, but 10 to the 17th years is a catastrophically long time because that's 100,000 times more time than the current length of the universe now. After 10 to the 27th years, which is 100 billion times longer than that, so we have to go 100 billion times more of those in order to get to the point where galaxies themselves, not just get spread apart because of interactions between stellar remnants such as black holes and dead neutron stars, and almost everything gets ejected and out from them, and they just go out. And so now there's no such thing as a galaxy anymore, and the rest is falling into the supermassive black holes at the center. Some of those things, if they coalesce into that supermassive black hole, the largest would become up to 100 trillion solar masses, which is much larger by a factor of 1,000 than any of the other any current supermassive black hole known. So galaxies would eventually spread out and not be recognizable in 10 to the 27th years. Even farther in the future than that, after 10 to the 32nd years, which is now, wow, really far, 10 to the 22nd times the current age of the cosmos, it is thought that protons themselves would be unstable. And if they are unstable, they would decay into electrons and positrons and neutrinos, and maybe even pions or something like that, which means that protons would disappear and matter would simply fall apart. And if matter falls apart, if it's not in a black hole, anything that's matter stops being what we call matter and basically becomes positrons, electrons, and neutrinos. And that's all we're left with. So that's going to be long, and nobody really has ever seen this decay, but it's possible that it's going to happen because, the strong nuclear force allows for things to happen, but the probability is extraordinarily rare. After an extraordinarily long period of time, 10 to the 67th years, stellar mass black holes evaporate by emitting Hawking radiation, and after 10 to the 106th years, supermassive black holes evaporate by Hawking radiation. This is enormous ending, and that is the end of all organized matter in any way. All that's left in the cosmos now is an rapidly accelerating cosmos filled or only gently filled with extremely long wavelengths of light and neutrinos and electrons and positrons. So after they're all evaporated, the universe is basically cooled off to a temperature of absolute zero. The only thing that's left is a formless thin gas of electrons, positrons, and neutrinos, and they're spaced apart by hundreds of megaparsecs, so they're not really touching. The radiation, the light, is incredibly redshifted photons, and in fact, probably the photons themselves would be much larger than the size scale of the universe today. So they would basically not even feel like photons to us. They would be very old, and the exponential expansion would make it very cold, very empty, with nothing in it. So a size scale of something like our current universe might contain one electron and might contain one neutrino and one photon. That's what's to happen in about 10 to the 106 years, and probably that's a very large number of one of each at that time. Probably none, probably nothing. It will all expand away. So that's kind of the heat death of the universe. There won't be nothing left. There won't be anything left. It'll just be cool, cold, and empty, and continuing to expand, and space will be bigger and bigger. However, if the equation of state of dark energy is less than -1, then it's still observationally possible, but it's not quite probable because of the most recent stuff that's come out by the Planck team. Then they would have a phantom energy, and it would eventually rip the universe apart in about 14 trillion years, where the expansion of the universe would be so fast that it would overcome the ability of the electrostatic force, the weak nuclear force, and the strong nuclear force to respond to the expansion of spacetime. And right before this, if the phantom energy was just minus 0.001, if W was just a little bit less than 1, the universe is done in 14 trillion years, like really done. or more like 20 or so trillion years. So it's going to take a while, but it'll happen. It'll rip itself apart. 60 million years before that, the Milky Way is torn apart by the expansion of the universe. 3 months, the solar system flies apart. 30 minutes before, the Earth explodes because of the expansion of the universe. And 10 to the minus 19 seconds before the rip, atoms themselves are torn apart. And it becomes kind of an inverse singularity like we had with the Big Bang, but it's just the universe expanding with nothing in it. That's a big rip. However, the Planck probe shows that we're in a flat, accelerating cosmos and not one with phantom energy. So this is very interesting to talk about, but it's probably not what it is. So the possible fates of the universe, some say the world will end in fire, some will say in ice, but from what I've tasted of desire, I hold with those who favor fire. But if I had to perish twice and think I know enough of hate to say that destruction, ice is also great and would suffice. And will the world end with a bang or a whimper? Is the real question. We don't know, but it seems like the world will end in ice, essentially. Not even in ice. Ice won't even be there. It'll be emptiness and cold. And so the end is a whimper, a tiny, tiny nothingness. How's that for you for an afternoon? Now, if we look then to the largest size scales and say outside of our cosmos, it's called beyond the particle horizon, meaning beyond every universe, what we can possibly know. What we can possibly measure, not know, but measure. There are lots of different things that we can talk about that we could go over in extended things, so I leave this as a list to you to go over and go hunt down, because this is really some interesting stuff for you to go investigate and learn about. Because to me, this has always been some of the most interesting things, like the chaotic inflation, meaning maybe the inflation happened here, or maybe it happened there. The concept, and it'll happen here, and maybe it'll happen again. So chaotic inflation has a very interesting concept. The concept of the land escape, meaning that there are many, 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 many universes, and the universe is much, much larger than our observable horizon. And there's a vast area where universes pinch off and expand from each other, but maybe they have different physical constants. Maybe the constant of the speed of light is different, or the charge of an electron is different. But then that leads to the concept of the anthropic principle, which is, our universe is funny. It has life in it. And if you change any one of those constants by a little bit, we ain't got nothing. Big number theory has some very strange things that say there must be some relationship between the big, big, big numbers because they all tend to be big and all the same rough value. The Poincaré recurrence says, well, if you let the universe age long enough, you eventually get the same stuff again. But that seems to be eliminated by the fact that dark energy is going to push everything apart. Multiverse concepts and brain theories posit that there are additional spatial dimensions that we do not perceive that then are literally right next to us. But since we don't perceive them, the only thing that leaks across is maybe gravity, and that would be what we call a brain. So they're as in membranes. So there'd be multiverses with the brain, the distance between them is millimeters, but in every direction. But we can't get there but maybe gravity reaches through. And that leads us to the concepts of like the many world string theory, and also the concept of many worlds interpretation of quantum mechanics, which says that every action you do creates a new universe. And that's an actual interpretation of quantum mechanics because of the nature of choice. String theory supports the concept of brain theory, which says that the fundamental things aren't atoms, but these tiny things that are strings that are 11-dimensional objects that you can only perceive their 11th dimensions if you're down on the size scale of 10 to the minus 43rd meters or so. For fun and enjoyment, I invite you to go look at author Greg Egan's science fiction novel Diaspora, which looks at all of these things that we just talked about in a very, really, really heady way. It's one of the most hard sci-fi novels, but I encourage you to go take a look at it. And I think that's a great way to end it, to give you something to go explore, because even as the universe is ending, we still have so many questions about the nature of nature. See you soon.